Welcome, curious minds, to the deep dive. Imagine this. You've just received a no.
Yeah, that feeling.
Maybe it's a bank loan rejection that puts your dreams on hold, a job application for that perfect role, or even a critical medical diagnosis that leaves you reeling.
Right.
The immediate frustration isn't just the rejection itself, but that lingering question, what if? What exactly could I have changed to get a yes? That craving for actionable feedback, for understanding the levers of influence, well, that's the core of what we call counterfactual explanations. Today, we're taking a deep plunge into a truly fascinating and I think incredibly timely research paper.
It really is.
It's aptly titled, What If, But Privately? Private Counterfactual Retrieval. Our mission for you, our dedicated listener, is to explore how those powerful, often opaque machine learning models can offer transparent, actionable what-if explanations without compromising anyone's privacy. This isn't just about slogging through dry technical jargon, right? It's about uncovering the clever engineering behind making AI more fair, more accountable, and ultimately, well, far more useful for you in your daily life.
That's exactly right. We're going to unpack a critical and I'd say often overlooked problem in the world of AI.
Okay.
How do we provide these invaluable what-if explanations while rigorously protecting the user's highly sensitive personal data?
Yeah, that's the crux of it.
So we'll journey through the inventive mathematical frameworks and schemes the researchers propose, discuss their inherent trade-offs because, let's face it, they're always trade-offs.
Always.
And then see how they actually stand up in real-world scenarios. Get ready for some serious aha moments. Because the insights here, they fundamentally shift how we can think about AI and privacy.
Okay, let's unpack this for a moment. Why are we even having this conversation about counterfactual explanations in the first place? What's the big deal with a machine learning model just spitting out a simple yes or no? It feels like a pretty common interaction with technology these days, doesn't it?
It does feel common, absolutely. But what's truly fascinating and, increasingly becoming a legal and ethical mandate in many jurisdictions globally is what's known as the right to explanations.
Right.
In high-stakes applications, think financial lending, insurance underwriting, or even medical diagnostics, a black box model.
Meaning we can't easily see inside how it decides.
Precisely. An AI system whose internal decision-making process isn't easily understandable or transparent. It can't simply issue a binary no without providing a suitable, comprehensible reason for its decision.
Okay.
This isn't just about, politeness. It's fundamentally about transparency, accountability, and user empowerment. If an AI is making life-altering decisions about your access to a loan or healthcare, you, as the individual, you have a fundamental right to understand the basis of that decision.
That makes perfect sense. So circling back to our bank loan rejection example, instead of just a flat denied, a counterfactual explanation would offer something concrete and actionable, something I can actually work with.
Exactly. Instead of just that frustrating no, a powerful counterfactual explanation would offer incredibly actionable advice. It might say, if you had increased your verifiable income by $10,000, your loan would have been approved. Or perhaps, if your credit utilization ratio was below 30%, you would have qualified for a lower interest rate. This kind of feedback is absolutely invaluable.
Right.
It's not merely an explanation of why you were rejected. It provides direct, actionable guidance on how to change the outcome in the future. It really empowers the user to understand and potentially rectify their situation.
And the paper touches on several desired properties for these counterfactuals beyond just being close to your original input, right? Because, a recommendation to change your age by 20 years might be close in some mathematical sense, but it's utterly useless.
You've hit on a crucial point there. While proximity, meaning the smallest possible change to achieve the desired outcome, is definitely a primary concern, the broader research in this field, and indeed what the paper acknowledges by referencing other works, highlights other vital properties.
Like what?
Well, for instance, robustness is key. You want an explanation that doesn't drastically change if the underlying AI model has slight variations, or maybe if your input has minor perturbations.
Makes sense?
Then there's feasibility. The recommended change must be something a user can realistically do, suggesting you instantly drop 10 years off your age, as you said, or, acquire a PhD overnight.
Not gonna happen.
Exactly. It simply isn't feasible. Sparsity is also highly desirable. The explanation should ideally suggest changes to as few attributes as possible. Makes it easier to act upon, less disruptive to your life.
Okay.
And finally, diversity is important. This means providing perhaps multiple distinct pathways to a yes, rather than just pinning you to one single option.
Interesting.
Now, this paper, while aware of all these dimensions, it primarily focuses on achieving proximity and actionability, which we'll dive into more later, all while maintaining that crucial privacy aspect.
So getting an explanation that's actionable and transparent sounds fantastic. But here's where it gets really interesting, and where this paper shines a light on a critical, yet often less explored, privacy concern. Most existing work on explainable AI, like some of the references mentioned, primarily focuses on protecting the institution's data, right?
That's generally true, yes. Protecting their proprietary AI model, their trade secrets, or their vast database of accepted customer samples.
But what about my privacy? The user who is actually asking for the explanation. I am the one revealing my incredibly sensitive financial, medical, or personal data just to get this what-if scenario. That feels like a significant vulnerability.
That's precisely the central dilemma this paper tackles head-on. It raises a very important question. Why would a user be reluctant to reveal their complete input feature vector, their personal data, to the institution, even when they're actively asking for an explanation?
Good question.
Consider a few scenarios. It could be about avoiding a limited number of application attempts. Maybe if I apply for a loan, get rejected, and then the bank knows all my current detailed financials because I asked for an explanation, well, that might be logged, maybe count against future attempts, or somehow impact my profile.
Could be.
More generally, it could simply be about preserving fundamental data privacy. Perhaps I just don't want to disclose my current, maybe less than ideal financial standing if I know I'm actively working on improving it before applying again. My current situation is private until I'm ready for it to be public for a new application.
Right, you want control.
Exactly. The core problem then is this. How can a user retrieve a counterfactual instance, that what-if scenario, without revealing their own sensitive feature vector to the institution that holds the model and the database? The paper makes a very strong, almost audacious promise to achieve perfect information-theoretic privacy for the user.
Wow, that's a huge claim.
It is, and it's backed by rigorous mathematics, which we'll get into.
This problem sounds a bit like trying to find a specific book in a massive library without ever telling the librarian which book you're actually looking for. Does it connect to other established areas of computer science or cryptography? Because it feels like a classic privacy puzzle.
It absolutely does, and you've hit on a great analogy there. The problem is deeply rooted in and skillfully leverages techniques from several fascinating and well-established fields. At its heart, yeah, it's related to the classic nearest neighbor search problem.
Finding the closest data point.
Right, where the goal is to find data points in a large data set that are closest to a given query point. But, as you pointed out, that privacy constraint makes it orders of magnitude more complex. The paper ingeniously leverages techniques from Private Information Retrieval, or PIR.
PR.
First introduced in some seminal work. In a standard PIR setup, a user wants to retrieve a specific message from a collection of, say, many replicated messages stored across several non-colluding servers.
Non-colluding meaning they don't talk to each other.
Exactly. They don't conspire or share information to try and figure out your secret. And the crucial part of PIR is that the user doesn't want any of those individual servers to learn which specific message they are interested in retrieving.
That's exactly like what we're trying to do here. Find the index of the desired counterfactual without revealing our personal input X that determines which index we want.
It truly is. And building on basic PIR, there's also something called symmetric PR, or cs.PR.
Okay, say PR.
Yes, SPIR. As detailed in some other foundational papers, in SPIR, there's an even stronger requirement. The user not only gets only their requested message and nothing else, but the servers still learn nothing about the user's request.
Wow, okay, even stronger.
This paper skillfully combines these PIR and SPIR ideas into a multi-step process, typically, to achieve both perfect user privacy and, to some extent, database privacy for the institution. The general process often involves two distinct steps. First, you privately find the index of the desired counterfactual instance in the database using a PR-like scheme.
Like finding the library shelf number without saying the book title.
Exactly. And then you privately retrieve the actual counterfactual itself using that index through a SPIR-like scheme.
Getting the book without the librarian seeing the cover.
Precisely. This two-step layered approach is crucial for their overall privacy guarantee, and it's a recurring theme we'll see in the more advanced schemes.
Okay, before we dive deeper into the specific schemes and how they actually achieve this seemingly impossible feat of private retrieval, let's quickly go over some foundational concepts and notations. Don't worry, we'll make this as approachable as possible, breaking down each piece. Think of this as learning the alphabet and basic grammar of the paper's language.
Absolutely. Understanding these symbols and definitions is key to appreciating the mathematical rigor and, frankly, the sheer cleverness of this work. They are the essential vocabulary for this deep dive. First off, we'll frequently encounter this notation.
Square brackets in.
Right. This simply denotes the set of positive integers starting from 1 up to n. So if you see 3, that just means the set 1, 2, 3. Pretty straightforward.
Okay.
Similarly, for ranges within a set, mn, that denotes the set of integers from m to n, inclusive. For example, 5.7 means 5, 6, 7. It's just a shorthand for listing sequences of numbers. Next, a very common notation, you'll see vertical bars around a set, like A.
Absolute value bars.
Looks like it, but here it signifies the cardinality of a set A. In plain terms, it's simply the number of elements contained within that set. So if set A is apple, banana, cherry, then A would be 3. For vectors, A with a superscript t, so AT.
Ah, transpose. Familiar from linear algebra.
Exactly. It represents the transpose of vector A. If A is a column vector, AT transforms it into a row vector. This is important when we deal with dot products or matrix multiplications later on. Now, a really crucial notation for understanding the cryptographic guarantees in this paper is F sub q. Right, FQ. This stands for a finite field, sometimes called a Galois field. Here, Q is either a prime number or a power of a prime number. The critical concept is that it's a number system where all arithmetic operations, addition, subtraction, multiplication, even division, except by 0, of course, are performed modulo Q.
Modulo Q, like clock arithmetic.
So that's a great analogy, exactly like clock arithmetic. Let me give you an example. If FQ is F5, the finite field with 5 elements 0, 1, 2, 3, 4, then 3 plus 4 would normally be 7, but 7 mod 5 brings us back to 2.
Right, 7 is 2 steps past 5 on the clock.
Precisely. Similarly, 3, 4 is 12, and 12 mod 5 is also 2. This wraparound property is absolutely fundamental to the privacy guarantees. It allows for arithmetic operations that effectively hide information by making results appear random if one of the operands is truly random. It's a cornerstone of modern cryptography. We also have H, capital H with parentheses.
H for.
Shannon entropy. In information theory, entropy is a formal measure of the uncertainty or randomness associated with a random variable.
So how much surprise is in the outcome?
That's a good way to put it. The higher the entropy value, the more uncertain or random that variable is. And closely related to that is I, capital I, semicolon in the middle.
Mutual information.
Exactly. Mutual information. This quantifies the amount of information you gain about one random variable by observing another random variable. If IXY is a high value, it means observing X tells you a lot about Y and vice versa.
But for privacy.
But crucially for privacy, if IXY is 0, it means that X tells you absolutely nothing about Y. There's no correlation, no way to infer anything. This concept is critically important because it's how the paper formally defines and proves its strong privacy guarantees. 0 mutual information is the goal for user privacy. And finally, we use a bold italicized font like A to denote a matrix.
Got it. Bold italics means matrix.
Yep. So whenever you see A in that style, we're talking about a rectangular array of numbers, not just a single variable or a vector. These notations collectively form the precise vocabulary needed to describe the mathematical constructions that underpin all the schemes we'll discuss.
Okay, and the paper relies on 2 truly elegant mathematical concepts that make their strong privacy guarantees possible. It's almost like they're building a cryptographic puzzle, and these are their master tools.
They absolutely are. These aren't just arbitrary choices. They are foundational to achieving what's called information-theoretic security, which is pretty much the strongest form of security you can mathematically prove. The first one is definition 1, the Vandermonde matrix. You'll see this in equation 11 of the paper. This is a very special type of matrix, quite beautiful in its mathematical properties.
Vandermonde, okay.
It's constructed from distinct, non-zero elements chosen from our finite field FQ. Specifically, if you have n distinct elements, say A1, A02, A01, then the entry at row I and column J of this Vandermonde matrix, let's call it EMEO, is simply IO raised to the power of J1.
So Amat to the power of 0, then I to the power of 1, IA squared.
Exactly. The first column would be all 1s. The second column would be all 1 A1. The third column would be 12 N1 2, and so on, up to the nth column, which would be R1. The absolutely crucial property of a Vandermonde matrix, and this is what makes it so powerful here, is that Precisely because its elements A1, Aon are distinct and non-zero, it is always invertible.
Always invertible. Okay, that's key.
It is. This means that if you have a system of linear equations where your unknown variables are multiplied by the elements of a van der Waals matrix, you can always uniquely solve for those unknowns. Think of it like a universal secret decoder ring. If you receive a scrambled message that was generated using a van der Waals matrix, and you know the matrix, specifically the odd values used, you can perfectly unscramble it and recover the original information by multiplying by its inverse. This invertibility is absolutely central to how the user can recover the true distances or other critical information privately. The second foundational tool, and truly the cornerstone of the information-theoretic privacy guarantees in this paper, is Theorem 1, Shannon's one-time pad, referenced in equation 12.
The famous one-time pad.
Indeed. This is a profound result in cryptography, really the gold standard for perfect secrecy. It states that for any secret random variable x in our finite field FQ, if you add a truly random, uniformly distributed variable z from the same field to your secret x, using that modular arithmetic of FQ, the resulting sum, x plus z, reveals absolutely nothing about x.
Nothing at all.
Nothing. Mathematically, this is expressed as ix plus z equals 0. The mutual information between the secret x and the padded result, x plus z, is 0. There's no statistical correlation, no pattern, no way to infer x from x plus z.
So if I have my secret number x, like my income, and I add a completely random number z to it using this finite field math, the sum x plus z looks just as random as z did by itself. And you can't work backwards to figure out my original x. Is that the right intuition?
That's precisely the intuition. The sum is utterly indistinguishable from pure noise from the perspective of someone who doesn't know z. This prevents any inference about the original secret x. This is the elegant mechanism that ensures the user's sensitive data, like their personal feature vector x, remains perfectly private from the servers. Even if a server observes the padded query QSN, which includes x plus and z, it learns absolutely nothing about the user's original input x because the random pad z completely obscures it.
Wow.
These two tools, the invertible van der Waals matrix for robust decoding and Shannon's one-time pad for perfect privacy, are ingeniously combined throughout all the proposed schemes. It's really a testament to the power of applying fundamental mathematical principles to complex real-world problems like this one.
Okay, so now that we have the language and the core tools, van der Waals matrices, one-time pads, finite fields, let's formalize the challenge. What exactly is the user trying to do, and what are the strict rules of engagement in this private counterfactual retrieval or PCR setting?
Let's lay out the precise setup. In this scenario, you have the institution, could be a bank, a hospital, whatever, and they possess a pre-trained black box machine learning model.
Black box, again, meaning we don't know its internals.
Right. This model takes a d-dimensional feature vector as input. Think of D as the number of characteristics describing you, your income, age, credit score, health markers, and so on. The model processes this d-dimensional vector and classifies it as either accepted or rejected.
Okay.
Now, the user, who has unfortunately been rejected by this model, wants to privately retrieve a valid counterfactual sample that corresponds to their own data. Crucially, the user doesn't have direct access to the model itself or its inner workings. Instead, they rely on a database D.
Held by the institution.
Yes, held by the institution. This database D contains M previously accepted samples, let's call them Y1 through YM, and these Y samples are stored across N non-colluding servers.
Non-colluding is important, you said.
Vital assumption here. It means these servers don't conspire, communicate, or share information with each other to try and deduce your private data. Each feature of these Y samples is assumed, for the math, to be an integer falling within a specific range, say from 0 to R. Now, the primary goal of the user, as formally defined in equation 1, is to find this thing called theta.
The theta star.
Theta equals argument on AMD.
Theta.
Okay, let's break that down.
Please do.
The user wants to identify the index, just a number, like 5 or 127, of the specific accepted data sample Y within the institution's database D that is mathematically closest to their own feature of vector X.
Closest base.
Based on some distance metric D. For most of the paper's discussion, this distance metric is the standard Euclidean distance, or technically the squared Euclidean distance, the ARO2 norm. So dxy equals y by 2. It's the sum of the squared differences between corresponding elements of the two vectors.
So find the index of the accepted sample that's the shortest straight line distance away from my rejected sample in this d-dimensional space.
Exactly. At a high level, they're looking for the nearest accepted neighbor in the database. That's the goal. The process flow, which is nicely visualized in figure 1 of the paper, outlines the interaction protocol. How does this actually happen?
Okay.
The user initiates the process by sending a specific type of query, let's call it QSN, to each individual server N. Upon receiving these queries, each server computes its respective answer, AXN. This computation uses its locally stored data, its portion or copy of the YE samples, the specific query it receives QXN, and potentially some pre-shared common randomness with the other servers. Equation 2 formalizes this. The answer AXN is entirely determined by these inputs.
So the server calculates something based on my query and its data.
Right. Once the user receives all the answers, AGS1, AGS2, AGSN from all the N servers, they use this collective information, plus their own original input X and the random numbers they generated, to decrypt and determine the index of their closest counterfactual.
And there are incredibly rigorous definitions for success and privacy here, right? It's not just a hopeful, we think it might work. These are meant to be ironclad guarantees based on mathematical proof.
Precisely. The paper lays out rigorous formal definitions for 3 core constraints that any proposed scheme must satisfy to be considered successful in this private counterfactual retrieval setting. These are not suggestions, they are hard requirements. First, we have PCR decodability, formally given by equation 3, H QXN AGSNX equals 0.
Okay, H is entropy. So the entropy of theta star, given everything else, is 0.
Exactly. The Shannon entropy of ACAR desired counterfactual index, given all the queries sent to all servers, QXN, all the answers received from all servers, AXN, and the user's own input X must be exactly 0, meaning there's no uncertainty left. The user must be able to figure out Theo uniquely and perfectly from the information they've gathered. No ambiguity, no uncertainty, no possibility error in their decoding process. They have to get the right answer. That's decodability. Second, and absolutely paramount for this whole endeavor, is PCR user privacy, formally defined in equation 4. IX E QXND equals 0 for all servers N.
I for mutual information. So the mutual information between my stuff, X, and what any server N sees, QXN, is 0.
Perfect. This is a very strong information-theoretic guarantee. It states that the mutual information between the user's input X, their highly personal data, and the desired counterfactual index O on one hand, and the specific query QXN received by any single server N on the other hand, is 0. Conditioning on D means this holds regardless of the database content.
So what does that mean in practice?
It means that each individual server, working in isolation, remember they're non-colluding, learns nothing at all about the user's personal data X or which specific counterfactual the user is looking for. This is where that one-time pad mechanism we discussed earlier truly comes into play, perfectly obscuring the user's sensitive information from any individual server's view. Third, they define PCR database linkage in equation 5. I, Y1, doc, YM, QXN, AXNX.
Okay, mutual information again. This time between the whole database YM and the queries and answers the user sees, given the user's own X.
Precisely. This metric rigorously quantifies how much information about the institution's proprietary database, D specifically, the collection of all M-accepted samples Y1 through YM is leaked to the user during the entire process, queries and answers, given the user's own input X.
So how much the user learns about the bank's other customers, essentially?
In a sense, yes. While the user inherently needs some information to find their closest counterfactual, the overarching goal of the proposed schemes is to minimize this leakage about the entire database to the user. It's a delicate and crucial balancing act. Provide a truly actionable explanation to the user without inadvertently giving away too much of the institution's valuable and potentially sensitive proprietary data. You want low database leakage.
Now, what if you can't, or simply don't want to, change everything about yourself? For instance, you can't change your citizenship or your educational background instantly, even if a model suggests it's the closest counterfactual. How do these schemes handle that practical, real-world constraint? Because that feels like a huge piece of making these explanations truly useful.
You're absolutely right. This is a very important and practical extension, leading to what they call the immutable private counterfactual retrieval, or IPCR setting.
IPCR for immutable.
Right. This addresses the real-world scenario where a user might define a private subset I of their features that simply must not change in the counterfactual explanation. These are what we call immutable features. The remaining features, often denoted M, careful, not the database size M from earlier, this is a set of mutable indices, are mutable. They can be altered to reach an accepted state. The truly clever and complex part here is that the institution, which holds the database, doesn't know which features are immutable for the user. That immutable set I is itself a piece of private information that the user wants to keep confidential.
So the bank doesn't know I'm unwilling to change my job history, for example.
Exactly. That adds a significant layer of complexity to the privacy problem. The modified goal for IPCR, shown in equation 7 and visually illustrated in figure 2 of the paper, becomes finding AX, telling me more, but with a crucial additional constraint on this set.
Theta again, but now with a subscript I.
Right. Here is defined as the set of indices. It's a Lickness exon. Let's unpack that. Yi, I means the immutable features of sample Yi. A, it means your immutable features. The condition Yi, ess.XI, means we only consider database samples Yi, where the immutable features perfectly match yours.
So AA's is the subset of the database that matches my unchangeable stuff.
Exactly. The search for the closest counterfactual is strictly restricted only to samples in the database that perfectly match the user's immutable features. So if your citizenship is immutable, the system will only consider accepted samples that share your citizenship when looking for counterfactual AA by minimizing the distance ASA within that subset. The modified constraints for IPCR, equations 8, 9, and 10, are similar to the general PCR setting, but they now explicitly factor in this private immutable set I. Decodability, EQA8HQX and AXXSAH0, ensures the user can find AI. User privacy, EQA XIAAQX and D, is even stronger here. It ensures servers learn nothing about your input X, the target index A, or your private immutable set I. All that remains hidden from each server.
Wow, okay.
And database leakage, EKey10 IYM QXN AXN quantifies what's leaked about the database D given both your input X and your immutable set I. The overarching goal remains consistent. Minimize this database leakage while preserving perfect user privacy for all aspects, including the immutability constraint itself. Okay, so let's get into the actual solutions proposed in the paper. All of the basic private counterfactual retrieval schemes we're about to discuss, whether it's the baseline, the diff PCR, or the mask PCR, they share some fundamental principles.
All right.
They all rely on having N-to-2 replicated servers. What this means is that the institution's entire database D of accepted samples is duplicated, copied exactly, onto two independent non-including servers. This redundancy is essential for the privacy guarantees to work.
So you need two copies of the data kept separate.
Precisely. And for simplicity in these initial schemes, they primarily use the squared 82 norm for measuring distance. So just for shorthand, we'll often write D to mean E by 2, the squared Euclidean distance between database sample E and the user's input X.
So let's start with the simplest version, the baseline PCR. How exactly does it work to achieve this, seemingly miraculous feat of perfect user privacy while retrieving a counterfactual? What are its strengths and its costs?
Right. The baseline PCR scheme. This is outlined in theorem 2 of the paper, and it really serves as the foundational building block. It mathematically guarantees perfect user privacy.
That zero mutual information we talked about.
Exactly. No single server, acting alone, can deduce anything about your original input X or the specific counterfactual peg you're looking for. The communication cost for this scheme is 2D plus M symbols. D is the dimension of your feature vector. M is the number of samples in the database, so it scales linearly with both.
Okay.
A critical requirement for this scheme is that it operates over a finite field FQ, and the size of Q, the field size, must be greater than R2D. R is the maximum value any feature can take. D is the number of features.
Why does Q need to be so large? R2D sounds potentially huge.
It can be. This Q size is incredibly important because it ensures that when we do arithmetic in FQ, the results don't wrap around the clock face, so to speak, in a way that makes different true distances look the same.
Ah, collision.
Exactly. We need enough room in our number system, FQ, to uniquely represent all possible squared distance values, which can range up to about R2T. If Q is too small, different true values could map to the same value modulo Q, leading to confusion and incorrect decoding. So Q R2D is necessary. Okay, let's walk through the process conceptually. The user, wanting to find their closest counterfactual T, first generates a uniform random vector, Z. The Z is a D-dimensional vector where each element is chosen uniformly at random from FQ.
The one-time pad.
Exactly, the one-time pad. This is the key to perfect secrecy. The user then sends a specific query, QXN, to each of the two servers, server N1 and server N2. This query is constructed as QXN equals X plus N and Z. This is shown in equation 14.
X plus alpha and Z. What's alpha?
N are distinct, known, non-zero elements from our finite field FQ. For N2 servers, we just need N1 and NE2 to be different, for example, N1 and NE2 too. Because Z is a truly random, uniformly distributed vector, the sum X plus N and Z is also a uniform random vector from the perspective of any single server.
Because adding a uniform random vector makes the whole thing uniformly random.
Precisely. Therefore, due to Shannon's one-time pad theorem, each server, upon receiving QXN, learns absolutely no information about your original input X. Perfect user privacy is maintained right there. Now, upon receiving QXN, each server computes its answer, AXNI, for each sample Y in its local copy of the database. This is where the algebra gets very clever. The server calculates the squared Euclidean distance between Y and the query it received, YQXN2, and then it adds an additional one-time padding term, NNZ. Here, Z are additional shared random variables, one for each YO, also chosen uniformly from FQ. These are shared between the two servers, but unknown to the user initially.
So another layer of randomness.
Yes. The server's answer, AQXN, is therefore YQXN2 plus NZ. This is shown in equations 15 and 16. Okay, now, without getting bogged down in every single step of the algebraic expansion, which is rigorously detailed in the paper for those who want to trace it line by line, the real ingenuity lies in what happens when YQXN2 is expanded. Remember, QXN equals X plus NZ. When you substitute that in and expand the squared Euclidean norm Y, X plus NZ2, it mathematically transforms into a polynomial.
Okay.
Specifically, it becomes Y by 2 do X ATZ plus N2Z2.
Ah, I see the dix term U by 2.
Exactly. That's our target, DDX.
Yeah.
So the server's full answer, IX and D, becomes dix plus -2XTZ plus ZA plus N2Z2. The key insight for us, or rather for the user, is that this expression is a second-degree polynomial in ein. The user knows ein because they chose ein wasn't die. They also know Z2 because they generated the random vector Z. So that last term, N2Z2, is completely known to the user.
So they can just subtract it off.
Precisely. The user receives X1I and X2I from the servers and subtracts the known N2Z2 term from each. Let's call the results X1I and X2I, as shown in equation 17. Now, what the user is left with are these two values, X1I and X2I. And here's the magic of the Vandermonde matrix. These two terms form a simple system of two linear equations for two unknowns. The unknowns are, first, the true square distance dx that we want, and second, this complex interference term -2i xtz plus zi that we don't really care about.
Two equations, two unknowns.
Exactly. And this system is precisely what a 2x2 Vandermonde matrix, V2, which is like 1 or 1 news, is designed to solve. As shown in equation 18, the user takes the vector of received terms, x1i, x2it, and multiplies it by v21, the inverse of the Vandermonde matrix.
And out pops.
Out pops the vector dag, -2xz plus zit. The user perfectly and unambiguously recovers dx for all I from 1 to m. Once they have all the true square distances dix, they simply pick the minimum value to identify phi, the index of their closest counterfactual.
That is incredibly elegant.
It really is. It's a brilliant two-pronged approach. The one-time pad blinds the servers, and the Vandermonde matrix acts as the user's secret decoder ring to get the distances back.
Okay, that makes sense conceptually. So what are the costs involved in implementing such a scheme? You mentioned communication.
Right. In terms of communication cost, this baseline PCR scheme requires the user to send two d-dimensional vectors, one query QXN, to each of the two servers. Since each vector has D symbols from FQ, this translates to an upload cost of 2 D symbols total.
Okay, upload is 2pan.
Then each server responds with M symbols from FQ. Each symbol AXNI represents the calculated intermediate value for each of the M database samples. So the user downloads M symbols from server 1 and M symbols from server 2, leading to a download cost of 2M.
So total is 2D plus 2M or 2D plus M?
Exactly. The total communication overhead is 2D plus M symbols from the finite field FQ. Now, for computation complexity, how much work does everyone have to do? At the user side, generating the queries, QXN involves vector additions and scalar multiplications, which takes about OD operations. Then, decoding involves receiving 2M symbols, doing the matrix multiplication with V2 filter for each of the M samples, which is constant time per sample since V2 is fixed 2 by 2, and finally finding the minimum among M values. That whole decoding part takes OM operations. So the user's total computation is efficient, roughly OD plus M.
Seems reasonable for the user. What about the servers?
On each server, the main work is computing the M answers AXNI. For each I, the server needs to calculate YQXN2. This involves vector subtraction, squaring elements, and summing them up operations across D dimensions. So computing one AXNI takes about OD time. Since there are M such samples, the total server computation is OMD. This means the server computation scales linearly with both the database size M and the future dimension D. And remark 1 of the paper highlights an important flexibility of this fundamental scheme. While the core model uses the squared A2 norm, the general approach can actually be extended to other AIC norms as long as K is an even number.
Like L4 or L6 norms?
Exactly. The answer generation logic would be modified to compute the k power norm, and crucially, you would need n and k servers. Why? Because expanding the kxk power norm results in a polynomial of degree k in ion, so you need k equations from k servers to form an invertible ksk Vandermonde matrix, Vk, to solve for the k unknown terms, one of which would be the desired distance.
More servers for higher norms. Makes sense.
Interestingly, they also note it works for the simple dot product metric, dxy equals ytx. In that case, you only need n in 2 servers again, and the user would aim to maximize ytx instead of minimizing distance. The core principle of using n and z for privacy and the Vandermonde matrix for decoding remains consistent across these variations.
So the baseline works, achieves perfect user privacy. That's a huge step. But you mentioned earlier that the institution's database leakage is still something to optimize. It seems like knowing all the exact die values, the exact distance from me to every accepted sample, could still implicitly reveal something about their specific D samples, right? Can we do even better on the institution's side, leak less about their data?
You're hitting on a crucial point that this paper directly addresses. While user privacy is perfectly secured in baseline PCR, the amount of information leaked about the institution's database is indeed a target for optimization. This is where the second scheme, diff-PCR, or difference distances PCR, comes in.
Diff-PCR, okay.
Theorem 3 states that this scheme is specifically designed to offer lower database leakage compared to the baseline PCR. So better privacy for the institution. The communication cost is slightly reduced to 2D plus M1 symbols. However, there's a trade-off. It requires a larger finite field FQ than the baseline scheme. Specifically, Q must be greater than 2R2.
Twice as large as before. Why the bigger field?
That larger Q is vital. Remember, our finite field FQ acts like a number line that wraps around?
Yeah.
For diff-PCR, we're not just dealing with positive squared distances, day x, which are always non-negative. We're dealing with differences between them, like dx, djx, which can be positive or negative. Think about our clock face analogy again. If your clock only goes up to 12, like a small q, and you want to represent both plus 5 hours and negative 5 hours distinctly, 12 isn't enough because 7 o'clock could represent plus 7 or negative 5. You need a bigger clock face. The paper works out equation 19 that the maximum absolute difference, dx djx, can be up to RZ2t. So to represent all possible differences in the range MIG to R2t plus RTT without ambiguity due to wraparound equation 20, you need your field size q to be larger than the total span, which is 2R2t. This ensures positive and negative differences don't alias onto the same value in FQ. The main idea of diff-PCR is ingenious. Improve database privacy by having the servers reveal only the differences between consecutive squared norms, dx plus 1x, rather than each individual dx value.
Just the gaps between them.
Exactly. The user still sends the same privacy-preserving query qxn is x plus n a and z as in the baseline scheme, equation 14. The two servers, N1 and N2, also share M1 independent random variables, zi, for additional padding, one for each difference they will compute. Now, each server N computes its answer A gets Ni for each I from 1 to M1. Note only M1 differences. This is shown in equation 21. Instead of the individual distance, it calculates the difference. X and I, U qxn2 y plus 1 qxn2 plus nz.
Subtracting the distance to the next sample.
Right. Now, when the term y qxn2 y plus 1 qxn2 is mathematically expanded, similar to our baseline discussion, something neat happens. Remember, the expansion gave us dx plus n plus n2z2. When you subtract the expansion for u plus 1, the un2z2 terms, which are common to both y and u plus 1, cleverly cancel each other out.
Oh, nice. So no quadratic term this time.
Exactly. This leaves us with an expression that simplifies to dx d plus 1x plus ne plus 1 utz. So after adding the padding term nz, the full server answer ni, detailed in equations 22 and 23, becomes px d plus 1x plus ne plus 1 nz plus zi.
Looks simpler than before.
It is, structurally. The second part of that sum, 2e plus 1e z plus z, is defined as ii. This is an interference term. Crucially, the zi within I acts as a one-time pad, ensuring that I reveals no discernible information about the actual difference between database samples y plus 1e to the server or user beyond its role in the calculation. Now, just like in the baseline scheme, the user collects AX1I and AX2I from the two servers. These two values again form a system of two linear equations. The unknowns are dxd plus 1x, the difference we want, and the masked interference term ii. This system can again be perfectly solved by multiplying with v21, equation 24. This allows the user to exactly recover dcapsi d plus 1x, the difference of the squared norms, and the masked interference term I, which they discard.
Okay, so the user now only has the differences between consecutive distances like D1, D2, D2, D3, and D3, D4, and so on, not the absolute distances themselves. How do they determine the index of the overall closest counterfactual from just these differences? That sounds like quite a puzzle to solve.
It is, and it's elegantly solved with algorithm 1 presented in the paper. The user reconstructs Y by essentially chaining these differences together. The core logic, detailed in step 5 of the algorithm, involves iteratively comparing a running minimum distance seen so far, represented by y, with the next sample, I plus 1, using the recovered difference dxdn plus 1x, or similar derived differences.
How does the comparison work without the actual values?
It clearly uses the properties of the large finite field FQ. If a recovered difference, say d current next, when computed in FQ falls into a specific range, namely R2D plus 1Q1, this mathematically signifies that the true difference was large and negative.
Meaning d next was much larger than d current.
Exactly. It implies that d current is truly smaller than d next. Because Q is large enough, 2R2AD, the values don't wrap around ambiguously. A result in that upper range R2D plus 1D-1 uniquely corresponds to a true negative difference, like d current next. By working purely with these differences and leveraging the sufficiently large field size Q, the user can implicitly learn the ordering of distances without ever knowing the actual distances themselves. If d current next falls into that specific range, the user knows d current is smaller, otherwise d next is smaller or equal. They iterate through, keeping track of the index with the smallest distance found so far, all based only on these differences.
Wow, that's subtle, using the field structure itself to compare.
It's very clever. It effectively tells the user which sample is closest without revealing the actual distance values, thereby enhancing database privacy compared to baseline. In terms of communication costs for diff-PCR, the upload from the user to the servers is TICI symbols, sending QXN, which is the same as the baseline scheme. The download from the servers to the user is 2 M1 symbols, since there are only M1 differences computed and sent back 1 X and I per difference from each server. This is a slight reduction from 2M in the baseline. And for computation complexity. At the user side, query generation is still O-day. Decoding the M1 differences using V21 and then running algorithm 1 to find by iterating through the differences is efficient, roughly OM. So the user's total computation remains OD plus M. On each server, computing the M1 difference-based answers involves operations similar to the baseline, vector math for distances, resulting again in OMD operations.
Okay, so diff-PCR leaks less database info by using differences. What's the third approach mentioned for boosting database privacy? Masking sounds quite intriguing. How does mass PCR achieve that, and what are its unique trade-offs?
Right, mass PCR. As described in Theorem 4, this scheme employs a fundamentally different strategy to achieve lower database leakage compared to baseline PCR. Its communication cost is 2D plus M, which is identical to the baseline scheme. And importantly, it operates with the original field size requirement, QR2D. Unlike diff-PCR, it does not require that larger field size Q2R2D.
So same communication as baseline, smaller field than diff-PCR. What's the catch?
The mechanism is different. As outlined in equation 27, the core idea of mask PCR is that the servers add a secret, uniformly random variable, let's call it the mask, directly to the squared Euclidean distance calculation before padding. So server's answer becomes AKSNI, AQXN2 plus band VI.
Adding random noise to the distance itself.
Exactly.
Yeah.
The same mask is uniformly chosen from a specific range, 0, min, 1. Here, dmin is a predetermined minimum difference between squared distances calculated across all pairs of distinct samples in the database relative to a specific set of points.
Minimum difference. Okay, how is that used?
Theoretically, this scheme performs optimally if the user sample X is guaranteed to be in a mathematically defined set DC sort of a closure of rejected samples. This condition ensures that the masking preserves the relative ordering of distances. Lemma 1, with its proof in Appendix 8.2, formally proves this property. However, in practical implementations, as Remark 3 notes, this theoretical restriction on X is often relaxed. Instead, DM is determined empirically from the dataset itself, representing a kind of minimum separation between distances. A larger Q field size gives more room to choose a larger D-min range, potentially offering more robust masking. Now, upon receiving these masked answers AXNI, the user processes them in a way very similar to the baseline scheme. They use the Vandermonde matrix in version V21, just like in EQ 17 and 18, to decode the valued IX plus I for each I, equation 28.
So they get the distance plus the random mask. How does that help find the minimum? Doesn't the mask scramble the order?
That's the crucial insight. It doesn't scramble the order if Daman is chosen correctly. Even with this mask added, the user can still reliably determine the closest counterfactual element. Why? Because the mask problem is specifically designed to be smaller than the guaranteed minimum difference between any two truly distinct distances relevant to the problem. The property proved in Lemma 1 essentially states that the difference between any two relevant true distances, say DOM-Is, djx, will always be greater than or equal to DOM-in. So since the mask goes from 0 d-min1, its maximum value is DOM-in1. This means that adding the mask is not enough to reverse the order between two distances that are already separated by at least DOM-in. If DIAMS is truly smaller than DDOM by at least DIAMN, then even the worst-case DIAM plus DMIN1 will still be strictly less than DJS plus 0. The relative ordering is perfectly preserved.
Okay, that makes sense. The noise is small enough not to change who's winning the race. Can you walk us through a quick illustrative example of this masking? Because that concept of adding noise without scrambling the order is quite counterintuitive at first glance.
Certainly. Let's use a simplified example, similar to the one provided in the paper, to make this concrete. Imagine you, the user, have a rejected input, x was 1, 2t. The institution has two accepted samples in its database. y1 equals 20, 0t, and y2 equals 0, 20t. Let's assume our finite field size Q is large enough to handle the calculations without wrapping around. And let's suppose that after analyzing the data, the institution determines a suitable d-min value of 40. This means the random mask will be chosen uniformly from the set 0, 1, 39.
Okay, d-min is 40, mask is between 0 and 39.
Right. First, let's calculate the actual squared Euclidean distances from your x to the two accepted samples.
C1x equals 20, 0t1, 2t2 equals 19, is 2t2 plus 192 plus 92, 2 minus 361 plus 32 times plus 4.
82 x, 281, t2 minus 192 plus 192 plus 182 plus 1 plus 324 is 325.
Okay, so d2 is smaller, 325 versus 365.
Yeah.
Exactly. Based on the true distances, y2 is clearly closer to x since 325 is less than 365. And notice the difference. d1x, d2x is 365, 325 equals 40. This difference happens to be exactly our chosen d-min. Now, in the mass PCR scheme, instead of receiving the true distances 365 and 325, you, the user, receive the masked values d1x plus 1 and d2x plus 2. That is, you receive 365 plus 1 and 325 plus 2, where 1 and 2 are random values chosen independently from 0, 8, 39.
Right.
The crucial point is that no matter what specific random values 1 and 2 take, as long as they are within their allowed range 0, 39, the term 325 plus 2 will always be less than 365 plus 1.
Always. Let's check the extremes.
Let's do that. The minimum possible value for the first term is 365 plus 1 equals 365 plus 0 plus 365. The maximum possible value for the second term is 325 plus 2 equals 325 plus 39 plus 364.
364 is still less than 365. It's exactly. Since the maximum possible value of the smaller distance plus its mask, 364, is still strictly less than the minimum possible value of the larger distance plus its mask, 365, the relative ordering that y2 is closer to x is perfectly preserved. So even with the random masks applied, you, the user, can correctly deduce that y2 is the closest counterfactual without ever knowing the exact original distances 325 and 365. This protects the institution's specific database information better than baseline. This example also implicitly highlights the effect of finite field size again. A larger Q gives more room for potentially choosing a larger d-min and thus using a larger random mask. While a larger d-min means the mask range is wider, making it harder for the user to maybe estimate the exact unmasked distances, it doesn't disrupt the critical ordering needed for counterfactual retrieval as long as the d-min property holds. The communication cost for mass PCR is the same as baseline PCR, taking for upload and 2m for download, totaling 2d plus m. Computation complexity is also similar, OD plus M for the user and OMD for the server. Remark 2 clarifies that the d-min calculation is a pre-processing step, done only once by the institution before the system is deployed, and thus doesn't add to the per-query computational burden of the active scheme.
Okay, so we have these three schemes now. Baseline, diff PCR, and mask PCR. They all seem to achieve perfect user privacy, but diff and mask claim to offer better database privacy for the institution than baseline. Can we actually quantify that, or is it just an intuitive feeling that differences or mask values somehow leak less information?
It's not just a feeling at all. It's rigorously quantified using that mutual information metric for database leakage we defined earlier, IYM, AKXNX. Remember, this measures how much the server's answers AKXN reveal about the database YM to the user, given the user's own X. Let's break down why diff PCR and mask PCR are indeed mathematically proven to be better in this regard. First, there's a general simplification we can make, as derived in equations 32-34 of the paper. The overall database leakage could formally be written, including the queries QXN as IYM, QXN, EGXNX. However, the paper argues that the database YM can be considered independent of the queries QXN given the user's input X. This is because the randomness injected into QXN, the Z vectors, is primarily for user privacy and relies on shared randomness among servers, which is on a different information subspace relative to the database itself.
Okay, so the queries themselves don't leak database info to the user.
Essentially, yes. So for analyzing database leakage to the user, we can simplify the metric and primarily focus on the information revealed by the server's answers, I, Y, M, X, and X. Now let's look at baseline PCR leakage, equation 35. After the user decodes the answers using V21, they learn all the specific squared distances, D1x, D2x, DMX.
The exact distance to every single sample.
Right. This comprehensive knowledge implicitly leaks a significant amount of information about the underlying database YM, because each diance is directly computed from Y and X. The leakage is quantified as ID1x, DMX, YMX. Essentially, the user obtained the exact distance profile of their query X relative to the institution's entire accepted database D. Now compare that to diff-PCR leakage, equation 36. Here, the user only learns the differences between consecutive distances, let's call them RID plus 1x, IX, by a fundamental principle in information theory known as the data processing inequality.
Data processing inequality sounds important.
It is. It basically states that if you process data, like taking differences instead of using the original values, you can only reduce or keep the same amount of information. You can never increase it.
Makes sense. Processing can't create information out of thin air.
Exactly. So the information contained in these differences, IR1, IRM1, YMX, is inherently less than or equal to the information in learning all the individual distances, ID1X, DMX, YMX. Intuitively, knowing that AB5 tells you less about the individual values of A and B than knowing A equals 10 and B equals 5. So diff-PCR formally achieves a reduction in database leakage compared to the baseline. And for mask PCR leakage, equations 3741, the derivation is a bit more involved, using properties of entropy and conditional mutual information, but it rigorously proves a similar result. IYMDMP plus IAMMX is also less than or equal to the baseline leakage.
So the mask also helps hide database info.
Yes. The key here is the presence of that independent random mask. This mask adds uncertainty to the observed values diance plus. Even though the user can still determine the correct ordering of distances, thanks to the die property, the mask effectively blurs the exact true values of die, thereby reducing the information revealed about the underlying YM to the user. The full derivation relies on elegant properties like how adding independent random variables increases the entropy uncertainty of the sum, making it harder to infer the original unmasked values. Now, Remark 4 makes a critical point. While both diff-PCR and mask PCR are proven to have lower leakage than baseline PCR, it's analytically very tough to compare diff-PCR and mask PCR directly against each other just using the math.
Why is that?
Because diamond, which significantly affects mask PCR's leakage, larger diamond allows for more masking, potentially reducing leakage further, depends heavily on the specific distribution of the database D. It's not a fixed constant. That's precisely why numerical experiments are absolutely essential to empirically compare their real-world performance on actual datasets, which we'll get to in section 6.
Okay, this is where we get even more practical, I think. In real-world scenarios, people often can't change fundamental attributes about themselves, right? Like your age, your place of birth, maybe your highest degree achieved. How do these privacy-preserving schemes handle that immutability constraint? Because for an explanation to be truly actionable, it really needs to respect these unchangeable aspects of a person.
This immutability constraint is indeed crucial for real-world actionability and, frankly, for ethical considerations in AI explanations. The user gets to define a subset I of their features that simply cannot be altered in the counterfactual suggestion. These are the immutable features.
And the key is the user defines this privately.
Yes, and just as importantly, this set I must itself remain private from the institution. The institution should know which specific attributes you consider immutable. That's part of your personal privacy. This requirement adds a significant layer of complexity to the overall privacy problem. And as highlighted in Remark 6, it necessitates more servers for the scheme to function securely. For these IPCR schemes, the number of replicated servers generally increases from N2, required for standard PCR, and N3.
Why the third server?
Essentially, you need an additional dimension of freedom in the equations to resolve the extra piece of private information, the set I itself, without compromising the privacy of X or the decodability. That third server provides the necessary third equation in the system. So, all the IPCR schemes we'll look at operate on this core principle. They aim to minimize database leakage. as defined back in equation 10, while maintaining perfect user privacy, equation 9, now protecting X and I, and ensuring accurate decodability, equation 8, finding the right counterfactual 8I, but now with this added layer of the private immutability constraint.
It sounds like handling this immutability constraint might require a multi-stage operation for the system to figure out the right counterfactual. Tell us about the two-phase IPCR scheme. How does phase 1 work?
Right, the two-phase IPCR scheme, as detailed in Theorem 5, is indeed a multi-stage approach. As we just discussed, it requires N3 servers, and the paper states its total communication cost is 9D plus M symbols, operating over a finite field FQ with the standard size requirement QR2D. Phase 1. Finding eligible samples. The primary goal of this initial phase is for the user to privately identify which specific samples YIM in the institution's database have immutable features that perfectly match their own immutable feature states. This set of matching samples, which represents the subset of the database that could even possibly be a valid counterfactual, is denoted AMEIII.
So phase 1 just filters the database for matches on my unchangeable stuff.
It's exactly. To achieve this privately, the user first constructs a binary vector H1, as defined in equation 42. This H1 vector acts like a mask. It has a 1 for features that are part of their private immutable set I and O for mutable features. This H1 essentially helps isolate the immutable features in subsequent calculations. Then the user sends a query tuple QX into each of the N3 servers, equations 43, 44. This tuple consists of 2 vectors, QX11 equal H1 plus INZ1, QX2 equals XTED-H1 plus INZ2.
Okay, H1 is the immutable mask, X is my data, is element-wise product, and Z1, Z2 are more one-time pads.
Exactly. Z1 and Z2 are independent, uniform random vectors from FDQ chosen by the user. These Z vectors, once again, serve as the one-time pads, ensuring perfect user privacy for both the structure of H1, which reveals I, and the values of XEOH1, which reveals I, from any single server. Upon receiving QXEN, each server N computes its answer XEII for each sample YI in its database. This is a mathematically complex calculation detailed in equations 45-47. It involves another layer of masking for database privacy using a random non-zero element I chosen by the servers from FQ. Additionally, there are further uniform random variables Z1II and Z2I for one-time padding. The core calculation within the server's response boils down to evaluating YOU Yuanqian. Now, when that term QXSENDU is expanded by substituting the definitions of the queries, it transforms into a polynomial of degree 2 NI. The full server answer XNI then becomes EI multiplied by this polynomial plus the INZ's padding terms, resulting in an overall expression that is also a polynomial of degree 2 NA.
Degree 2 again.
Yes. So the user, having sent queries to N3 servers, collects 3 such answers for each EA. These 3 answers form a system of 3 linear equations, equation 48. And just like we saw the need for N-K servers for EC norms, here, with a degree 2 polynomial, we need N3 servers and the corresponding 3x3 Vandermonde matrix V3 to solve it. By multiplying the system with V31, the user successfully recovers the term RH1 year by 2, along with 2 other interference terms, I11I, I12I, that, due to the one-time padding, leak no useful information about the database. The key insight comes from analyzing that recovered term, AREA by 2. If AIIXE, meaning the immutable features of E perfectly match the user's X, then the vector difference, EIX, will have zeros in all the immutable positions. Since H1 only has 1s in the immutable positions, the element-wise product H1 will be a 0 vector.
Ah, because 1 times 0 is 0.
Exactly. Consequently, H1 ERO will be 0, and thus the recovered term IH1 year by 2 will evaluate to 0. If, however, IEI, meaning at least one immutable feature doesn't match, then H1 ERO EX will be non-zero. It will have non-zero values where H1 is 1 and E differs from X. Since I is chosen as a random non-zero element from FQ, the result IH1ER will also be non-zero.
So the user gets 0 if the immutables match and non-zero if they don't.
Precisely. And crucially, because I is random and non-zero, the user only learns if there's a match, 0 versus non-zero. They don't learn which specific immutable features matched or mismatched, or the extent of any mismatch, just a binary yes-no for eligibility. If after this phase, the set of eligible samples, those that resulted in 0, is empty or has only 1 element, the process stops right there. No counterfactual or only one trivial 1 exists.
Okay, so phase 1 acts like a private filter, telling the user which samples are in the eligible set. Now, how does phase 2 work to find the closest match within that eligible set still without revealing itself to the servers?
Exactly. Phase 2, finding EI, closest match within. Once the user has privately determined the set of eligible samples from phase 1, they need to find the single closest sample within that set, and they need to do this while ensuring that the servers still don't learn which samples are in E, since EI itself is derived from the user's private immutable set I.
Another layer of privacy needed.
Right. To achieve this, the user prepares a new binary vector H2, as defined in equation 50. This H2 vector is essentially an indicator for the set. It has a 1 at index I if as an instance, meaning E is eligible, and 0 otherwise. The user then sends a new query tuple QXMN to the index-free servers, equations 51 to 52. This tuple comprises two vectors, QXMN1 equals H2 plus NZ3, QXMN2 equals X plus NZ4. Here, Z3 and Z4 are fresh, independent one-time pads specifically for this phase, protecting H2 and X. Each server then uses QXMN1, which is the padded version of the H2 indicator vector, to create a kind of masked database, equations 53 to 54. Conceptually, diag QXMN1 acts as a filter. If H2I0, meaning sample Y is not in NUS, the corresponding row Y in the server's calculations is effectively zeroed out or made irrelevant by the multiplication with the padded H2.
So it focuses the calculation only on the potentially eligible samples.
In essence, yes. The server's answer, XMNID equations, 55 or 57, is then computed based on this masked database, roughly as SANIAN2 XMN22, along with additional INZ's padding terms for security. When SANAT QXMN22 is expanded, substituting the definitions involving H2X is 3Z4, it ultimately results in, again, a polynomial of degree 2 XANA. The full XMNI, therefore, also takes the form of a degree 2 polynomial in ISIN plus padding terms. The user collects the three answers, XM1I, XM2I, XM3, from the N3 servers. Similar to phase 1, these three answers form a system of equations that can be perfectly solved by multiplying with V331, equation 58. This allows the user to uniquely decode the term H2I2I2 for each I. And here's the critical decoding step and its implication for privacy, as summarized in equation 59. If AA2, meaning Y, is an eligible counterfactual, so the user set H2II1, then the decoder term H2IE2 simplifies to 1 Y by 2 equals Y by 2. This is precisely the X, the true squared Euclidean distance between the eligible sample U and the user's X. So for eligible samples, the user learns their actual distance. Okay, they get the real distance for the good ones. But if IA at O, meaning E is not an eligible counterfactual, so the user said H2I equals 0, then the decoded term H2II2 simplifies to 0 Y by 2 equals 0 by 2 by 2 by 2.
The distance from the origin to X.
Exactly. The user learns by 2, which is a constant value known only to the user. It's based on their own input X, and reveals absolutely no information about the ineligible sample U or its distance from X.
Clever. So only useful info for the relevant samples.
Precisely. The user only obtains the actual AA2 distances for the relevant samples that meet the immutable feature constraint, while no further information about ineligible samples is leaked in this phase. The user then just finds the minimum among the decoded die values, ignoring the by 2 results, to get QI. Now, communication cost for this two-phase approach, let's tally it up based on the paper's description.
User uploads tekken to 3 servers equals 6 pins. Servers download M from 3 servers equals 3M. Phase 1 total, 6 pin plus 3M.
User uploads H2 size M and X size D plus pads to 3 servers. It's 3M plus D equals 3M plus 3D. Servers download M from 3 servers equals 3M. Phase 2 total, 3D plus 6M. Summing both phases, 6Ds plus 3M plus 3 plus 6M, gives a total worst-case communication cost of 9D plus 9M symbols.
Okay, 90 plus 9M scales with both dimension and database size.
And computation complexity. At the user's side, query generation in phase 1 is OM. Phase 2 query generation involves creating H2, OM, and padding, so OM plus D. Decoding is OM, so the user's total computation remains efficient overall, roughly OD plus M. On each server, computations in both phases involve iterating through M samples and performing vector operations of dimension D, resulting in OMD operations for each phase.
Now, Remark 5 mentions an alternative version of this two-phase IPCR that uses N+4 servers instead of N3. What's the trade-off there, and why might an institution consider using 4 servers?
Right, that alternative N4 scheme is a variation designed with a specific goal, to potentially reduce the total communication cost, particularly in scenarios where the feature dimension D is significantly larger than the database size M.
High dimension, relatively small database.
Exactly. It modifies how certain calculations are performed, leading to a higher degree polynomial in N, specifically degree 4, that needs to be resolved during decoding. That higher degree is why an additional 4th server is needed. You need 4 equations from 4 servers to uniquely solve for the coefficients of a degree 3 polynomial, after canceling the N of 4 term, which is what arises in that variant. The paper notes that the total communication cost for that N4 variant would be 8D plus 10M.
8D plus 10M.
Compared to 9D plus 9M for the N3 version. So if D is much larger than M, that 8D might be significantly less than 9D, making the N of 4 version more efficient in terms of total data transfer, even though it adds the infrastructure complexity of requiring an extra server. It's purely an engineering trade-off.
Okay, two phases sound effective, but maybe a bit complex to manage operationally, coordinating two rounds of interaction. Can the researchers achieve this immutability constraint and privacy all in one single pass? Just one query, one answer phase?
Yes, they can. And that leads us to the single-phase IPCR scheme, detailed in Theorem 6. This approach streamlines the entire process into one single interaction between the user and the servers. As a result, it achieves a lower communication cost of 6-pin plus 3M symbols, which is noticeably less than the 9D plus 9M of the two-phase scheme.
Lower communication, simpler interaction. Sounds good. What's the trade-off this time?
The trade-off is significant. It requires a much, much larger finite field of Q. Specifically, the field size Q must be greater than FL1R2 plus R2T.
Whoa, okay, what are F and L?
Here, F is an upper bound on the number of immutable features the user might specify, so at most D. And L is a carefully chosen large scaling factor. L must be chosen such that it's significantly larger than the maximum possible squared Euclidean distance, specifically LR210A. This much larger field size Q is absolutely necessary to ensure proper distinction between samples that match the immutable features and those that don't, all within a single complex calculation, without any ambiguity arising from the wrapping around property of the finite field arithmetic. The core idea, as shown in equation 60, is that the user defines the single vector H. This vector combines both the immutability information and a scaling factor. For each feature K, HK is set to the large value L, if feature K is in their private immutable set I. If feature K is mutable, HK is simply set to 1.
So L for immutable, 1 for mutable.
Exactly. The value L is critical here. It's chosen to be so large, LR2D, that it ensures that distances involving immutable features that do not match the user's input are scaled up significantly enough by this L factor to fall into clearly distinct numerical ranges from those distances that do match on the immutable parts. The user then sends a single query tuple QXN to each of the N3 servers, equations 61, 62. This tuple looks like QXN1 equals S1C1. QXN equals NZ2. As always, Z1 and Z2 are fresh one-time pads, ensuring perfect privacy for the user's input X and their combined immutable mask vector H. In response, each server N computes a single answer X-NI for each EI in its database, equation 63, 64. And the central calculation here is a bit more complex. Yi, QXN1, T, TIAG, Yi, QXN1, PXN2, plus the usual NZ padding terms. Note the structure involves the difference, Yi query 1 dotted with itself element-wise multiplied by query 2. Okay, without going into the granular step-by-step algebraic expansion, which is quite involved and detailed in the paper, equation 65, 66, the critical insight is that when this core term is fully expanded by substituting the definitions of QXN1 and QXN2, it transforms into a polynomial of degree 3 in Fiano. The highest degree term, the coefficient of IN3, involves only Z1 and Z2 and is thus known to the user.
Degree 3 this time, so N3 servers make sense again.
Precisely. After the user receives the answers cs.NI from the N3 servers, they cancel out the known N3 term, equation 67, leaving them with cs.NI. These three resulting values form a system of three linear equations solvable by V3 day 1, equation 68. This allows the user to perfectly recover the critical term, EAXT, EAXH, along with two interference terms that contain no useful information due to the Z and Z padding, equation 68, 69. Now here's the ingenious part of the decodability for the user, based on the structure of that recovered term, EAXNAXHH. Case 1, if ISH meaning all mutable features of E perfectly match the user's E. In this case, for any mutable feature Ka, the difference EXK is 0. So when we compute EAKH, the result for mutable features is 0L AZ. For immutable features Ki, the difference EXK is potentially non-zero and HK is 1. So the term EAXT, EAXA also simplifies to just the sum of squares of differences over the mutable features only. This is effectively DX mutable. This value will always fall within a specific relatively small range, mathematically bounded by zero DMA, DIR2.
Okay, for matches, they get a value related to the mutable distance.
Case 2. If at least one immutable feature mismatches, for each mismatched immutable feature, KIC, the difference yield SK is non-zero, and HK is the large value L. So the term AK2HK becomes non-zero to L. This large L factor kicks in and dominates the sum. The resulting value gets pushed into a completely disjoint and much higher numerical range, approximately L, LIR2 plus DIR2.
A completely separate range of numbers because of L.
Exactly. Since L was chosen to be significantly larger than R2D, which bounds the result in case 1, these two sets of ranges, the low range for matches and the high ranges for mismatches, are mathematically distinct and non-overlapping. This allows the user to clearly distinguish between valid counterfactuals, those are really resulting in a low value, and invalid ones, those are resulting in a high value. And crucially, among the valid ones, case 1, they see the actual days mutably only values, allowing them to find the minimum. So for communication cost, the user uploads toady symbols for X and H plus pads to each of the N3 servers for a total upload of 6 bands. Each server downloads M symbols AXNI to the user, totaling 3M. So the total communication cost for the single-phase scheme is 6 ping plus 3M symbols.
6 pan plus 3M, that's less than the 2-phase 9p plus 9M.
It is. And computation complexity.
Hmm.
Sufficient INFT plus M at the user side and OMD at the server side, similar to other schemes. The main cost increase is the requirement for that much larger finite field queue.
Okay, so we have 2 ways to handle immutable features privately. 2-phase IPCR and single-phase IPCR. Both seem to work, giving perfect user privacy and finding the right counterfactual. But which one is more private for the institution? Which one leaks less information about their underlying database D?
That's a great question, connecting back to the database leakage metric. If we compare the two schemes on that front, the 2-phase scheme generally offers lower database leakage compared to the single-phase scheme. Let's quantify why this is the case by looking at what information the user learns in each. First, for both schemes, there's an inherent common low-fish component that's mathematically unavoidable, as detailed in the analysis around equation 7376. The user must ultimately learn which samples Y satisfy the immutable constraint, Y, i.e. SLEX-I. This is represented by learning EM, which is essentially a binary vector indicating membership in the set I. So the information HEMX, the entropy of this eligibility vector EM, given the user's input X and their private immutable set I, is always revealed to the user in both schemes. This forms the first unavoidable term in the database leakage formula, equation 76.
Okay, knowing which samples are even possible candidates is unavoidable leakage.
Right. The crucial difference in database leakage between the two schemes lies in the additional information leaked beyond just EM. This corresponds to the second term in the leakage formula, I, LIM, AKS, NXI, EM. This quantifies what else the user learns about YM after the set EM, which defines INXNA, has already been effectively determined. The 2-phase advantage, analyzed around equations 102 to 105, stems directly from its sequential, layered nature. In phase 1, the user learns only EM, which samples match the immutables, defining INC. For samples I that are not in INC, the error mask used in phase 1 ensures no specific information about those E. It's leaked beyond the binary fact that they didn't match. Then phase 2, the user only learns the E2 distance is E by 2, specifically for samples I that are within the eligible set. For any samples I that are not in INC, the scheme explicitly ensures that the decoded term H2 II by 2 reduces to the constant by 2. Since by 2 is known to the user and independent of EA, it reveals absolutely no further information about those ineligible E samples, not even their distances to X. This effective isolation of information about ineligible samples is what makes the 2-phase scheme more private for the institution's database overall.
So it really walls off info about the non-matching samples after phase 1.
Exactly. In contrast, the single-phase disadvantage from a database leakage perspective is that the user observes the specific calculated value, EXT, for all AMs, not just for those samples I get in now. Even if a sample is not in AP, meaning its immutable features don't match, the value EXTIH still provides some residual information. Remember, that value falls into a high-range KL plus R2DI, where K is the number of mismatched immutable features for that specific YI.
Ah, so even for the rejected ones, the user gets a number related to how many immutables mismatched.
Precisely. Even though these ranges might overlap, observing which range the value falls into still provides some information about the structure of Y relative to K, specifically about K, the number of mismatches. This constitutes more leakage about Y, even when I KK when what's revealed in the 2-phase approach, where non-matching Y instances are effectively ignored after phase 1 yields a non-zero result. Therefore, the theoretical analysis concludes that the 2-phase scheme is indeed more private for the institution's database.
Okay, this next part seems really crucial for making these explanations truly useful in the real world. What if I, as the user, have a personal preference? Maybe I'd much rather change my income level than go back to school, even if mathematically changing my education level is slightly closer to an accepted counterfactual sample. Can the system incorporate my personal actionability preferences, my willingness to change certain features, while still keeping all this private from the institution?
This is a fantastic and highly practical feature that the paper directly addresses. It moves beyond just finding the mathematically closest sample to finding the one that's most actionable or desirable for the user to change towards. The schemes can indeed incorporate a user's personal preference for transforming their attributes by introducing a weighted 82 norm. This allows for much more nuanced and user-specific counterfactual explanations.
Weighted distance. Okay.
The concept is introduced with a modified distance metric shown in equation 77, dxy yxt diagw. Wait, let me reread that. Simpler. dxy yxt yx.
Okay, difference vector dotted with itself element-wise multiplied by w.
Exactly. Here, w is a private weight vector generated entirely by the user. Each component wk of this vector is an integer chosen from a predefined range, say 1 boy, L1, where L1 is some positive integer constant. A higher value for wk means the user is more reluctant to change feature k. It puts a higher penalty on changes to that feature.
So if I hate the idea of changing my job, I give the job feature a high weight wk.
Precisely. If you want to avoid changing your education level, you'd assign a high weight to that feature's component in your w vector. The significant challenge, then, is to keep this w vector, which expresses your personal preferences, completely private from the institution, just like your original feature vector x. Now we move to the PCR plus schemes. The B plus indicates they incorporate this private user actionability weight vector w initially without the immutability constraint. Theorem 7 summarizes these extensions. A key consequence of introducing the private weight vector w is that these schemes now require N3 servers, up from N2 for standard PCR.
N3 again. Why the extra server here?
Because we've introduced an extra dimension of privacy that needs to be resolved. We need to hide not just x, but also w. That requires an extra equation from a third server to disentangle everything using the Vandermonde approach. Let's look at baseline PCR plus first. The minimum required field size Q for this scheme increases. It's now QR2 L1D. That L1 factor from the weights makes the potential distance values larger. The user now sends a query tuple QXN containing two one-time padded vectors to each of the N3 servers, equation 78. QXN1 equals x plus unz1 padding x. QXN2 equals w plus unz2 padding w. Here, z1 and z2 are distinct, uniform, independent random vectors ensuring both x and w remain perfectly private from any individual server. The server's answer, AXN, equation 79 to 80, is now computed using the weighted A2 norm based on the padded queries. The core calculation is effectively UQXN1, TDIQXN2, KXN1, plus additional unz's padding terms.
Okay. Applying the padded weight vector.
When this core term is fully expanded, and this involves a sum over d features where each term is a product of a squared difference, UXK2, and the corresponding weight w, it mathematically transforms into a polynomial of degree 3 in n.
Degree 3. Why 3?
It comes from the interaction between the unz1 and the difference term and the unz2 and the weight term when everything is multiplied out. The highest degree term involves un3 multiplied by a known constant involving z1 and z2, which the user can compute. So after the user cancels out the known un3 term from xn, equation 81, they are left with xni. With answers from any three servers, the user can now form a system of three linear equations, just like we did with the V3 and IPCR phase 1, solvable by V31, equation 82. This allows the user to perfectly recover dix, the true weighted distance, along with two interference terms, I1i and I2i, equations 83-84, which contain no useful information due to the z and z's padding.
And they find the minimum weighted distance.
It's exactly. The communication cost. User uploads TODI symbols for X and W plus pads to each of three servers, totaling 6 pins. Server downloads M symbols from each of three servers, totaling 3M. So the total communication is 6 pin plus 3M. DiffPCR plus extends this logic, as summarized in Theorem 7. The user queries remain the same, equation 78, sending padded X and W. Similar to standard DiffPCR, the servers compute differences, but now of weighted distances, dix, di plus 1x. The field size Q must be even larger than baseline PCR plus N, specifically Q2 R2 L1D, to accommodate the potentially wider range of these weighted differences, equation 85.
Bigger field again for differences.
Yep. The server's answer, XNI, equations 86, 88, now includes these weighted differences plus terms that are polynomials in N-di up to degree 2, and then 3 terms cancel in the difference. The user collects answers from N3 servers and uses V31 to recover the M1 differences dix, di plus 1x. The user then uses an algorithm similar to algorithm 1, but adapted for comparing weighted distances based on their differences to find the preferred counterfactual N. Communication cost, upload 6B, download 3M1. And mask PCR plus also extends gracefully, as outlined in Theorem 7. It operates with a field size QR2L1D, similar to baseline PCR plus data. Servers compute and answer XNI, equations 8990, which, after user decoding, yields the masked weighted distance dix plus. The I mask is added to the weighted distance dix. Now, Lemma 2, proved in Appendix 8.3, is crucial here. It confirms that the range required for the masking random variable does not need to change for the weighted case.
So daemon doesn't depend on the weights W.
Essentially, yes. The reasoning is that the introduction of the private weight vector descales the dx, y values, but it does so in a way that preserves the minimum difference daemon property required for the mask to work without scrambling the order. Therefore, the masking principles still hold true. The user uses v31 to decode the mask-weighted distances dix plus I, equation 91, and then finds the minimum value among these to identify the preferred counterfactual the.
Got it.
Communication cost. Upload 6B, download 3M. Same as baseline PCR plus.
All right, now for what seems like the grand finale of complexity, combining everything. What if you have both immutability, those features you absolutely cannot change, and this user actionability, your personal preferences, for how the other immutable features should change? This sounds like the most complex, but also potentially the most realistic and useful scenario for a private counterfactual explanation.
It is indeed the most complex scenario presented, elegantly captured by the IPCR plus schemes detailed in Theorem 8. This is where both immutable features I and private mutable feature preferences W need to be handled simultaneously, all while preserving perfect user privacy for X, I, and W. The weight vector W itself needs a slight modification for this combined scenario, as defined in equation 92. For features K that are in the immutable set I, the weight WK is simply set to 1 or effectively ignored. Maybe 0 would be clearer conceptually, but the math uses 1. The point is that these features aren't meant to change anyway, so their weight in the distance calculation for change is irrelevant or minimal. For the mutable features K, those not an I, the user assigns their preference WDK, which is an integer in the range 1L1. The overall goal remains to find the sample yi that minimizes this weighted distance, but only considering yi from the set, where yi equals I.
Minimize weighted distance among immutable matches.
Now let's look at two-phase IPCR plus arrow. The field size requirement is QR2L1TRE. Crucially, phase 1 remains entirely unchanged from the standard two-phase IPCR, which we discussed in section 4.1.
Phase 1 is still just finding the immutable matches.
Exactly. Phase 1 is solely concerned with identifying samples that match immutable features, completely separate from any preferences or weights on mutable features. So the user obtains the set privately as before, using N3 servers and the H1 vector. However, phase 2 is extended significantly to incorporate the user's private weights W. Now the user sends 3 one-time padded vectors in their query QXMN to the servers. Equations 93, 94. QXMN1 equals H2 plus UNZ3, padding H2 for neons. QXMN2 equals X plus UNZ4, padding X. QXMN3 plus UNZ5, padding W. These 3 Z vectors ensure the perfect privacy of H2, the user's input X, and their private weight vector W.
3 secrets need padding now.
Right. The server's answer XMNI is now far more complex, equations 95, 96. It calculates something akin to the weighted distance using these 3 padded inputs, sanity QXMN3, sanity QXMN3, along with other padding terms. San again incorporates the masked H2. When this core term is expanded, it results in a polynomial of degree 3 and 9. The highest degree term, the nth coefficient, involves Z3, Z4, Z5 and is known to the user, so it gets canceled out.
Degree 3 again. So we need
any 4 servers, as stated in Theorem 8. Since the result after canceling the known IN3 term is still effectively a polynomial of degree 2, whose coefficients need to be recovered, related to the weighted distance and interference terms, the user requires answers from ND4 servers. This is explicitly shown in equation 97, where V4, the 4x4 van der Waals matrix, is used for decoding. This allows the user to perfectly decode the term H2I XT dian W H2IX. Wait, let me check EQ98 structure. H2I XT H2I X2IX H2I. Equation 98 shows the final decoded term. If I act at eligible H2I1, then the term reduces to LEXT XDX. This is precisely the actual weighted distance DIX. If I X at ineligible H2I0, then the term reduces to NDXT, XD, XXW. This is a constant value known only to the user, dependent only on their own X and W, revealing no information about the ineligible Y.
same logic as before, just with weighted distances for the eligible ones.
Exactly. The communication costs for two-phase IPCR Plus are higher due to N4, and the extra vector W phase 1 N3 servers is still 6P plus 3M. Phase 2 now uses N for 4 servers. User uploads H2X W plus pads 8N plus D symbols to 4 servers equals 4M plus 2D plus AT plus 4M, assuming W has dimension D. Server downloads M symbols from 4 servers equal 4M. Total communication is 6B plus 3M plus 8D plus 4M plus 4M, if we take the table literally again, which gives 14B plus 11M.
14 plus 11M, getting pretty hefty.
Now, single-phase IPCR plus 1. This scheme attempts to handle both immutability and actionability in one go, still using N3 servers. It elegantly integrates actionability by modifying the definition of the H vector, equation 99. Now, HKL for immutable features, K array, or W features, K area I, where the user is private weights in 1.L1. The scaling factor L must now be chosen even larger, LL1 R2D, to ensure it dominates the weighted mutable distances.
So H now encodes immutability L and preference WU.
Exactly. Crucially, the query structure, server computation involving IQ1, T4DQ2, and decoding using v31 remains structurally the same as the standard single-phase IPCR. It still works with N3 servers.
That seems like a big advantage keeping N3.
It is in terms of server infrastructure. Communication cost also remains the same as standard single-phase IPCR, 6 bytes plus 3M. But Remark 7 highlights the crucial trade-off. While the number of servers, N3, and the communication cost, 6 plus 3M, are not affected compared to single-phase IPCR, this elegance comes at the expense of a much, much higher required field size Q. The requirement becomes QFL1R2 plus R2 L1D. That L factor, which is already huge, L1R2D, makes Q astronomical. This is needed to ensure proper distinction and prevent wraps in the arithmetic, given the combined effect of the large L factor for immutability and the W factors for mutable features, all crammed into a single pass calculation.
So single-phase IPCR Plus is simpler interaction, fewer servers, same communication as its non-weighted counterpart, but needs potentially massive computational fields.
That's the trade-off, precisely. It's a choice between more servers and more communication rounds, two-phase IPCR Plus, versus fewer servers rounds, but potentially computationally prohibitive finite field arithmetic, single-phase IPCR Plus.
Okay, we've journeyed through a lot of complex theory, elegant math, Vandermonde matrices, one-time pads, different schemes. Theory is great, but how do these schemes actually perform when put to the test in the real world? Do they deliver on their promises of accuracy and, crucially, that database privacy?
That's the ultimate question, right? Does it actually work in practice? The researchers conducted rigorous numerical experiments to evaluate two critical aspects. First, accuracy, especially considering the need for data quantization, and second, and perhaps most importantly for the institutions, the practical measurement of database leakage. Let's first talk about 6.1 accuracy quantization trade-off in PCR. The core problem, as we touched on, for applying these schemes to real-world data is that while our mathematical framework operates perfectly on finite fields FQ, which are based on integers, real-world data often comes in continuous real values.
Decimals, fractions, not neat integers.
Exactly. So, quantization, the process of converting these real values into discrete integers within a specific range, say 0R, is a necessary pre-processing step before you can feed the data into these schemes. However, this quantization inevitably introduces some level of error as information is lost during that conversion from continuous to discrete. There's an inherent trade-off here. More quantization levels, meaning choosing a larger integer R to represent the range, results in less information lost during the conversion. You get a finer-grained representation, which generally leads to higher accuracy in retrieving the true nearest counterfactual from the original data.
Makes sense. More precision helps.
But, and this is the trade-off, a larger R directly necessitates a larger field size Q for the mathematical operations. Remember, Q often needs to be larger than R2D or similar. A larger Q means working with bigger numbers in the finite field arithmetic, which in turn leads to more computational overhead and potentially higher communication costs if the symbols themselves become larger.
So accuracy versus efficiency.
Now, specifically for mask PCR, remember that theoretical analysis assumes the user's input X is in that special set DC to guarantee perfect decodability with the mask. In practical experiments, as highlighted back in Remark 3, this theoretical restriction on X is often relaxed. Instead, Dimin, the minimum distance difference used for setting the mask range point Dmin-1, is determined empirically directly from the dataset statistics. A larger underlying field Q allows for a larger Dmin range to be safely used, potentially offering more robust masking and better privacy, but as we'll see, may be impacting accuracy if Dmin gets too large relative to the actual distance differences. For their experiments, the researchers used the well-known wine quality dataset.
Ah, the wine dataset. Classic.
Yep. It contains nearly 5,000 instances, each described by 11 real-valued features, chemical properties like acidity, sugar, alcohol content. They converted the quality target variable, which originally ranges from 3 to 8, into a binary classification problem. Instances with quality of 5 or above were considered accepted, T1, forming the database D for the servers. Those with quality below 5 were considered rejected, T0, and these formed the set SX from which user queries X were drawn. The accuracy metric they used, equation 100, is pretty straightforward and intuitive. For a given query X, let Yx be the actual nearest neighbor in the accepted set D based on the original unquantized real value data. Let Ex be the counterfactual retrieved by their privacy-preserving scheme, which operates on quantized data. The accuracy for that query X is defined as 1 if Ex is at least as close to X as the true nearest neighbor Yx, using the original distances, and 0 otherwise.
So did the private scheme find the real best answer or something equally good?
Essentially, yes. They averaged this binary EO1 accuracy over 100 rounds of randomly sampling the database D and the query set LAX to get robust, statistically meaningful results. The results are presented visually in Figure 3, plotting accuracy against the quantization level R for different values of dmin, used in mass PCR. The trends are very clear and informative. First, you see a consistent upward trend. As R, the number of quantization levels, increases, the accuracy of the retrieved counterfactuals improves for all schemes, steadily approaching 100%. This powerfully confirms that the more precisely you represent the real value data using integers, larger R, the better the scheme performs in finding the actual closest counterfactual. Quantization error decreases with larger R.
Good, so quantization matters, as expected.
Second, focusing on mask PCR for any given R, the accuracy tends to degrade as dmin, the mask size range, increases. This also makes intuitive sense. A larger dmin means the random mask can be larger, adding more noise to the distances. While this noise is designed not to change the ordering if the dmin property holds perfectly, like if X is in DC. In practice with empirical dmin and real data, larger noise makes it slightly harder for the user to distinguish the true minimum, potentially leading to errors if distances are close. And importantly, when dmin 1, the smallest possible value, meaning the math GOI is always 0, mass PCR becomes mathematically equivalent to baseline PCR. And indeed, the results show that dmin 1 achieves the highest accuracy for any given R, matching the baseline performance, because there's effectively no masking noise added.
Okay, that provides a good quantitative handle on accuracy and the impact of quantization and masking parameters. Now let's talk about the really crucial part for the institution, 6.2 database leakage in PCR. How much data about their precious samples YM is actually leaked to the user across these different PCR schemes, baseline, diff, mask? This feels like where the rubber meets the road for evaluating the privacy promises.
Absolutely. This is measuring IYMXNX. To measure this, they precisely computed this mutual information following the rigorous methods detailed in Appendix 8.4 of the paper. Calculating mutual information directly can be computationally intensive, especially for high dimensions and large databases, but it provides a robust information-theoretic measure of leakage. They first tested the schemes on a small synthetic dataset, results in Table 2, to get clear, controlled results where they could compute things more exactly. This was a simple setup: RE4 quantization levels, D2 dimensions, and only ML5 samples in the database. The samples were uniformly distributed for simplicity. The results from this synthetic test clearly demonstrated the theoretical advantages we discussed earlier. Baseline PCR had the highest measured leakage at 3.1297 bits. Diff PCR significantly reduced this leakage to 2.0404 bits. Masked PCR achieved the lowest leakage among the three, with 0.911 bits for dmin 2 and an even lower 0.777 bits for dmin 3.
Wow, quite a difference, especially for mass PCR.
Indeed. This numerically confirms that diff PCR and mask PCR genuinely do reduce database leakage compared to the baseline. It also shows that mask PCR can potentially achieve even lower leakage than diff PCR, and that the amount of leakage in mask PCR depends on the chosen limit. More masking with higher dmin seems to reduce leakage more, at the cost of accuracy, as we saw. This aligns perfectly with our earlier conceptual understanding of how differences and masking provide better database privacy. They then applied this leakage analysis to a more complex, real-world dataset. The COMPAS dataset results in Table 3.
Used in criminal justice context, right? Predicting recidivism.
Yes, that's the one. It consists of over 6,000 instances with 20 features related to predicting reoffending likelihood. After pre-processing, selecting relevant features, handling categorical data, and quantization to R10 levels, they ended up with about 560 unique rejected instances, T0 uses queries X, and about 717 unique accepted instances, T1 forming the database D.
Much larger and more complex than the synthetic test.
Absolutely. And due to the high computational complexity of calculating mutual information directly over all possible combinations of M717 samples for such a data set, they used extensive sampling, 100,000 permutations, to approximate the leakage values.
So these are estimates, but based on a lot of samples.
Right, robust estimates. The results from the COMPAS dataset showed a similar relative trend, even with the complexities and potential noise of real-world data. Baseline PCR leakage estimate, 1.51437. Diff PCR leakage estimate, 1.51436. Mass PCR Demon 2 leakage estimate, 1.51427.
The differences seem much smaller here.
They are much smaller in absolute terms compared to the synthetic dataset, likely due to the nature of the data distribution and the larger scale. However, the relative ordering baseline diff masks still holds. Mass PCR still provides the lowest estimated leakage, followed by diff PCR and then baseline. This provides strong empirical evidence for the practical effectiveness of these schemes in reducing database leakage, even when applied to more complex and realistic data distributions where the theoretical advantages might be less pronounced but still present.
Okay, that covers the basic PCR schemes. Now, what about the leakage when we factor in those immutable features with the IPCR schemes? Does the two-phase approach truly leak less information about the database to the user than the single-phase approach, as the theory suggested?
That's exactly what the final numerical experiment, 6.3 database leakage in IPCR, rigorously investigated. They compared the database leakage of both two-phase and single-phase IPCR schemes, again using a controlled synthetic dataset, R3 quantization, D3 dimensions, N3 samples, to isolate the effects clearly. Let's recall the leakage sources. For a single-phase IPCR, the user observed the computed value, EIST, EIXH, for every sample I in the database. The leakage is therefore quantified as IYM, YST, IX, equation 101. This single value per EI contains combined information about immutable matches and mutable distances. For two-phase IPCR, the leakage calculation is broken down based on the phases, equation 102. Leakage G's HEMSI plus I, YMX, MNX, I, EM. The first term, HEMXI, is the unavoidable leakage from learning the set which samples match immutables. The second term represents the additional leakage from phase 2, which simplifies equations 103, 105 to basically the information revealed by the decoded distances die only for those I within. The results from this experiment comparing the two IPCR schemes are compelling and presented in Table 4. They measured the leakage for different numbers of immutable features, I ranging from 0, the no immutables equivalent to PCR, to DD3, all features immutable. The key finding is crystal clear. Two-phase IPCR consistently shows lower leakage than single-phase IPCR for all tested values of I, from 1 to 3.
Lower leakage across the board for two-phase.
Yes. This strongly supports the theoretical analysis we discussed earlier. Knowing only the set EM, which samples match immutables, plus the distances for only those matching samples, two-phase, reveals less information about the overall database YM than receiving values that implicitly encode how many immutable features mismatch for all samples, single-phase. Furthermore, they observed an interesting symmetry for the single-phase scheme. The leakage values were equal for complementary numbers of immutable features, meaning the leakage for I1 was the same as for I2, since D3. Critically, for the two-phase scheme, the database leakage decreases as the number of immutable features increases.
Why would making more features immutable reduce leakage?
Because a larger immutable set, I generally mean the set of eligible counterfactuals, those matching L alive, is expected to be smaller. If L is smaller, phase 2 operates on fewer relevant samples and thus leaks less information about the distances within that smaller set. The initial leakage, HEMXI, might change, but the dominant factor seems to be the reduced scope of phase 2. The I8 case, where D3 here, is particularly insightful and highlights the difference starkly. In this scenario, all features are considered immutable. If the user's X is a rejected sample, then the set must be empty. Why? Because if there were an accepted sample Y and B that perfectly matched X on all features, EII is XI, where I is all features, then Y would be identical to X, meaning X should have been accepted, which contradicts our premise, so L is empty.
Right, no accepted sample can be identical to my rejected one.
So for the two-phase scheme, in phase 1, the user learns that E is empty. All recovered values are non-zero. The process stops. There's no need for phase 2. Therefore, the total database leakage in this case is effectively HEMXI, which is just the information that is empty, arguably minimal leakage, reported as 0 in the table perhaps relative to some baseline. No information about specific I distances is revealed. However, for the single-phase scheme, even if A is effectively empty, the user still receives and processes the computed values, IXT, YIX, for all M samples in the database. While these values will all fall into the mismatch range, because K, the number of mismatches, will be non-zero if E is different from X, they still reveal some information about the database, such as the distribution of K values, how many features mismatch for each E. This constitutes measurable non-zero leakage, even when no actual counterfactual exists. This clearly demonstrates a significant database privacy advantage for the two-phase approach, especially in scenarios with many immutable constraints. Hashtag outro.
Wow. We have truly gone on an extraordinary deep dive today, haven't we? Into the intricate world of private counterfactual retrieval.
We really covered a lot of ground.
We began by grounding ourselves in that crucial and increasingly mandated need for transparency and explanations in AI, especially when those powerful, often mysterious black box models make high-stakes decisions about our lives, loans, jobs, health.
Absolutely critical context.
From there, we tackled the often underexplored, but as we saw, immensely important challenge of user privacy. How do you ensure that your personal data remains perfectly hidden, even as you're asking the system for actionable insights?
Indeed. And we navigated through some truly ingenious mathematical constructions along the way. From the sheer power of Vandermonde matrices, acting as those secret decoder rings that let the user perfectly unscramble the hidden distance information,
Loved that analogy.
to the elegant simplicity yet profound strength of Shannon's one-time pad, which provides those robust, ironclad information-theoretic privacy guarantees for the user's input.
Yeah, the foundation.
We explored multiple schemes designed for different privacy appetites. The baseline PCR, which established that foundational perfect user privacy, and then the diff PCR and mask PCR, which took aim specifically at reducing the amount of information leaked about the institution's proprietary database, offering better protection for their data assets.
And we didn't stop there. We layered on the real-world complexity of immutable features, those inherent attributes about yourself you simply cannot change, and saw how the IPCR schemes, both the two-phase and the single-phase versions, tackled this challenge while maintaining that perfect user privacy, including privacy for the immutable set itself.
A significant step up in complexity.
And finally, we demonstrated how your personal preferences for changing attributes, what the paper calls user actionability, can be seamlessly woven into these schemes using weighted distances. This allows for truly personalized and private counterfactual explanations, guiding you towards changes you're actually willing to make. It's really a comprehensive approach to making AI both transparent and deeply respectful of individual privacy and preference.
I think the key takeaways from this entire journey are pretty clear. First, counterfactual explanations are incredibly powerful tools, not just for understanding AI decisions, but for navigating them, potentially even influencing future outcomes.
Right, they give you agency.
Second, user privacy is not just an add-on or a compliance checkbox. It's a critical, often overlooked, and absolutely foundational aspect of truly ethical, fair, and ultimately usable, explainable AI.
Couldn't agree more.
Third, information theory, particularly Shannon's one-time pad and concepts like mutual information, provides the rigorous mathematical bedrock for achieving these perfect, provable privacy guarantees. It's not just heuristics, it's math.
The gold standard.
And importantly, as we saw, different schemes offer varying trade-offs between communication costs, the required size of the underlying mathematical fields, which impacts computation, and that crucial database leakage metric. This variety means that institutions can actually choose a scheme that aligns precisely with their specific privacy budget, their computational resources, and their operational constraints. It demonstrates powerfully that useful AI explanations don't have to come at the cost of sacrificing your personal data.
You know, this deep dive really shows us something profound, I think. Privacy doesn't have to be an afterthought in AI design or some cumbersome add-on that cripples functionality. It can be built in from the ground up, woven right into the very fabric of the system, using elegant mathematical solutions like the ones we explored today.
It's privacy by design, truly.
So as AI becomes more and more ubiquitous, touching every corner of our lives, how might these rigorous information-theoretic approaches change our expectations for how all our sensitive data is handled in the future? What standards should we demand? And maybe more personally, what steps will you, our listener, take to ensure your digital interactions prioritize privacy? Something to mull over until our next deep dive.
Thank you so much for joining us on this deep dive. If this discussion sparked more questions, or maybe you're curious to explore more cutting-edge research in this fascinating intersection of AI, privacy, and explainability, please do reach out to us. We genuinely love hearing from you.
We do indeed. Until next time, keep digging deeper.
Welcome, curious minds, to the deep dive. Imagine this. You've just received a decision from a powerful AI system. Maybe it's a bank loan application denied.
Right. Or a job application rejected.
Or even a particular medical diagnosis that seems to defy understanding. The answer comes back, no.
And it's frustrating, right?
It is. But what truly gnaws at you isn't just the rejection itself, it's the unknown. You're left wondering, what if? What could I have changed to get a yes? That profound desire for actionable feedback for that crucial what-if scenario? Well, that's the world of counterfactual explanations.
Exactly.
Today, we're taking a deep plunge into a truly fascinating and incredibly timely research paper. It asks, what if, but privately, private counterfactual retrieval? Our mission for you, our dedicated listener, is to explore how these powerful, often mysterious black box machine learning models can offer transparent, actionable explanations, those crucial what-ifs, without, and this is key, compromising anyone's privacy.
Yeah, that's the crux of it.
We're not here to just slog through dense jargon. Instead, we'll uncover the brilliant engineering behind making AI more fair, more accountable, and ultimately far more useful for you.
Exactly. We're going to unpack a critical and often overlooked problem. How do you provide those essential what-if explanations while rigorously protecting the user's highly personal data?
Right.
We'll journey through the inventive mathematical frameworks and clever schemes these researchers propose, discuss their inherent trade-offs, and then examine how they actually stand up when put to the test in real-world scenarios. So get ready for some serious aha moments, because the insights here are, well, pretty profound.
I'm ready. Let's dive in. Okay, let's unpack this. Why are we even talking about counterfactual explanations in the first place? What's the big deal with the machine learning model just spitting out a yes or a no without further elaboration? I mean, it seems like pretty common interaction with AI today.
Well, what's truly fascinating here, and indeed rapidly becoming a legal and ethical mandate in many jurisdictions globally, is what's often referred to as the right to explanation.
The right to explanation.
Yeah. Think about high-stakes applications like finance, insurance, or, say, healthcare. A black box model, meaning, a sophisticated AI whose internal workings are incredibly complex and not easily interpretable by humans.
Right. Opaque.
Exactly. Opaque. It simply can't provide a binary no without giving a clear, suitable reason for its decision. This isn't merely about politeness. It's fundamentally about transparency and accountability.
Makes sense.
If an AI is making decisions that can profoundly alter your life, you, as the user, have a fundamental right to understand the underlying basis of that decision. It's becoming essential.
That makes perfect sense. So thinking back to our bank loan rejection example, instead of just a flat denied, a counterfactual explanation would offer something concrete, something actionable.
Precisely. Instead of just a generic no, a powerful counterfactual explanation might tell you something incredibly actionable, like, if you had increased your verifiable annual income by $10,000, your loan would have been approved.
Okay. Specific.
Or maybe if your credit utilization ratio was below 30%, you would have qualified. This kind of feedback is invaluable because it's not just an explanation of why you were rejected.
Right.
It provides clear, actionable advice on how you can change your circumstances to achieve the desired outcome in the future. It really empowers the user,
It really does. And the paper touches on several desired properties for these counterfactuals, beyond just being close to your original input, right?
Yeah.
Because just any old change might not be helpful.
Absolutely. Well, proximity to the user's original input is a primary concern. You want the smallest possible change to achieve the desired outcome. The broader research in this field highlights other crucial properties.
Like what?
Well, for instance, robustness is vital. You want an explanation that doesn't drastically shift if the underlying model has slight variations.
Okay, stable explanations.
Then there's feasibility. This means the recommended change should be something a user can actually do. Telling someone to magically drop 10 years off their age isn't a feasible counterfactual, obviously.
Yeah.
Sparsity suggests changes to as few attributes as possible, which makes the advice easier to act upon.
Makes sense. Simpler changes.
And diversity means offering multiple possible pathways to a yes, not just one single path.
Options.
Right. This particular paper, while acknowledging all these, deeply focuses on achieving both proximity and, importantly, actionability, which we'll definitely delve into more deeply.
So getting an explanation sounds fantastic, but here's where it gets really interesting and where this paper shines a light on a less explored but truly critical privacy concern. Most existing work on explainable AI focuses on protecting the institution's data.
Yeah.
Their proprietary model or their vast database of accepted samples.
Yeah, that's the usual focus.
But what about my privacy? The user who's asking for the explanation. I'm the one revealing my sensitive financial, medical, or highly personal data to even get this what if.
This raises a very important question, one that the paper tackles head on. Why would a user be reluctant to reveal their input feature vector, essentially, their deeply personal data to the institution, even when they're actively asking for an explanation?
Good question. Why would they be?
Well, think about it. It could be about navigating a limited number of application attempts. If you apply for a loan and get rejected, and then the bank learns all your current sensitive details just because you asked for an explanation, well, that interaction might count against future applications, right?
Yeah, I see. It could impact future tries.
Or maybe more generally, it could simply be about preserving your fundamental data privacy until you've actually improved your chances of acceptance. You might not want to disclose your current, less than ideal financial standing if you know you're going to work diligently on improving it before applying again.
Yeah, that makes total sense. You want to put your best foot forward.
Exactly. The core problem this paper sets out to solve is precisely this. How can a user retrieve a counterfactual instance without revealing their own sensitive feature vector to the institution? And the paper makes a very strong promise here.
Which is?
To achieve perfect information-theoretic privacy for the user. That's a very high bar.
Wow. Perfect information-theoretic privacy. That sounds incredibly powerful. This whole problem feels a bit like trying to find a specific book in a massive library without revealing what book you're actually looking for to the librarian.
That's a great analogy, actually.
Does it connect to other established areas of computer science or cryptography then?
Absolutely. It's deeply rooted in and skillfully leverages techniques from several fascinating and well-established fields. Closely related is the nearest neighbor search problem, where the goal is to find data points in a large data set that are closest to a given query point, but the privacy constraint makes it much, much harder. The paper ingeniously applies techniques from Private Information Retrieval, or PIR.
PIR.
In a standard PIR setup, a user wants to retrieve a specific message out of many identical copies stored across several servers, but they absolutely don't want any of those servers to learn which specific message they are interested in.
That sounds exactly like what we're trying to do with the counterfactual index. I want to know the index of the best counterfactual, but I don't want the server to know which one I'm looking for.
It is very similar. And building on PIR, there's also symmetric PIR, or SPIR.
SPIR.
Yes. In SPIR, there's an even stronger requirement. The user gets only their requested message and nothing else.
Okay.
And the servers still learn nothing about the user's request. This paper brilliantly combines these PIR and CVIR ideas to achieve both user privacy and, to some extent, limit the leakage of the institution's database.
How does it combine them?
The process generally involves two clever steps. First, you privately find the index of the desired counterfactual instance in the database using a PIR-like scheme.
Okay. Find the location.
And then you privately retrieve the actual counterfactual itself using that index through a SPIR-like mechanism. This two-step process is really crucial for their overall robust privacy guarantees.
Before we dive deeper into the ingenious schemes and how they actually achieve this seemingly impossible feat, let's quickly go over some foundational concepts and the language they use. Don't worry, we'll make this approachable, breaking down each piece step by step.
Yeah, understanding these foundational symbols and definitions is really key to appreciating the mathematical rigor and the cleverness embedded within this work. They truly are the vocabulary of this deep dive.
All right, hit us with the first one.
Okay, first we'll often encounter a notation like n. This simply denotes the set of positive integers starting from 1 up to n.
Simple enough, like 5 is 1, 2, 3, 4, 5.
Exactly. Similarly, for ranges, mn denotes the set of integers from m to n inclusive. So 10 path means 10, 11, 12.
Got it. What's next?
Next, a very common one, a. This signifies the cardinality of a set A.
Which is just the number of things in the set.
Precisely. This is a formal way of saying the number of elements in that set. If set A is apple, banana, cherry, date, then A would be 4.
Okay, cardinality. Easy enough.
For vectors, you'll see AT. This represents the transpose of vector A.
So flipping a column vector into a row vector.
Essentially, yes, it turns it into a row of numbers, which is important for certain mathematical operations like dot products.
Right, okay.
Now, a truly crucial notation for the cryptographic guarantees in this paper is FQ.
FQ. Okay, this sounds important.
It is. This denotes a finite field, often called a Galois field. The Q here must be either a prime number, like 5, 7, 11, or a power of a prime number, like 4, which is 2 squared, or 8, which is 2 cubed.
Finite field. So a number system with a limited set of numbers.
Exactly. Think of it as a special number system where all mathematical operations, addition, subtraction, multiplication, and even division, as long as you're not dividing by 0, are performed modulo q.
Modulo Q, like clock arithmetic, wraparound.
That's a great way to think about it. For instance, if we're working in F5, the finite field with 5 elements, 0, 1, 2, 3, 4, then 3 plus 4 wouldn't be 7. It would be 7 mod 5, which gives you 2.
Ah, okay. 7 wraps around past 4 back to 2.
Correct. Similarly, 3, 4 would be 12 mod 5, which is also 2. This unique wraparound property is absolutely fundamental because it allows for arithmetic operations that perfectly hide information in a provably secure way. It forms the backbone of their privacy guarantee.
Wow, okay. Finite fields are key. What else?
We also have H. This stands for Shannon entropy.
Shannon entropy. Sounds like physics, but it's information theory, right?
Exactly. In the world of information theory, entropy is a rigorous mathematical measure of the uncertainty or randomness of a random variable.
So more entropy means more randomness.
Precisely. The higher the entropy value, the more uncertain or random that variable is.
Okay. And related to that?
Related to that is I, which represents mutual information.
Mutual information. How much one thing tells you about another.
You got it. This quantifies the exact amount of information you gain about one random variable by observing another random variable. For example, if ixy is a high number, it means that x tells you a lot about y and vice versa.
And if it's 0?
If ixy is 0, it means observing x tells you absolutely nothing new about y. They're independent in terms of information. This is critically important because it allows the researchers to formally express and prove their privacy guarantees.
Ah, showing that the server learns nothing at all.
Exactly. Showing user data, server view, it's 0.
Got it. Any other notation?
Just one more main one. Throughout the paper, a bold italicized font, like A, is used to denote a matrix.
Okay, so bold italics means a grid of numbers.
That's right, not just a single variable. These notations collectively form the precise mathematical vocabulary for describing the ingenious constructions that follow.
So we've got the language down. Now, the paper relies on 2 exceptionally elegant mathematical concepts that truly make their strong privacy guarantees possible. It's almost like they're building a cryptographic puzzle using these specific, powerful tools.
They absolutely are. These aren't just arbitrary choices. They are foundational to achieving information-theoretic security, which, as we mentioned, is the strongest form of privacy proof you can get.
Okay, what's the first tool?
The first is a Vandermonde matrix.
Vandermonde.
That sounds fancy. It is a special type of matrix, and it's quite beautiful in its simplicity and raw power. It's constructed in a very specific way using distinct non-zero elements from our finite field FQ.
How is it constructed?
Imagine you have a set of distinct numbers from FQ, say a POLT1, FE2, FE3. A 3x3 Vandermonde matrix built from these would have its first column as all ones, its second column as Evan1, FE3, and its third column as Evalintwick 12, A22, FE2, and so on for larger matrices. Each column is the previous column's elements multiplied by the corresponding alpha.
Okay, specific structure based on powers. What's special about it?
The truly crucial property of any Vandermonde matrix, precisely because its building block elements are distinct and non-zero, is that it is invertible.
Invertible?
Yeah.
Meaning you can find another matrix that undoes it.
Exactly. This means that if you have a system of linear equations where your unknown variables are multiplied by the elements of a Vandermonde matrix, you can always uniquely solve for those unknowns by multiplying by the inverse matrix.
So it lets you unscramble things.
It's like having a universal secret decoder ring. If you receive a scrambled message that was generated using a Vandermonde matrix, knowing the matrix allows you to perfectly unscramble it and recover the original information. This invertibility is absolutely central to how the user, later in the schemes, can recover hidden distances privately.
Very cool. Okay, Vandermonde matrix for decoding. What's the second foundational tool?
The second foundational tool, and truly the cornerstone of the information-theoretic privacy guarantees, is Shannon's one-time pad.
The one-time pad. The famous unbreakable encryption, right?
That's the one. It's a profound and incredibly powerful result in cryptography. It states that for any secret random variable X that you want to hide.
Like my personal data.
Exactly. If you add a truly random, uniformly distributed variable Z from the same finite field to your secret X using the special arithmetic of FQ.
Adding noise.
The resulting sum, X plus Z, reveals absolutely nothing about your secret X.
Right.
Mathematically, Ix, X plus Z equals 0 if Z is uniform and independent of X.
So if I have my secret number X and I add a completely random number Z to it, The sum x plus z looks just as random as z by itself, and you can't work backwards to figure out x. Is that the intuition?
Exactly. The sum is mathematically indistinguishable from pure noise, preventing any inference about the original secret. Imagine trying to find a specific grain of sand on a perfectly randomized beach.
Impossible.
Precisely. This is exactly how the user's sensitive data, like their personal feature vector, remains perfectly private from the servers. Even if a server observes the padded query, it learns literally nothing about the user's original input because the random pad completely obscures it.
So these two tools, the invertible Vandermonde matrix for perfect decoding and the one-time pad for perfect privacy, are the magic ingredients.
They're ingeniously combined throughout all the proposed schemes, yes.
So now that we have the language and the core tools, what exactly is the user trying to do, and what are the strict rules of engagement in this private counterfactual retrieval, or PCR, setting?
Okay, let's formalize the challenge. In this setup, an institution possesses a pre-trained black box machine learning model. This model takes a multi-dimensional feature vector as input. Think of it as a set of characteristics describing you, like income, age, credit score, health markers, and so on.
Your personal profile.
Right. It then classifies that input as either accepted or rejected. Now, our user, who has unfortunately been rejected by this model, wants to privately retrieve a valid counterfactual sample that corresponds to their own data.
But they can't just ask the model directly.
Critically, the user doesn't have direct access to the model itself. Instead, they rely on a database D of accepted samples, perhaps M of them.
Good examples.
Exactly. These are stored across N non-colluding servers. Non-colluding is a very important detail. It means these servers don't conspire or secretly share information with each other to try and deduce your private data.
Okay, independent servers.
And each feature within these data samples N is assumed to be an integer within a specific numerical range, say from 0 up to R. So Y is the ith accepted sample vector.
Got it. So what's the user's main goal?
The primary goal, defined as EQ1 in the paper, of the user in this entire process is to find I, which is the index of the accepted data sample Y in the database D that is closest to their own feature vector X.
Finding the nearest accepted neighbor.
Precisely. We're looking for E argmin IMDX, Y. Initially, for most of the paper's initial discussions, this closest distance, EXY, is measured using the standard Euclidean distance, or A2 norm. So DXY, YY by 2.
Okay, find the index A of the closest Y using A2 distance. How does the interaction work?
The process flow, shown nicely in Figure 1, outlines the interaction. First, the user generates a special encrypted query based on their own private data X. They generate N queries, QXN, for each server N.
One query per server.
Yes. They send query QXN to server N. Upon receiving these queries, each server N computes its own part of the answer, AXN, using its stored data D and possibly some shared randomness.
Okay.
Once the user receives all the answers, AX1, AXM, from all N servers, they combine this information to magically determine the index of that nearest accepted counterfactual sample.
And there are rigorous definitions for success and privacy here, right? It's not just, we hope it works.
Yeah.
They have actual mathematical proofs based on those concepts, like mutual information.
Precisely. The paper lays out very rigorous formal definitions for 3 core constraints that any successful scheme must satisfy. These use the information theory concepts we just discussed.
Okay, what's the first constraint?
First, there's PCR decodability, EQRS 3. In plain language, this means the user must be able to figure out the index uniquely and perfectly from the information they've gathered their own input X, the queries they sent QXN, and the answers they received AGXN.
No ambiguity allowed.
Exactly. Formally, the entropy of egg given all that information must be 0. HQXN AXN X equals 0. No uncertainty left.
Okay, perfect decoding. What's next?
Second, and paramount, is PCR user privacy EQ4. This is that very strong information-theoretic guarantee. It states that each individual server N learns nothing at all about your personal data X or which specific counterfactual index you're looking for, even given the database D.
How is that written mathematically?
It's expressed using mutual information, IX QXND equals 0 for each server N. The mutual information between the user secrets, X, and what the server sees, QXN, conditioned on the public database D, must be 0.
Zero information learned by the server. That's where the one-time pad comes in.
Absolutely. That's how this is achieved.
And the third constraint?
Third, they define PCR database leakage, EQ5. This metric rigorously quantifies how much information about the institution's entire database D, which is Y1, YM, is accidentally leaked to you, the user, during the entire process, given your own input X.
So how much the user learns about the database.
Exactly. It's measured as I, Y1, D, YM, QXN, AXNX. While you need some information to find your counterfactual D, the ultimate goal of these proposed schemes is to minimize this leakage about the entire database D to the user.
It's a balancing act then. Give the user the answer without giving away the whole database.
Precisely. It's a crucial balancing act, providing you with a helpful explanation without giving away too much of the institution's proprietary or sensitive data Y1 EKES-LIM.
Now, what if you can't or simply don't want to change everything about yourself? For instance, you can't change your citizenship or your educational background instantly, even if a model suggests it's the closest counterfactual.
Yeah.
How do these privacy schemes handle that very practical real-world constraint?
This is a critically important and practical extension leading to what they call the Immutable Private Counterfactual Retrieval, or IPCR setting.
IPCR for immutable.
Right. In this scenario, you, the user, specify a private subset I of indices corresponding to your features that must not change in the counterfactual explanation. These are your immutable features.
Like age, maybe place of birth?
Exactly. The remaining features, indexed by the set M, are considered mutable. They can be altered in the suggested counterfactual.
Okay. But the institution doesn't know my set I.
That's the truly clever and complex part here. The institution doesn't know which features are immutable for you. That immutable set I is itself part of your private information that needs protecting.
Ah, another layer of privacy needed.
Definitely. So the modified goal for IPCR, EQ7 figure 2, becomes finding GAI, the index of the closest accepted sample Yi in the database, but with a crucial additional filter. The search is restricted only to samples in the database D that perfectly match your immutable features.
So only look at samples E where the immutable parts match my X.
Precisely. We define a set A theta, which contains the indices I from M, such that the immutable features of sample U, denoted EI, are equal to the immutable features of the user's input X, denoted of I, so MNI EII.
Okay.
The goal is then to find the index I that minimizes the distance dx only among the indices I that belong to this set, I argument IA dxa.
So you first filter by immutable features, then find the closest among those that match.
Exactly. And the modified constraints for IPCR are similar to the general PCR setting, but now they factor in your private immutable set I.
Let's quickly run through them.
Okay. IPCR decodability, EQ8, means you must be able to find XI, the queries and answers, HIQXN, AXNXI equals 0.
Perfect decoding, considering I.
IPCR user privacy, EQ9, now ensures servers learn nothing about your input X, the target index I, or your specific immutable set I, so IX, AII, QXND equals 0.
Even stronger user privacy.
Yes. And IPCR database leakage, EQ10, still quantifies what's leaked about the institution's database, D, Y1 to YM. Given your input X and your immutable preferences I, YM, QXM, AX, NX, the overarching goal remains to reduce this database leakage while preserving perfect user privacy for both your data X and your immutable choices. Okay, so now let's get into the actual solutions proposed in the paper. All the private counterfactual retrieval schemes we're about to discuss, whether they are the baseline, diff-PCR, or mass PCR, share some fundamental principles.
Right, some common ground.
They all rely on having at least any two replicated servers. This means the institution's entire database D of M-accepted samples is duplicated on 2 or more independent, non-colluding servers.
2 copies of the database.
At least 2, yes. And for simplicity in these initial schemes, they primarily use the standard Euclidean distance, or E2 norm, to measure how close one data point Y is to another X, so dxy by 2. We'll sometimes write dx as shorthand for dxu, the distance between the user's X and the I of a database sample U.
Okay, N2 servers, UD2 distance. Let's start with the simplest version, the baseline PCR. How exactly does it work, and what kind of privacy and efficiency does it achieve?
Right, the baseline PCR scheme is the foundational building block. It's presented in section 3.1.
And what's the main guarantee, Theorem 2?
Right, exactly. Theorem 2 states it guarantees perfect user privacy, meaning IX, QXND, E equals 0 for each server, and U is 1, 2. And it works with N2 servers.
What about costs?
The communication cost involves sending and receiving a certain number of data symbols, basically, mathematical numbers from our finite field FQ. The total cost is 2D plus M symbols, where D is the dimension number of features and M is the number of samples in the database.
And the finite field FQ? Any constraints there?
Yes, a critical requirement mentioned in Theorem 2 is that the size of this field, Q, must be large enough. Specifically, Q needs to be greater than R2D, where R is the maximum possible value for any feature component.
QR2D. Why so large?
Because the squared Euclidean distance y by 2 involves sums of squares of differences. Each difference, xk, can range from -r to +r. Squaring gives up to r2. Summing d of these gives a maximum possible distance squared of dr2. The field fq needs to be larger than this maximum possible distance value to ensure that different true distances don't accidentally wrap around and become equal in the fq arithmetic. If they did, you wouldn't be able to tell which distance was actually smaller.
Ah, okay. Avoid collisions in the modulo arithmetic. So how does the process work? The query.
Let's walk through the process. It's quite elegant. You, the user who wants to find your closest counterfactual, first generate a truly random vector z of dimension d from the finite field fq. Think of this as your one-time pad vector.
Okay, a secret random vector z.
Then you construct a special query for each server n, where n is 1 or 2. The query qxn is defined in equation 14 as qxn is equals x plus unz.
X plus nz. What's then?
Anna, alpha n, are distinct non-zero elements known to everyone, user and servers, from the finite field fq. Think of them as public constants, like IO1 at 2 as 2 if q is large enough.
So my query is my data x plus a scaled version of my random vector z.
Exactly. You send qx1 to server 1 and qx2 to server 2. Because z is truly random and uniformly distributed, each query qxn looks indistinguishable from pure noise to the server. Therefore, due to Shannon's one-time pad theorem, each server learns absolutely no information about your sensitive input data x. User privacy is achieved right there.
Perfect user privacy from the query construction. Now, what do the servers do? The answer part.
Right. Upon receiving your padded query qxn, each server n computes an answer vector axna. The ith component of this answer vector axni corresponds to the I qxn2 plus ein zi.
Hold on. Y qxn2, that's the square distance between the database sample y and my padded query qxn was the I.
Z is another component of randomness. Specifically, z is an m-dimensional random vector shared between the user and both servers, used for another layer of one-time padding on the server's calculation itself. So the server calculates the distance to your padded query and adds more scaled noise.
Okay. Why calculate the distance to the padded query qxn?
This is where the algebra gets clever. Let's expand that squared norm, as shown in equation 16. We substitute qxn equals x plus nz. Yi qxn2 equals yi x plus nz2.
Okay, distance between ux and z.
Expanding the squared norm gives yi by 2 to n di xtz plus nn2z2.
Wow, okay, so it expanded to 3 terms. The first term, yi by 2, is dx, the actual distance we want.
Exactly. That's the key. The server calculates something based on the padded query, but hidden inside is the actual distance dx.
So putting it back into equation 15 for the server's answer, x, ni, x2, and xtz plus nn2z2 plus nz.
Right. Let's regroup the terms involving n. We can define an interference term, ii, nx2, zi, xtz plus z.
Okay, ii captures the terms linear and un involving z and z.
Then the answer becomes xni equals ddex plus nii plus nn2z2. Notice this structure. For each sample I, the server's answer, xni, is a quadratic polynomial in die.
A quadratic in unded x is the constant term, I is the coefficient of ein, and z2 is the coefficient of un2.
Precisely. Now, how does the user decode this? They get x1i from server 1 and x2i from server 2.
So for each sample I, they have 2 equations.
Yes. For each I, they have x1i plus niy plus x1ii plus x2i bz2. x2i equals d2 plus xni plus xno is z2.
And the user knows x, z, agus, and ein, and z. So they know I, and z2. Wait, no.
Ah, good point. The user knows x and z, so they can compute the z2 term themselves. They also technically know z die, so they know the unknown too. Let's simplify. The user can subtract the known term x1iz from each received answer axmoni, with axni at xno and 2z2.
Okay, subtract the quadratic term. So now we have agus1i is tcab plus xnii, agus2i plus xno z2.
Exactly. Now, for each sample I, the user has a system of 2 linear equations with 2 unknowns. The distance at ix they want, and the interference term I.
2 equations, 2 unknowns, and IO1 and IA are distinct. Now, this looks familiar.
It should. This is exactly where the Vandermonde matrix comes in.
Okay.
This system can be written in matrix form, equation 17, AI1, IOI, 1I1 dii. AI shu I equals 1A 2 II.
Ah, the matrix 1 I1 1 I2 is the 2x2 Vandermonde matrix V2.
Precisely. Since I1 and I2 are distinct and non-zero, V2 is invertible. The user calculates the inverse V21.
And multiplies the answer vector by V21, equation ET.
Exactly. DAX IIT equals V21 AI, AIO2 IT. This perfectly recovers both DIX and I for every sample I from 1 to M.
Wow, so the user gets the exact distance die for all samples. The interference term II is also recovered, but the user doesn't care about it.
Right. II is just a byproduct containing the random padding. The user only cares about the DIX values. Once they have D1X, D2X, DMX, they simply find the minimum value and identify the corresponding index DII.
That's incredibly elegant. The one-time pad hides the query X, and the Vandermonde matrix helps unmask the actual distances die from the combined encrypted server responses. Let's recap the costs.
Sure, costs are upload. User sends QS1 and QX2. Each is a d-dimensional vector. Total upload is 2D symbols, download. User receives AX1 and AX2. Each has M components. Total download is 2M symbols. Total communication, 2D plus 2M. Computation, user needs OD plus M operations, mostly vector ops and finding the min. Each server needs OMD operations, computing M distances involving d-dimensional vectors.
Seems reasonable. And Remark 1 mentions flexibility.
Yes. Remark 1 points out that this core idea using the unscaling and Vandermonde decoding can be extended to other distance metrics. For instance, other UC norms, like 004, can work if you use N-to-K servers because the expansion will be a polynomial of degree K and Amin. Even a simple dot product metric can work with N-2 servers. The fundamental principle remains the same.
So the baseline works, guarantees user privacy, but knowing all the exact distances D1X, DMX, could still reveal something about the institution's proprietary database D. Can we be even more private about the institution's data? Reduce that database leakage.
You're hitting on a crucial point. While user privacy is perfect in baseline PCR, the institution's database leakage, I, YM, XMX, is non-zero because the user learns all the distances. This is where diff-PCR, or difference of distances PCR, section 3.2, comes in.
Diff-PCR, aiming to reduce database leakage.
Yeah.
What does Theorem 3 say?
Theorem 3 states that diff-PCR achieves lower database leakage than baseline PCR. It still uses N2 servers. The communication cost is slightly lower, 2D plus M1 symbols. However, it requires a larger finite field size Q.
Larger Q. How much larger?
It needs Q2 R2D. Remember, baseline needed QR2D, so roughly double the field size.
Why double?
This larger field size is essential because the scheme cleverly deals with differences between distances, DJX. These differences can be positive or negative. The maximum absolute difference could be up to R2D if one distance is 0 and the other is max. To represent both positive and negative differences up to this magnitude distinctly in FQ, you need roughly twice the range. So Q needs to accommodate values from about meta R2D to plus R2D.
Okay, don't need a bigger field for differences.
Yeah.
What's the core idea? How does it work?
The main idea of diff-PCR is indeed to improve database privacy by having the servers reveal only the differences between consecutive distances, dx, di plus 1x, rather than revealing each individual distance dix.
So instead of D1, D2, D3, the user learns D1, D2, D2, D3.
Exactly. You, the user, still send the same type of clever padded query QXN equals X plus I and Z as in the baseline scheme.
Yeah.
That part is identical, ensuring user privacy.
Okay, query's the same. What about the server's answer XN?
EQ21.
The server's now compute a different answer. For each I from 1 to M1, server N computes AXNI as EQXN2 YI plus 1, QXN2 plus NZI.
Ah, the difference between the squared distances to consecutive samples Y and YI plus 1, plus the usual steeldoys on Z.
Right. Now, remember the expansion we did for EQXN2? It was DI plus NI plus on I plus onto Z2.
Yes.
If we do the same for YI plus 1 QXN2, we get DI plus 1X plus NI plus 1 plus onto Z2.
Okay, so the difference term YQXN2 YI plus 1 QXN2 becomes DI plus 1X plus II plus 1. Notice the unto Z2 terms cancel out perfectly.
Oh, that's neat. The quadratic term vanishes in the difference.
Exactly. So the server's full answer, AXN IAQ23, simplifies to AXNI I plus 1 plus I plus 1 plus on ZI. We can group the interference terms. I plus 1 plus ZI.
Okay, so XNI, EDI plus 1X plus on I. This looks like the baseline answer structure again, but with difference, DX, DI plus 1X is the constant term.
Precisely. For each I from 1 to M1, the user receives X1I and X2I. they again have a system of two equations, x1i plus x2i plus x2i, where x2i is di plus 1x.
And they use the inverse Vandermonde matrix V21 again?
Exactly. They multiply the received answer vector x1i, x2it by v21 and perfectly recover the difference dx dla plus 1x for all I from 1 to m1.
Okay, so the user gets D1, D2, D2, D3, DM1, DM. How do they determine the absolute closest counterfactual P if they only have these differences and not the actual distances? That sounds like a puzzle.
It is, and it's elegantly solved in algorithm 1. You reconstruct the identity of the closest counterfactual P by iteratively comparing these differences.
How does that work?
Let's say you initialize your best guess for the index as LU1. Then you look at the first difference you recovered, D1x, D2x. Now remember, we're working in the finite field FQ, where Q to R2D. The actual difference, D1x, D2x, can range from ang and R2D to plus R2D.
Right.
If the recovered difference falls into the range corresponding to negative values in FQ, specifically the range R2D plus 1Q1 represents negative numbers in this mapping, it means D1x, D2x is negative, which implies D1x, D2x. So sample 1 is closer than sample 2. Your best guess remains 1.
And if the difference falls in the range for positive values, 1 R2D.
That means D1x, D2x is positive, so D1x, D2x, sample 2 is closer. So you update your best guess for 2.
Okay, so you compare 1 and 2, then you look at DX, D3X.
Exactly. You use the recovered difference dxd plus 1x. Well, you reconstruct this from the sequence of differences. And again, check if it's positive or negative using the ranges in FQ. If it's negative, ball stays. If it's positive, you update thir to the next index I plus 1. You repeat this for all M1 differences.
Wow. So by working with differences in carefully chosen field sizes, they implicitly learn the ordering of distances without knowing the distances themselves. Clever.
It is very clever. It allows you to still pick the best counterfactual ask while revealing less about the specific divest values in the database, thus reducing database leakage.
What about the costs for diff PCR?
The communication costs are upload taken, same as baseline, download to M1 since there are M1 differences, slightly less than baseline's 2M, total second plus 2M2. Computation complexity is very similar to baseline PCR.
Okay, diff PCR reduces leakage by revealing differences. And what's the third approach? Masking sounds quite intriguing. Mask PCR.
Yes, mask PCR section 3.3 uses a distinct strategy to achieve lower database leakage than baseline PCR.
Theorem 4, right? What are its specs?
Theorem 4 confirms it has lower database leakage than baseline. Its communication cost is 2D plus M, same as baseline PCR. And crucially, it operates with the same finite field size as baseline, QR2D. It notably doesn't require a larger field like diff PCR does.
Interesting. Same cost and field size as baseline, but lower leakage.
Yeah.
How does it achieve that? What's the mechanism? EQ27.
The ingenious mechanism of mask PCR involves the servers adding a secret, uniformly random variable, the mask, to each of the distance calculations before applying the n-scaling and z's noise.
Wait, adding the mask before the other stuff, how does that work?
Let's look at the server's answer x(n)i in equation 27. It's defined as EQXN2 plus INI plus INZ.
So the server calculates the distance to the padded query, adds the mask, and then adds the usual unz noise.
Exactly. Now remember, EQXN2 expanded to dx plus INI plus INI plus ONCZ2. So across an IXN becomes dx plus INI plus IN2Z plus INI plus INZD. Let's regroup this slightly. AXNI plus INI plus ZI plus ON2Z2.
Okay, so the structure is again constant plus on interference plus on into noise. The constant term is now dix plus INA.
Exactly. When the user receives x1i and x2i, they subtract the known onto z2 term and then use the inverse Vandermonde matrix v21, just like in baseline PCR.
And what do they recover? EQ28.
They perfectly recover the masked distance dific plus every sample I.
Okay, they get the distance plus a random mask. How can they possibly find the minimum actual distance die if it's hidden by this random mask?
This is the clever part. The mask isn't just any random number. It's chosen very specifically. IA is uniformly chosen from the range 0, Nademan 1, where dmin is a carefully selected value.
Dmin, what does that represent?
Theoretically, dmin is defined based on the minimum difference between distances among rejected samples, those not in the database D. It relies on an assumption, lemma 1, appendix A, pot 2, that the user's sample X belongs to a set DC, a closure of rejected samples. This assumption ensures that the difference between the distance to the true closest counterfactual DX and any other counterfactual DX is at least dmin.
Okay, so dx, dmin for all I. The closest one is separated by at least dm.
Exactly. And since the mask is always less than dmin, it's in 0 dmin 1, adding the mask cannot change the ordering.
because the gap between the best and the next best is bigger than any possible mask value.
Precisely. Even though the user receives the masked distances dx plus I, the sample which had the minimum original distance dx will still have the minimum mask distance dm plus x. The relative ordering is perfectly preserved.
So the user just finds the minimum among the dx plus d sample values they recover, and that index is the correct out.
That's the core idea. In practice, remark 3, determining d-min rigorously based on the DC assumption can be hard, so it's often determined empirically from the database D itself, perhaps as the minimum difference between distances observed in the data, maybe with a safety margin. Remark 2 notes that calculating d-min is a one-time pre-processing step for the institution.
Can you walk us through that illustrative example again, the one with x equals 1, 2t? How does masking work there?
Sure. Let's say x was 1, 2t. The database has two accepted samples, y1 equals 20, 0t, and y2 equals 0, 20t. We calculate the squared of two distances, d1x, y1 by 2 equals 19, and minus 22 plus y-2, 2 plus 3 nas 1, 182, plus 182, plus 182 plus 1 plus 324, x2 is 25.
Okay, D1 365, D2 equals 325. So Y2 is the true closest counterfactual. The difference is 365, 325 was 40.
Right. Now let's say we choose d-min equals 40. The masks 1 and 2 will be chosen randomly from 0.39.
Okay.
The user receives the mask distances d1x plus 1 and d2x plus 2. Let's consider the worst case for preserving the order. What if 1 is the smallest possible value and 2 is the largest possible value, 39?
Then the user sees 365 plus 0 leaves 365 for sample 1, and 325 plus 39 equals 364 for sample 2.
Exactly. Even in this extreme case, 364, 365, the masked distance for sample 2 is still smaller. The user correctly identifies 2. The masked successfully hid the true values, 365, 325, but preserved the crucial ordering.
That's really neat. What about the cost for mask PCR?
Costs are the same as baseline PCR. Upload Tekken, download 2M, total 2D plus 2M. Computation is also similar. The only extra bit is the one-time d-min calculation.
Okay, so we have baseline, diff PCR, lower leakage, bigger field, and mask PCR, lower leakage, same field size as baseline, relies on d-min. How do we formally compare the database leakage of diff and mask to baseline?
Right. Section 3.4 gives the formal comparison using mutual information IYM.
Baseline leak.
For baseline PCR, the user perfectly recovers the vector at all distances, dmx, evo d1x, dmx, so the leakage is IYM, dmxx. Knowing all the distances reveals significant information about the database YM relative to the user's S.
And diff PCR, Kikyo 36.
For diff PCR, the user recovers the vector of differences, m1x, nu1x, d2x, dm-1x, dmx. The leakage is IYM, m1xx. Since the differences are derived from the distances, by the data processing inequality in information theory, processing data, taking differences, cannot increase information. Therefore, IYM 1x, IYM DMX x. Diff PCR leakage is provably less than or equal to baseline leakage.
Okay, the math confirms the intuition about differences leaking less. What about mask PCR, EQ 3741?
For mask PCR, the user recovers the vector of mask distances dmx plus m, where m is the vector of random masks. The leakage is IYM dmx plus mx. The rigorous derivation using properties of entropy and mutual information, particularly how adding independent noise increases entropy, shows that this leakage is also less than or equal to the baseline leakage. IYM dmx plus mx, IYM dmx. The random mask schema adds uncertainty, reducing the information revealed about the original distances dmx and less about ym.
So both diff PCR and mask PCR are formally proven to leak less database information than baseline PCR. Can we compare diff PCR and mask PCR leakage analytically? Remark 4.
That's tough. Remark 4 points out that it's difficult to analytically compare the leakage of diff PCR and mask PCR. The leakage of mask PCR depends heavily on the chosen daemon, which in turn depends on the specific distribution of the database D and potentially the user's query X. Because of this dependency, a direct analytical comparison isn't straightforward.
So we need experiments for that comparison.
Exactly. That's why the numerical experiments in Section 6 are crucial for seeing how they stack up against each other in practice.
Okay, this is where we get even more practical. We often can't change fundamental attributes about ourselves, like our exact age or perhaps our highest degree achieved. How do these privacy-preserving schemes handle that immutability constraint? It's one thing to offer a counterfactual, another for it to be useful in the real world.
This immutability constraint is indeed crucial for real-world actionability. You, the user, need to be able to define a subset I of your features that simply cannot be altered in the counterfactual suggestion.
My non-negotiables.
Exactly. And just as importantly, this immutable set I must itself remain completely private from the institution. The institution shouldn't know which specific attributes you consider immutable.
Right. Protecting I is also part of user privacy.
It is. This adds a significant layer of complexity to the privacy problem, necessitating more servers. For these IPCR schemes, immutable PCR, the number of replicated servers N typically increases from 2 to 3.
Why 3 servers now? Remark 6 touches on this.
Yes, Remark 6 mentions this. Essentially, we need to resolve an additional dimension of privacy hiding the set I itself. The mathematics of linearly separating the desired information from the noise requires solving a system of equations, and adding this extra private variable I increases the number of unknowns, requiring an extra equation, and thus an extra server's response, to solve it uniquely using the Vandermonde approach.
Okay, so N3 for IPCR. The goal is still to find the closest U, but only among those where the immutable parts match.
Correct. Find high argumentier dxi where I high, while keeping x and I private from the servers and minimizing database leakage. IYM answers x, I.
It sounds like a multi-stage operation for these complex scenarios. Tell us about the two-phase IPCR scheme, section 4.1, starting with its first phase.
Right. The two-phase IPCR scheme is indeed a multi-stage approach, detailed in section 4.1. Theorem 5 gives its specs. It uses N3 servers. The communication cost is higher, around 90 plus M symbols in total worst case. And the field size requirement is QR2D, similar to baseline PCR.
Okay, N3, higher comms cost. What happens in phase 1?
Phase 1. Finding eligible samples. The primary goal of this initial phase is for you, the user, to privately identify which samples I in the institution's database D belong to the set, meaning their immutable features, YI, match your own AI.
How do you do that privately?
Okay, first the user creates a binary vector H1 of dimension DH1K, I if feature K is immutable, i.e. Ki, and H1K is 0 if feature K is mutable, Ki. This H1 vector encodes your private immutable set I.
Got it. H1 marks the immutable features.
Then the user generates 2 d-dimensional random vectors, Z1 and Z2, as one-time pads. They construct a query tuple QXN for each server N1, 2, 3. This query, QR42, has 2 components, H1 plus NZ1, xarray H1 plus NZ2.
Whoa, okay, H1 padded with Z1. The second part is xarray H1. What's the circle E?
Denotes the element-wise product, Hadamard product. So H1 creates a vector where only the components of X corresponding to immutable features where H1K1 are kept and the others become 0. This is then padded with Z2.
Okay, so the query contains padded versions of the immutable indicator H1 and the immutable feature values HI, sent to N is 3 servers.
Correct. The NEN are again distinct non-zero elements from FQ, like 1, 2, 3. Now, what do the servers compute? EQ 45, 47.
Let's complicate it. XEN.
It is. For each sample, ye server N computes XA, H1 plus NZ1, ye X, X0 H1 plus NZ22 plus some other noise terms involving N, and another shared random vector Z. Here, row I is a random non-zero element from FQ, unique to each sample I but known to the user. It adds another layer of masking.
Okay. A masked squared distance involving the padded H1 and XCA H1. How does the user decode this?
The user gets XI1I, XASI2I, XASI3I. Because the expression inside the norm after expansion turns out to be a quadratic in ein, similar to before but more complex, the user can use the inverse of the 3x3 Vandermonde matrix V31 to decode.
And what do they get after decoding? AQ49.
After canceling noise terms and dividing by the known I, the user recovers the value H1I, U by 2 for each I.
H1I, you know, too. Let's think about that. H1 is 0 for mutable features. H1 is 1 for immutable features. So H1I is a vector that has echo xk if k is mutable and 0 if k is mutable.
Exactly. So H1I of E by 2 is the squared Euclidean distance between E and X, calculated only over the immutable features.
Ah, so what does this value tell the user?
Here's the key. If the immutable features match, yi by I, then yi xk will be 0 for all immutable k. In this case, h1i will be the 0 vector, and the decoded value h1 no will be exactly 0.
And if they don't match, if ui...
Then, at least one immutable feature k will have yanga xk 0. The vector h1 erx will be non-zero, and the decoded squared norm h1u will be non-zero.
So by checking if the decoded value is 0 or non-zero, the user learns exactly which samples I are in the set, those with matching immutable features.
Precisely. And crucially, because the non-zero values depend only on the squared difference and are masked by Rai during the process, the user only learns if there's a match. Value is 0, not which immutable features matched or mismatched, or the extent of any mismatch. Privacy of I is preserved.
Brilliant. So phase 1 identifies the set of eligible samples. What if I is empty?
If I is empty, no samples match immutable features, or has only one element, only one match found, the process stops. The user either has no counterfactual or has found the only possible one.
Okay. Assuming it has multiple samples, we proceed to phase 2.
Yes. Phase 2, finding a high, closest match within a UTE 50 to 59. Now that you know the indices I that belong to I, you need to find the one among them that has the minimum overall H2 distance dxi to your original input x, all without revealing the set to the servers.
How is that done?
First, the user creates a new binary vector H2 of size mh2i equals 1 if I and x, the indices found in phase 1, and h2i equals 0 otherwise. This H2 vector privately encodes the eligible set.
Okay, H2 marks the eligible sample.
The user then generates two more random vectors, z3 size m and z4 size d. They send a new query qxmn to each server n123. This query eq50 is h2 plus nz3 x plus nz4.
Padded H2 and padded X sent to the N3 servers again. What do servers do now?
The servers use this query to effectively mask the database samples EI that are not in it. Server N uses the first part of the query QXMN1, which is related to H2, to construct a diagonal matrix sen diag QXMN1 EQ53 through 54. They then compute an answer vector AXMN whose ith component EQ.55 57 involves terms like diag QXMN1 UQXMN2 plus noise.
This looks even more complex. What does the user recover after decoding with V31, EQ59?
After decoding, the user recovers the value H2I by 2 for each I.
H2II by 2. Let's analyze this. If sample I is eligible, I is H2I but 1, the value is 1I by 2 equals U by 2 equals dix.
Correct. They recover the actual squared E2 distance for the eligible samples.
And if sample I is not eligible, then H2I is 0. The value is 0I by 2 equals nil by 2 else by 2.
Exactly. For ineligible samples, the user just recovers the squared norm of their own input x, which is a constant value they already know, and reveals nothing new about those ineligible yi.
So the user gets the true distances die, only for the relevant samples in E, and a constant junk value for all others. Then they just find the minimum among the meaningful distances to get I.
That's the two-phase IPCR scheme. It works, guarantees privacy for X and I.
What about the cost again?
Costs. Phase 1 communication is roughly 6pen plus 3m. Phase 2 communication is roughly 30 plus 6m. Total communication in the worst case is 9D plus 9M symbols. Computation is also higher due to the two phases and N-3 servers.
Remark 5 mentions an alternative.
Yes. Remark 5 briefly notes an alternative scheme using N4 servers that might reduce communication cost if the dimension D is much larger than the database size M, but the main focus is the N13 scheme.
Okay, two phases sound quite complicated and the communication cost is high. Can they streamline this and do it all in one go?
Yes, there's a single-phase IPCR scheme, section 4.2, that streamlines the process into one interaction.
One round of query response. That sounds better. What's theorem 6 say?
Theorem 6 confirms it works with N3 servers. The communication cost is lower. 6 spam plus 3M symbols total, 60 upload, 3M download. That's significantly less than two phases 9D plus 9M.
Lower comms cost, still N3. What's the catch? There's always a catch.
The catch is the finite field size Q. It requires a much, much larger Q. Specifically, Q must be greater than FL1 R2 plus R2D.
Whoa, what are F and L?
F is the maximum possible number of immutable features the user might specify, so FAD, and L is a large scaling factor chosen by the user. This L needs to be greater than the maximum possible mutable distance R2D.
LR2P. Okay, so a very large L and Q depends on LFR2. That could be a huge field size requirement.
It definitely can be. That's the trade-off. Simpler interaction, lower communication, but potentially much higher computational demand due to the very large field arithmetic.
So how does this single-phase scheme work? What's the idea? EQ60.
The core idea here is ingenious. The user defines a single vector H of dimension D. For features K that are immutable, KI, the user sets HK equal L, that big scaling factor. For features K that are mutable, KII, the user sets HK equal 1.
Okay, H encodes both immutability L and mutability 1.
Right. This vector H combines the roles of H1 and implicitly handles the filtering of using the magnitude of L.
How? Let's see the query. EQ61, 62.
The user generates two random vectors, Z1, Z2. The query sent to server N123 is QXN plus NZ1H plus NZ2.
Padded X and padded H sent to any three servers. What do the servers compute? EQ63, 66. Each server N computes an answer X and I for each sample E. The calculation EQ63 is roughly EQXN1 T EEXN1 plus noise terms involving N and Z. It looks like a weighted inner product.
Okay, that's complex again. What does the user recover after decoding with V31, EQ67, 69?
After decoding and canceling noise, the user recovers the value EXT, EIX for each sample I.
EXT, EX, let's try to understand this term. It's a sum over features K of
xk, xk,
Yeah.
exactly, which simplifies to the sum over k of yi xk, k.
CHK. Okay, now let's consider the value of HK.
Case 1. If sample I is eligible, I chime, meaning UIXI, then for immutable features ki, the difference YKXK is 0. For mutable features ki, the difference is YAXK and HK1.
So the sum becomes just the sum over mutable features k of EXK21. That's the squared R2 distance calculated only over the mutable features. Let's call this DMX.
Almost. It's actually the full distance dxyix by, because if k is immutable and I is in xa0, so YKXK 0 LLLEO. If k is mutable HK1, so we get YK21. Summing over all k gives the total squared distance dx.
Ah, right. If I had the decoded value is exactly dx. What's the range of this value? It's between 0 and R2ds. Let's adjust that slightly. The distance is only over the di mutable dimensions, right? Now, the L term is zeroed out, so yes, it should be dx. The paper says 0 no dir2. Let me reread EQ68.
Let's recheck EQ68 and 69. If I, then YXA 0 for ki. The sum is YK, XK, xk. Since HK1 for ki, this is EKXK, this is the squared distance over only the mutable dimensions. Its maximum value is indeed dir2. Let's call this DMX, yay.
Okay, so if I EKI, the user recovers DMX, the distance over mutable dimensions, which is in the range 0 no. What happens if I X?
Case 2. If sample I is not eligible, meaning at least one immutable feature ki has UKXK, remember for these immutable k, HK, XK...
So the sum xk2hk will now have terms like yik2l.
Exactly. Since L was chosen to be very large, LR2D, this L factor dominates. The recovered value will be at least L if only one immutable feature mismatches by the smallest amount, and can go up to ILR2 plus DIR2 if all immutable features mismatch maximally plus the mutable distance. Crucially, this range starts at L.
And since L dir2 as LR2t, the range for ineligible samples L is completely disjoint from the range for eligible samples 0 dir2.
Precisely. The user can clearly distinguish between valid counterfactuals, those in the lower range, and invalid ones, those in the higher range starting at L. And among the valid ones, they see the distances DMXA over the mutable dimensions, allowing them to find the minimum.
But wait, they need to minimize the overall distance dx, not just DMX. Does this still work?
Ah, good catch. Let's re-examine the derivation or intent. If I arrays the immutable parts match, so DMX, Vero2 plus DIX2, DMX EAA, yes, it works out. For eligible samples, the distance over mutable features is the total distance.
Phew. Okay, so single phase works, gives the right distances for eligible samples, distinguishes them from ineligible ones. What about costs?
Costs. Upload 2-day plus tekken equals 4. No, the query is x plus z1, h plus z2, so d plus d. 2 components of size D, sent to any 3 servers. Upload 3 seconds is 6 pence. Download is 3M. Total 6 pence plus 3M. Lower communication than 2-phase.
Okay, single phase. Lower communication, simpler flow, but needs a much larger field queue, 2-phase. Higher communication, more complex flow, but smaller field queue. Which one is more private for the institution regarding database leakage? Section 4.3.
This is analyzed in Section 4.3. When we compare database leakage IYM answers XI, the 2-phase scheme generally offers lower database leakage than the single-phase scheme.
Why is that? Don't both eventually tell the user which samples are in X?
Yes, there's a common component of leakage for both. EQ 7376, the user must learn which samples I belong to. Let EM be a binary vector where EI1 if I know otherwise. Both schemes inevitably reveal EM. The leakage includes HEMXI.
Okay, learning is unavoidable leakage in both. What's the difference then?
The difference lies in what additional information is leaked about the samples outside.
How does 2-phase handle samples II, O Fure 102, 105, and appendix?
The 2-phase advantage, EQ 102 shows leakage calculation, stems from its sequential nature. In phase 1, you learn EM. For samples, no further information about you is leaked in phase 1 beyond the fact that they don't match OAGI. In phase 2, the scheme is designed so that for IA, the user only recovers the constant by 2, which tells them nothing more about IA.
So for not matching samples, 2-phase reveals almost nothing beyond they didn't match.
Exactly. Now consider the single-phase disadvantage. The user observes the value, ESXT, ESA for all IM, even those AIR.
Right, they get values in that high range starting from L.
Even though these values distinguish eligible from ineligible, they still contain some information about the ineligible YI. If an immutable feature K doesn't match, the value is roughly XA, XK, 2L plus other terms. If 2 immutable features mismatch, the value is roughly L plus L. The magnitude of the value in the high range can potentially reveal how many immutable features mismatch for each LA.
Ah, so single-phase leaks information about the degree of mismatch for ineligible samples, whereas two-phase leaks almost nothing about them after phase 1.
Precisely. Knowing how many features mismatch is more leakage about Y, even if I A, than simply knowing it didn't match, which is all two-phase reveals about those samples. Therefore, two-phase offers lower database leakage.
Okay, this is where the schemes get even more sophisticated and incredibly useful for you, the listener. What if I, as the user, prefer to change my income over, say, my education level? Even if my education attribute is technically closer to an accepted counterfactual, using the standard @2 distance, can the system incorporate my personal actionability preferences while still maintaining privacy?
This is a fantastic and highly practical feature directly addressed by the paper in Section 5. The schemes can indeed incorporate your personal preference on transforming your attributes by using a weighted distance metric. This allows for far more actionable and personalized counterfactual explanations.
Weighted distance. How does that work? EQ77.
The concept is introduced with a modified way of calculating distance. Instead of just the raw Euclidean distance yx2 equals yxk2, we use a weighted version, defined in EQ77 as dxy, yxt, yx.
Okay, that's WIKSK2. What's W?
W is a private weight vector generated by you, the user. Critically, this vector W must remain private from the institution. Each component WK corresponds to feature K. These weights are positive, say WKSL1, where L1 is the maximum weight value.
And how do the weights reflect preference?
A higher weight WK means you are more reluctant to change feature K. If you assign a large WK to education, then counterfactuals requiring changes to education will incur a larger penalty in the weighted distance, making them less likely to be chosen as the closest.
So you weight the features you don't want to change more heavily. Makes sense. The challenge is keeping W private.
Exactly. Keeping W private adds another layer, just like keeping I private did.
So now we move to PCR plus schemes, section 5.1, which add these personal weights W into the mix, initially without the immutable feature constraint. What's the impact? Theorem 7.
Theorem 7 confirms these schemes work. A key consequence of adding your private weight vector W is that these schemes now require N3 servers, up from N2 for the standard PCR schemes. Baseline, diff, mask.
Again, N3 because we added another private input W.
Precisely. We need that third server to mathematically resolve the additional dimension of privacy needed to successfully hide your private weight vector using the Vandermonde approach.
Okay, let's look at baseline PCR plus first. EQ 7884. How does it work?
It builds on the NW3 IPCR logic. The minimum required size of the finite field Q increases now because the weighted distance can be larger. It needs QR2 L1D. L1 is the max weight.
Okay, field size depends on max weight. Now, what's the query?
You, the user, now send a query QXN to each of the N-layer servers, NUS1, 2, 3. This query, EQ78, contains two d-dimensional one-time padded vectors, QXN equals X plus NZ1, W plus NZ2.
Padded data X and padded weights W sent to any three servers.
Right. Z1 and Z2 are your random pads, are distinct non-zero elements like 1, 2, 3. This ensures both X and W remain perfectly private.
What do the servers compute? AXNI, EQ82.
The server's calculations become more intricate. AXNI involves terms like EQXN1 key, EQXN1, QXN2, plus noise. Notice this structure is similar to the single-phase IPCR calculation.
Using the padded weight vector QSN2 and the element-wise product.
Exactly. When you expand this, the resulting expression turns out to be a polynomial of degree 3 in honor.
Degree 3, why 3?
It comes from terms involving products like UNZ1 times NZ2. This UN2 term gets multiplied by another UN from the expansion, so the dependence goes up to UND.
Okay, cubic and UN, so the user needs n weight. Theorem 7 says n3. How can you decode a cubic polynomial with only 3 points? You need 4 points and 4 for cubic.
Right. You are absolutely right to question that. A cubic polynomial has 4 coefficients: constant, linear, quadratic, cubic. To solve for them uniquely using a Vandermonde system, you generally need 4 equations, hence n to 4 servers. Let me double-check the paper's claim for baseline PCR plus in Theorem 7 and EQ84.
Yeah, please do. EQ84 says decode using V3 inverse.
Okay, apologies. Let's trace the derivation in EQ82 carefully. I see the subtlety. While the intermediate server calculation might look like it could go up to degree 3, The specific structure they use and decode ensures that the user only needs to recover the coefficients up to UN2. The term they ultimately recover is the weighted distance, DIIX. It seems the higher order terms either cancel out or are combined into the interference terms in a way that N3 is sufficient. My earlier statement about degree 3 might have been based on a general intuition rather than the specific final equation. The paper explicitly states N3 is sufficient here.
Okay. Trusting the paper's derivation that N3 works for baseline PCR plus array, they use V31 and recover the weighted distance DIX for all I.
Correct. They recover like EK, XK, 2WK for each I and find the minimum.
What about communication cost?
Communication. Upload is 3 SECs 6 pence. Download is 3M. Total 6 pin plus 3M. Similar to single-phase IPCR.
Okay. And how are diff PCR plus and mass PCR plus extended, EQ 8591?
Diff PCR plus EQ 8588 extends this logic naturally. It also requires N3 servers. Servers compute and return differences of weighted distances dyx dy plus 1x. This now requires a larger field size Q2R2L1D to handle the range of weighted differences. User decodes the differences using V31 and uses the comparison algorithm.
And mass PCR plus Q 8991.
Mass PCR Plus also uses N3 servers and the field size QR2L1D, same as baseline PCR Plus. Servers add a secret random mask to the weighted distances DIX before noise and decoding. Lemma 2, Appendix A.3, proves that the required masking range daemon remains the same as the unweighted case, ensuring the mask preserves the relative ordering of weighted distances. User decodes the masked weighted distances DIX plus A using V31 and finds the minimum.
Okay, so PCR plus adds weights W, requires N equal 3, and has variations for baseline, diff, and mask. Now, what if you have both immutability I and user actionability W? This sounds like the ultimate private counterfactual explanation, Section 5.2. This is indeed the most complex and arguably most practical scenario covered in Section 5.2, IPCR plus schemes. Here, both the immutable set I and the mutable feature preference weights were private user inputs. How is the weight vector W handled here? EQ92.
Your private weight vector W, now dimension D, needs a slight modification. For features K you've designated as immutable, KAI, their corresponding weight WK is set to 1 or effectively ignored as they aren't meant to change. For your mutable features, KM, where M is the complement of I, you assign your personal preference weights WK-L1. So W combines W through for mutable parts and 1 for immutable parts.
Okay, the goal is to find the sample in I matching immutable feature that minimizes the weighted distance DXII TIA. How does two-phase IPCR plus work, EQ 93 to 98?
It extends the two-phase IPCR scheme. Phase 1 remains entirely unchanged from the standard two-phase IPCR. It only uses H1, based on I, and X to privately identify the set of eligible samples. It doesn't need the weights W yet, so it still uses Enclave servers for Phase 1.
Okay, Phase 1 finds A's of before. What about Phase 2?
Phase 2 is extended to incorporate the weights W. The user still creates the binary vector H2 marking the samples in A, but now the user sends 3 one-time padded vectors in the query QXMN, EQ93, H2 plus NZ3, X plus NZ4, W plus NZ5.
Padded H2, padded X, and padded W, 3 components.
That's right. Sent to the servers, the server answer XMNI, EQ9596, now involves calculations combining all 3 parts, similar to the PCR plus schemes. The resulting expression after expansion becomes a polynomial of degree 3 NI.
Degree 3 again. And this time it seems unavoidable, so.
So, as stated in Theorem 8 and EQ97, Phase 2 now requires Engel 4 servers. The user needs answers from 4 servers to apply the inverse of the 4x4 Vandermonde matrix V41 and uniquely decode the coefficients of the cubic polynomial.
Okay, N4 for Phase 2, what does the user recover?
After decoding with V41, the user recovers the value H2IXTXTAT for each I.
Let's analyze that. If I AH H2I1, the value is YXT which is exactly the weighted distance DXGO.
Correct.
If I MHQ0XJ2W, this is a constant based only on the user's X and W.
Exactly. So again, the user gets the true weighted distances for eligible samples in A and a constant junk value for ineligible ones. They find the minimum weighted distance among the eligible ones to get AI.
So two-phase IPCR plus Phase 1 uses N3 to find A. Phase 2 uses N4 to find the best weighted distance with N. What are the costs?
Costs. Communication is higher due to Phase 2 using N4 servers and 3 query components. The paper estimates total communication as 14 plus 11 M symbols. Quite high.
Very high. What about single-phase IPCR plus A? Can it avoid N4 EQN99?
Yes. This scheme very elegantly integrates actionability W with immutability I into the single-phase approach. It modifies that single vector H from single-phase IPCR.
How is H defined now?
HK, L, the large scaling factor, for immutable features KA, and HK, the BUK, the user's preference weight, for mutable features KAI. L now needs to be even larger, L1 R2D, where L1 is max weight, to ensure separation from weighted mutable distances.
So H encodes immutability with L and actionability with W weights.
Precisely. The query is still QXNI equals X plus NZ1, H plus NZ2. The server calculation XNI is the same form, YI QXN1, T YI QXN1 plus noise.
And crucially,
The paper states, remark 7, this scheme still works with N3 servers. The decoded value is still YXT, YX, AH.
let's reevaluate that decoded value. XKXK.
If the AKI is mutable match, then for KI the term is 0. For KAXK, the sum becomes NYAK. This is exactly the weighted distance DXI.
Yes, because WK1 for immutable K doesn't contribute anyway. So for eligible I, they recover the true weighted distance. What about I?
If I say at least one immutable K mismatches, the sum will contain terms like Yaya K2L. Since L is huge, L1 R2D, this term dominates, pushing the value into a high range separate from the weighted distance range 01 R2P.
So it still distinguishes eligible weighted distances from ineligible high L values using only N3 servers.
Exactly. Single-phase IPCR Plus keeps N3 and total communications 6P plus 3M.
What's the trade-off then? Remark 7 spells it out.
The trade-off for Remark 7 is a much higher field size requirement Q. Now, Q needs to be greater than FL1R2 plus R2L1T. Since L itself is already large, L1R2P, this Q can become astronomically large, potentially posing significant computational challenges.
So key trade-off again. Single-phase IPCR Plus uses fewer servers, 3 versus 4, and less communication than two-phase IPCR Plus PIA, but demands a vastly larger finite field Q. Theory and mathematical elegance are great, but how do these ingenious schemes perform when put to the test in the messy, imperfect real world? The paper includes numerical results in section 6, right?
Excellent question. Yes, the researchers conducted extensive numerical experiments to evaluate two critical aspects. First, the accuracy of the retrieved counterfactuals, especially considering that real-world data is often continuous and needs to be converted into integers for the finite field arithmetic.
Right, the quantization issue.
And second, and perhaps most importantly, the actual quantifiable database leakage achieved by the different schemes in practice.
Okay, let's first talk about accuracy and the quantization trade-off in PCR, section 6.1. What was the setup?
The core problem, as you said, is quantization. Real data, like income sensor readings, is often real valued, but the schemes operate with integer 0.r within a finite field FQ. So real data needs to be quantized into these integer bins. This quantization, however, can introduce a small amount of error. You lose some precision.
And there's a trade-off.
Yes, an inherent trade-off. More quantization levels, a larger R, means less information loss and thus higher accuracy in finding the counterfactual that's truly closest in the original unquantized space. But a larger range R directly necessitates a larger finite field size Q, since Q depends on R2D or similar, which typically translates to more computational resources and communication overhead.
Makes sense. More precision costs more. What about masked PCR's daemon in the experiments?
Good point. For masked PCR, the theoretical analysis had that specific assumption about the user's data X being in DC to guarantee the daemon property. In the experiments, they pragmatically lifted this restriction and determined a daemon empirically from the dataset itself. They also noted that a larger finite field Q allows for a larger daemon range, potentially offering more robust masking.
What data did they use?
They tested this using the wine quality dataset, a publicly available dataset with about 4,900 instances, 11 real valued features, like acidity, sugar levels. They converted the wine quality score into a simple accepted good quality or rejected bad quality binary classification. They then used the rejected wines as user queries X and the accepted wines as the database D of counterfactuals Y.
How did they measure accuracy, EQ100?
The accuracy metric EQ100 was straightforward. They compared the counterfactual X retrieved by their private scheme after quantization with the actual nearest neighbor YX found using the original unquantized real-valued data and standard 2 distance. Accuracy was the fraction of queries X for which eess was indeed the true nearest neighbor YX.
And the results, figure 3.
The results in figure 3 clearly showed the expected trend, as they increased R, the number of quantization levels, meaning the more precisely they represented the real value data with integers, the accuracy of the retrieved counterfactuals improved significantly, approaching 100% for larger R.
So quantization level R is key for accuracy. What about daemon's effect on masked PCR accuracy?
They also observed that for a given quantization level R, the accuracy of mask PCR degraded slightly as daemon increased. This makes intuitive sense. A larger mask, since I is up to daemon 1, adds more uncertainty or noise, making it slightly harder to distinguish the true closest distance perfectly, unless the daemon property holds perfectly.
And when daemon was small,
When daemon 1, meaning the mask is always 0, mask PCR becomes equivalent to baseline PCR, and as expected, it showed the highest accuracy for any given quantization level in that case.
okay, accuracy behaves as expected with quantization R and mask size daemon. Now let's talk about database leakage in PCR, section 6.2. This is a core privacy metric for the institution. How much data about their samples YM is leaked to the user?
Right. To measure this rigorously, they computed the mutual information, IYM XNX, which quantifies how much information about the institution's database YM is revealed by the answers AXN the user receives, given the user's own input X. Calculating this precisely is computationally hard, so they use methods detailed in Appendix A.4, likely involving sampling or approximations.
Did they test on a simple case first? Table 2.
Yes, they first tested this on a synthetic dataset, a very simplified setup with R4, dimension D2, and only M5 database samples. The results in Table 2 were very clear and numerically confirmed the theory. Baseline PCR had the highest leakage value, around 3.13 bits. Diff PCR significantly reduced this leakage, around 2.04 bits. Mask PCR achieved the lowest leakage, around 0.91 bits for daemon 2, and even lower at 0.78 bits for daemon 3.
So the synthetic test clearly shows baseline diff mask in terms of leakage.
Exactly. It numerically confirmed that diff PCR and mask PCR indeed reduced the amount of information leaked about the institution's database compared to the baseline scheme, and mask PCR can be even more private depending on its daemon configuration.
What about a real-world dataset? Table 3.
They then applied this leakage analysis to a more complex real-world dataset, COMPAS. This dataset is used in some U.S. jurisdictions to predict criminal recidivism likelihood, so privacy is extremely important. It had about 6,200 instances and 20 features after preprocessing, quantized to R10. Due to the immense computational complexity on this larger dataset, they definitely had to use sampling techniques for the mutual information estimation.
And the results on COMPAS, did the trend hold?
Yes, the results in Table 3 showed a very similar relative trend, even with this more intricate data. Baseline PCR still had the highest estimated leakage, around 1.5144 bits. Diff PCR was slightly lower, around 1.51436 bits, a very small difference here. And mask PCR had the lowest leakage, around 1.51427 bits.
So the differences are much smaller on the real data, but the relative ordering still holds. Baseline new diff your mask.
Correct. This demonstrates the practical effectiveness of the schemes in reducing database leakage, even with the complexities and noise inherent in real-world data, although the absolute gains might be smaller than in idealized synthetic settings.
And what about the leakage? When we factor in immutable features with the IPCR schemes, section 6.3, does the two-phase approach truly leak less than the single phase, as we hypothesized from the theory?
That's exactly what their final numerical experiment investigated. Database leakage in IPCR, they computed leakage for both two-phase and single-phase IPCR schemes using another synthetic dataset with R3, D3, M3 this time.
How do they calculate leakage for these?
For single-phase IPCR, the leakage is IYM VXI, where V is the vector of decoded values, EKYXA for all I, EQ101. For two-phase IPCR, the leakage calculation reflects the two stages. EQ102, it's essentially HEMXI, the leakage from learning the eligibility set in phase 1, plus IYM, XM, and XIEM, the additional leakage from phase 2 conditioned on knowing.
Okay. What did the results show?
The results in Table 4 are compelling and strongly support the theoretical analysis we discussed earlier. Two-phase IPCR consistently showed lower database leakage than single-phase IPCR for all tested numbers of immutable features I.
So the experiments confirm two-phase is better for database privacy.
Yes. This supports the theory that knowing only EM, which samples match, plus the distances for those matching samples two-phase, leaks less information overall than knowing values related to the degree of mismatch for all samples, single-phase.
Did they notice any other trends in Table 4?
Yes, a couple of interesting points. For single-phase, the leakage was roughly symmetrical. Leakage was similar when immutable features were chosen versus when immutable features were chosen.
Great.
But for two-phase, the leakage decreased as the number of immutable features increased.
Leakage went down as more features became immutable. Why?
Because a larger immutable set, the set of eligible counterfactuals, is expected to be smaller. If A is smaller, Then phase 1 reveals less information, less uncertainty in EM. And phase 2 operates on a smaller subset of YM, thus leaking less additional information.
That makes sense. What about the extreme case where all features are immutable?
The IID case is particularly insightful. If the user's X is rejected and all features are immutable, I equals I with D, then must be empty. There's no Y in the database D that perfectly matches X and is accepted.
Right. What did the leakage results show then?
For two-phase IPCR, the leakage was measured as 0. This makes perfect sense. Phase 1 correctly determines that A is empty, EM is all zeros. Since A is empty, phase 2 is skipped entirely. No further information about YM is revealed beyond the fact that none of them match X.
Okay, 0 leakage for two-phase when no counterfactual exists? What about single-phase?
For single-phase IPCR, the leakage was non-zero, even when it was effectively empty. Why? Because the user still receives and processes those masked TYX values for all M samples. Even though all these values fall into the high ineligible range, they still reveal some information about the database. For example, how many immutable features mismatched for each EI, even if the final outcome is that no counterfactual exists.
So single-phase leaks info even when telling you there's no solution, while two-phase leaks nothing in that case. That's a clear privacy advantage for two-phase again.
Absolutely. The numerical results really highlight these subtle but important differences in privacy characteristics between the schemes. Hashtag tag check outro.
Wow, we've truly gone on a deep dive today into private counterfactual retrieval. We started by grounding ourselves in the crucial need for transparency and explanations in AI.
Yeah, especially when those powerful black box models make high-stakes decisions that impact your life.
Exactly. Then we tackled the often underexplored but immensely important challenge of user privacy, ensuring that your personal data remains perfectly hidden even as you seek actionable insights from an AI system.
Indeed. We navigated through some pretty ingenious mathematical constructions, didn't we? From the power of Vandermonde matrices acting as our secret decoder rings, to the elegant simplicity and profound guarantees of Shannon's one-time pad. These are really the underlying mathematical bedrock for achieving those robust information-theoretic privacy guarantees.
And we explored multiple schemes for different privacy appetites. The baseline PCR, which established perfect user privacy.
And then the diff PCR and mask PCR, which specifically focused on reducing the amount of information leaked about the institution's database, offering more privacy for them.
And we didn't stop there. We added the real-world complexity of immutable features, those attributes about yourself you simply cannot change.
Right, the IPCR schemes.
And saw how IPCR schemes, both the two-phase and the single-phase approaches, tackled this while maintaining privacy, though with different trade-offs.
And finally, we saw how your personal preferences for changing attributes, what they call user actionability, can be seamlessly incorporated into these schemes, the PCR Plus and IPCR Plus versions, allowing for truly personalized and private counterfactuals.
So boiling it down, what are the key takeaways for you?
Well, I think the key takeaways from this entire journey are pretty clear. First, counterfactual explanations are incredibly powerful tools for understanding and meaningfully interacting with AI decisions. They're not just nice-to-haves.
Definitely.
Second, user privacy is not just an add-on. It's a critical, often overlooked aspect of truly ethical and usable, explainable AI. We need to protect the person asking the question.
Couldn't agree more. Third point.
Third, information theory, particularly Shannon's one-time pad and related concepts like mutual information, provides the robust mathematical bedrock for achieving these perfect privacy guarantees. It's not just heuristics, it's provable.
Provable privacy. Love it. And finally.
And importantly, different schemes offer varying trade-offs between things like communication cost, the required size of the underlying mathematical fields, that Q value, and crucially, the database leakage.
Which means
that institutions can actually choose a scheme that aligns with their specific privacy budget and computational resources. It demonstrates that powerful AI explanations don't have to come at the cost of your personal data or even excessive leakage of their own data. There are options.
That's a great summary. This deep dive shows us something truly profound, I think. Privacy doesn't have to be an afterthought in AI design or some cumbersome add-on that compromises functionality.
Exactly. It can be built in from the ground up, woven into the very fabric of the system with elegant mathematical solutions like the ones we explored today.
So the provocative thought for our listeners. As AI becomes more and more ubiquitous in every corner of our lives, how might these rigorous information-theoretic approaches change our expectations for how all our sensitive data is handled? What steps will you take, listening now, to ensure your digital interactions prioritize privacy? Something to mull over until our next deep dive.
Indeed. Thank you for joining us on this deep dive. If this discussion sparked more questions or you want to explore more cutting-edge research, please reach out to us. Until next time, keep digging deeper. Welcome, curious minds, to the deep dive. Imagine this scenario. You've applied for something really important, maybe a bank loan or that dream job you've been eyeing, or perhaps you've received a medical diagnosis that's, well, challenging, and the answer comes back, just a flat no.
Yeah.
It's incredibly frustrating, isn't it? But what really, truly gnaws at you isn't just the rejection itself, it's the unknown. You're left sitting there wondering, okay, but what if? What was the one thing? What crucial change could I have made to turn that no into a yes? That deep desire, that need for actionable feedback, for understanding that vital what if, well, that's the very heart of what we call counterfactual explanations. Today, we're taking a really deep plunge into a fascinating and I think incredibly timely research paper. It's titled, What If, But Privately? Private Counterfactual Retrieval. Our mission for you, our dedicated listeners, to explore how these powerful machine learning models, the ones that often feel like black boxes, how they can offer transparent, useful, actionable explanations, those critical what ifs. But, and this is the kicker, how they can do it without compromising anyone's privacy. This isn't just about wading through technical jargon. It's really about uncovering the clever engineering, the smart thinking behind making AI more fair, more accountable, and ultimately more useful for you.
Exactly. And it's a really interesting space. We're going to unpack a critical and I think often overlooked problem, which is, how do you provide these incredibly valuable what-if explanations, its counterfactuals, while rigorously protecting the user's personal data, the person asking for the explanation? So we're going to dive deep into the inventive mathematical frameworks, the different schemes the researchers propose. We'll definitely discuss their inherent trade-offs, because there always are trade-offs. And then we'll look at how they actually stand up in, more realistic, real-world scenarios. So yeah, get ready for some serious aha moments, I hope. But the insights here are genuinely quite profound.
Okay, so let's unpack this right from the very beginning. Why are we even talking about counterfactual explanations in the first place? I mean, what's the big deal? Why can't a machine learning model just give us a simple yes or no? That seems like a pretty standard interaction we have all the time with technology.
Well, it's becoming a much bigger deal, legally and ethically. What's truly fascinating here, and it's becoming an increasingly important mandate in many places, is this concept often called the right to explanations. Especially when you think about high-stakes applications, things like finance, getting a loan, insurance, or even healthcare decisions. If a black box model, and by that we mean an AI system where the internal logic, the decision-making process, isn't easily understandable or transparent to us humans.
Right, you just get the output, not the why.
Exactly. If that kind of model just says no to something as critical as a loan approval or maybe suggesting a particular medical treatment path, well, that's increasingly seen as just not good enough anymore. And it's not just about, being polite or user-friendly. It's fundamentally about transparency and accountability. If an AI is making decisions that can profoundly impact your life, you, as the user, arguably have a fundamental right to understand the basis of that decision. Why did it say no?
That makes complete sense. So going back to that bank loan example, the rejection, instead of just getting that blunt denied stamp, a counterfactual explanation would offer something more concrete, something I could actually use.
Precisely. Instead of just no, a counterfactual explanation aims to give you something incredibly actionable. You might say something like, if you had increased your reported annual income by, say, $10,000, your loan application would have been approved. Or maybe if your credit utilization ratio was below 30% instead of its current level, you would have qualified. See, this kind of feedback is invaluable. It's not just an explanation of why you were rejected in the past. It's tangible, actionable advice on how you might change the outcome in the future. It really empowers the user, gives them agency.
And the paper mentions, I think, several desirable properties for these counterfactuals. It's not just about being close to your original situation, right? What else makes a good counterfactual beyond just being the nearest possible yes?
Right. Proximity is definitely key. You generally want the smallest, most manageable change possible to flip the decision from no to yes. That makes it feel achievable. But research in this whole field of explainable AI, or XAI, highlights other crucial properties too. For instance, robustness. You want an explanation that's stable. It shouldn't drastically change if the underlying AI model is tweaked just slightly.
Okay, so it's not brittle.
Exactly. Then there's feasibility. This is a big one. The recommended change has to be something a user can realistically do. Telling someone, if you were 10 years younger, you'd get the loan. Well, that's not feasible. It's not actionable advice.
Right, not helpful.
Not helpful at all. Then there's sparsity. Generally, users prefer explanations that suggest changes to as few attributes, as few features as possible. It's just easier to understand and act upon if you only need to change 1 or 2 things, not 10. And finally, you sometimes see discussion around diversity. This means providing maybe multiple different pathways, multiple different counterfactuals that could lead to a yes, giving the user options. And this specific paper, while it acknowledges all these aspects, it really focuses its technical machinery primarily on achieving proximity, finding that closest yes and ensuring the explanation is actionable, all while doing it under strict privacy constraints.
Okay, so getting an explanation sounds fantastic. I'm sold on the idea. But here's where, as you said, it gets really interesting. And this is where this paper seems to shine a light on a less explored, but honestly critical privacy concern. You mentioned most existing work, maybe the stuff cited like 13 to 19 in the paper, tends to focus on protecting the institution's side of things, like protecting their proprietary model or their big database of accepted customer samples. But what about my privacy? Me, the user, the person asking for the explanation, I'm the one who has to hand over my sensitive data, my financial details, my health info, whatever it is, just to get this what if.
You've hit the nail on the head. This raises a truly important question, one that this paper really centers itself around. Why would a user be reluctant or maybe even outright refuse to reveal their input feature vector, which is just a fancy term for their deeply personal data, to the institution, even when they're the ones asking for help, asking for an explanation? There are several good reasons. Think about it. Could be about avoiding, say, a limited number of application attempts.
Oh, right. Like if you only get 3 tries at a mortgage application or something.
Exactly. If I apply, get rejected, and then to get an explanation, I have to formally submit all my current details again. Does that count as try number 2? Does it go on some permanent record associated with me at that institution? Users might worry about that. Or, maybe more fundamentally, it could simply be about preserving your basic data privacy until you've actually had a chance to improve your situation. If I know my financial standing isn't great right now, I might not want to disclose all those details just to get advice. I might prefer to work on improving my income or credit score first and then apply, without the institution having logged my previous less than ideal state. So the core problem, the central challenge this paper tackles, is this. How can a user retrieve a counterfactual instance, that helpful what-if example, without revealing their own feature vector to the institution providing the service? And the paper makes a very strong claim. It promises to achieve perfect information-theoretic privacy for the user. That's a very high bar.
That phrase again, perfect information-theoretic privacy. It really stands out. It sounds incredibly strong, like mathematically unbreakable privacy. It almost sounds like trying to find a specific book in a huge library, but you can't tell the librarian which book you're looking for. Does this problem have roots in other, maybe more established areas of computer science or cryptography?
Absolutely. Your library analogy is actually quite fitting. This problem isn't appearing out of nowhere. It's deeply rooted in and cleverly leverages techniques from several fascinating and well-established fields. On one hand, it's clearly related to the general problem of nearest neighbor search. That's a classic problem. You have a big data set, and you want to find the data point in it that's closest to your query point. But as you rightly pointed out, adding that strict privacy constraint, not revealing your query point, makes it significantly harder.
Okay, so standard nearest neighbor search assumes you can reveal your query.
Typically, yes. So the paper skillfully borrows and adapts techniques from a field specifically dedicated to this kind of challenge. Private Information Retrieval, usually abbreviated as PIR. In a standard PIR setup, the goal is for a user to retrieve a specific message, say message number I, from a database that's replicated across several servers. And the crucial requirement is that none of those individual servers should learn which message, which index I, the user was actually interested in.
That sounds exactly like what we need for finding the counterfactual. We want the index of the closest accepted sample, but we don't want the servers to know which index we ended up wanting.
Precisely. It maps very well conceptually. And building upon the ideas of PIR, there's an even stronger notion called symmetric PIR, or SPR. In SPR, you have 2 privacy guarantees. The user still retrieves their desired message without the servers learning which one. That's the standard PIR part. But additionally, the user learns only their requested message and absolutely nothing else about the rest of the database.
So it protects the database too, in a way.
Yes, it limits what the user learns about data they didn't explicitly ask for. This paper ingeniously combines ideas from both PI and SexWire to achieve both user privacy, well, the servers learn nothing about the user's request, and also to minimize database privacy leakage. The user learns only what's necessary to find their counterfactual. The overall process, as we'll see in the schemes, often involves two conceptual steps, drawing inspiration from this peer-to-peer world. First, you need a way to privately find the index of the counterfactual. You want the index of that closest accepted sample in the database. This feels very much like a PR problem. Second, once you have that index, you need to privately retrieve the actual counterfactual sample data itself using that index, potentially without learning much else. This has MCR flavors. This two-step thinking, or variations of it, is pretty fundamental to how they construct their privacy guarantees.
Okay, so we've got the problem framed really well now. We understand the why and the what. Before we dive headfirst into the actual schemes, the clever ways they solve this, let's pause and quickly go over some of the foundational concepts and the mathematical language they use. We'll see some symbols and definitions. Don't worry, we'll break it down and make it approachable. Understanding this notation is key to unlocking how these schemes work their magic.
Absolutely. Getting comfortable with these symbols is really essential to appreciating the rigor and, frankly, the elegance of the mathematical constructions in this work. They form the vocabulary for the rest of our discussion. Okay, first up, some simple set notation. When you see a number inside square brackets, like n, it's just shorthand for the set of positive integers starting from 1 up to n. So n means 1, 2, n. If you see 5, it just means the set containing 1, 2, 3, 4, and 5.
Simple enough, like counting numbers.
Exactly. And similarly, if you see a range notation like mn, that represents the set of integers starting from m and going up to n inclusive. So 3.6 would be the set 3, 4, 5, 6. Next, vertical bars around a set name, like A, denote the cardinality of set A. That's just a formal way of saying the number of elements in that set. If your set A is red, green, blue, then A is simply 3.
Okay, the size of the set.
Correct. Now for vectors, you'll often see AT. This is standard notation for the transpose of a vector A. If you think of a vector as a column of numbers, its transpose AT is that same sequence of numbers written as a row. Basically flips the orientation.
Standard linear algebra stuff.
Okay. Now, here's a concept that's absolutely crucial for the cryptographic guarantees underpinning these schemes. The finite field, which is typically denoted as FQ. Here, Q must be a prime number, like 5, 7, 11. Or a power of a prime number, like 4, which is 22, or 8, which is 23, or 9, which is 32. Think of FQ as a special self-contained number system. It has exactly Q elements, usually represented as 0, 1, Q1. And the key thing is that all arithmetic operations, addition, subtraction, multiplication, even division, except by 0, happen modulo Q.
Right, you mentioned this earlier. Modulo Q, that's the wraparound arithmetic, like on a clock.
That's the perfect analogy. It's exactly like clock arithmetic. You perform the operation as usual, then you divide the result by Q and keep only the remainder. So if we're working in F5, the field with 5 elements, 0, 1, 2, 3, 4, if we calculate 3 plus 4, that's 7. But 7 mod 5 is 2, since 7 divided by 5 leaves a remainder of 2. So in F5, 3 plus 4 is 2. Similarly, 3, 4 equals 12. And 12 mod 5 is also 2, so 3, 4 equals 2 in F5. This wrapping around property is fundamental. It allows us to perform calculations that effectively hide information in a way that can be mathematically proven to be secure, which is essential for the privacy techniques used here.
Okay, finite fields are like closed mathematical universes where numbers wrap around. Got it.
Good. Next we have H. This represents Shannon entropy. It's a cornerstone concept from information theory. Intuitively, entropy measures the amount of uncertainty, randomness, or surprise associated with a random variable. A variable with high entropy is very unpredictable, like the outcome of a fair coin flip repeated many times. A variable with low entropy is more predictable.
So more entropy means more randomness, less predictability.
Exactly. And closely related to entropy is I, which denotes mutual information. Mutual information quantifies the amount of information that one random variable contains about another random variable. It measures their statistical dependency. If I, X, Y is high, it means that knowing the value of X tells you a lot about the likely value of Y and vice versa.
Yeah.
They're strongly related. If I, X, Y is 0, it means X and Y are statistically independent. Knowing X tells you absolutely nothing about Y. This concept is absolutely critical for formally defining and proving privacy guarantees. When we say something is private, we often express it mathematically by saying the mutual information between the secret thing and the observed thing is 0.
Ah, okay. So I secret observation equals 0 means the observation revealed nothing about the secret.
Precisely. That's the mathematical way to state perfect privacy in this information-theoretic sense. And one last notation point. When you see a letter in bold, italicized font, like A, that will denote a matrix, a rectangular array of numbers. just to distinguish it from regular variables or vectors. So that's our basic vocabulary for diving into the mechanics.
Great. That sets the stage nicely. And you mentioned the paper relies heavily on two specific, elegant mathematical concepts that really make these strong privacy guarantees possible. It's not just random math. These are specific tools chosen for the job.
They absolutely are. These are foundational tools from algebra and cryptography, and their properties are essential for making the schemes work and proving they are secure. The first one is the van der Waals matrix. We'll see this pop up again and again in the decoding steps. A van der Waals matrix is a special type of square matrix. It's constructed in a very specific pattern based on a set of distinct elements, usually taken from our finite field FQ. Let's say we pick n distinct non-zero elements, A1O and AK2 and NiCoQ. The van der Waals matrix V, based on these alphas, would have its entry in the ith row and j twice the column given by a j1. So the first column is all I0, which is likely 1. The second column is I1. The third is I2, and so on. The absolutely crucial property of a van der Waals matrix, as long as the I values used to build it are distinct and non-zero, is that it is always invertible.
Okay, invertible again, meaning you can always find another matrix, its inverse, that undoes its operation. If you multiply by the matrix and then by its inverse, you get back where you started.
Exactly that. It means if you have a system of linear equations where your unknown variables are multiplied by the entries of a van der Waals matrix, which is what happens when the user combines answers from multiple servers, you're guaranteed to be able to uniquely solve for those unknowns. You just multiply the vector of results by the inverse of the van der Waals matrix, V1, and boom, you recover the original unknowns. It's like having a guaranteed decoder key. This invertibility is absolutely central to how the user privately recovers the information they need, like the distances, from the encoded answers sent by the servers.
Okay, van der Waals matrix inverse invertible decoder key. What's the second foundational tool?
The second tool is arguably even more fundamental to the privacy aspect. It's Shannon's one-time pad, sometimes called the Vernam cipher. This is a classic foundational result in cryptography, proven by Claude Shannon to offer perfect secrecy. The core principle is incredibly simple but powerful. It states that if you take any secret message or data, let's call it X, which could be a number, a vector, whatever, and you combine it, usually using addition modulo Q in our finite field context, with a truly random key, Z, that is at least as long as the message and is used only once.
The one-time part of the name.
Exactly. That one-time use is critical. If you have this truly random secret key Z, the pad, and you compute the ciphertext C equals X plus Z using modulo Q arithmetic, then this ciphertext C reveals absolutely no information about the original secret message X.
So even if someone intercepts C, they learn nothing about X as long as they don't know Z, and Z was truly random and used only once.
Precisely. Mathematically, Shannon proved that the mutual information IXC is exactly 0. The ciphertext C is statistically indistinguishable from pure random noise. It's like adding an overwhelming amount of random static to your secret signal. The original signal becomes completely lost in the noise to anyone who doesn't know exactly what static was added. This is the mechanism that guarantees the perfect information-theoretic privacy for the user's data in these PCR schemes. The user's sensitive input X is masked with a one-time random pad Z before being sent to the servers. The servers only see X plus Z, which tells them nothing about X.
Wow. Okay, so van der Waals matrices for decoding and the one-time pad for perfect secrecy of the user's input. That's a powerful combination.
It really is. These two concepts used together form the bedrock of the proposed solutions.
So now we have the language and the core tools. Let's formalize the challenge again. What exactly is the user trying to achieve, and what are the precise rules of engagement in this private counterfactual retrieval, or PCR, setting?
Yeah.
Okay, let's lay out the formal setup. We have an institution, like a bank or a hospital, that has a pre-trained black box machine learning model. This model takes an input, which is a feature vector X describing a user. This vector X has D dimensions or features, like income, age, credit score, etc. Each feature is assumed to take values in some range, often mapped to integers 0.r for calculations in FQ. The model classifies X as either accepted, let's say class 1, or rejected, class 0. The user, let's call their input X, has been rejected by this model. The user wants to find a counterfactual explanation. They don't interact directly with the institution's model. Instead, the institution maintains a database. Let's call it D. This database contains M samples, Y1, Y2, Ym, all of which were previously accepted by the model. Crucially, this database D is replicated across N servers, and these servers are assumed to be non-colluding.
Meaning server 1 doesn't talk to server 2 behind the scenes to try and piece together my private information?
It's exactly. That's a standard but important assumption in many privacy-preserving protocols, including PIR. Each server operates independently based on the query it receives from the user and its copy of the database D. Now, the goal for the user, as formalized in equation 1 of the paper, is to find the index, let's call it, of the accepted sample yi in the database D that is closest to their own rejected feature vector x. So A ickies argmin im d x yi. Initially, the paper focuses on using the standard squared Euclidean distance, the AOS2 norm squared, for measuring closeness dxy, that is dxy 8xk. Finding the minimum squared distance is equivalent to finding the minimum distance.
Okay, find the index of the nearest neighbor in the accepted database D.
Correct. Now, the process flow, illustrated nicely in figure 1 of the paper, involves the user interacting with these n servers. 1. The user, based on their private input x, constructs n potentially different queries, qx1, qx2, chan. 2. The user sends query qxn to server n3. Each server n, using its database D, and the received query qxn computes an answer xn. 4. Each server n sends its answer xn back to the user. 5. The user collects all the answers x1, xn, and uses them, along with their original input x and knowledge of how the queries were constructed, to decode the desired index.
And this whole process has to adhere to some very strict constraints, which they define formally. It's not just about getting the right answer, it's about doing it privately.
Precisely. The paper lays out 3 rigorous information-theoretic definitions that any valid PCR scheme must satisfy. First, PCR decodability. This is stated formally in equation 3. It essentially says that the user must be able to determine the correct index with 0 uncertainty, given everything they know at the end of the protocol. Mathematically, h of qxn, axnx equals 0. The conditional entropy of date must be 0. The user must be able to perfectly decode the index of the closest counterfactual from their queries, the server's answers, and their own input x. No ambiguity allowed.
Okay, the user has to succeed in finding the answer. Makes sense.
Second, and absolutely paramount for this work, is PCR user privacy. This is defined in equation 4. It captures the requirement that the user's private information must be protected from each individual server. Formally, for each server n from 1 to n, the mutual information ix, qx, and d equals 0. This means that the query qxn sent to server n reveals absolutely nothing about the user's input vector x or the final desired index, even given the database d, which the server already knows. This is where the one-time pad comes in to provide that perfect information-theoretic secrecy. Each server learns nothing for the query it receives.
That's the core user privacy guarantee. What's the third constraint?
The third is PCR database leakage. This is defined in equation 5. It quantifies how much information about the institution's entire database D, containing all M-accepted samples y1 day IYM, is leaked to the user during the whole interaction. Formally, it's the mutual information I, y1, ym, qxn, axnx. How much does the user learn about the whole database D from the queries they sent and the answers they received, given their own input x, which they obviously know? While the user needs to learn something to find due, namely the distances or related information, the goal of the more advanced schemes like diff-PCR and mask-PCR is to minimize this database leakage compared to simpler approaches. It's about giving the user their answer without revealing unnecessary details about all the other samples in D.
Okay, so 3 pillars. User must get the answer, decodability. Servers learn nothing about the user privacy, and try to minimize what the user learns about the rest of the database leakage.
That's a perfect summary of the core PCR setting.
Now, you mentioned earlier this practical issue. What if I can't, or simply don't want to, change everything about myself? Things like citizenship, maybe race, maybe highest educational degree. How do the schemes handle these immutable features?
Right. This leads to the immutable Private Counterfactual Retrieval setting, or IPCR. This is a crucial extension for making the explanations truly practical and actionable. In the IPCR setting, the user specifies a subset of their features, let's call this set I for immutable, that must not change in the counterfactual explanation. The features not in I are the mutable ones, denoted by M, which can be altered. And the really clever part, the extra privacy challenge, is that the set I itself is private to the user. The institution, and therefore the servers, do not know which features the user considers immutable.
So not only is my data X private, but my constraints on X, which parts are immutable, are also private.
Exactly. That adds another layer that needs protection. So the modified goal for IPCR, equation 7, becomes finding the index I that minimizes the distance, dxi, but only among those samples E in the database D that already matched the user's input X on all the immutable features specified by I. Let B the set of indices I such that Y matches X on the immutable features, YI. The goal is I give my rush YX I. You're searching for the nearest neighbor only within this eligible subset.
And the constraints get modified too, I assume, to protect the privacy of I.
Yes, the formal definitions are updated. Equations 8, 9, 10. IPCR decodability, EQ8, means the user must be able to find EI given their input X, their private immutable set I, and the query's answers. HIQX, IN, XIN, XI equals 0. IPCR user privacy, EQ9, is even stronger now. IXI could AQXND equals 0. Each server learns nothing about the user's input X, nothing about their private immutable set I, and nothing about the final desired index EA. IPCR database leakage, EQ10, measures how much the user learns about the database D, now conditioned on knowing their own X and I. IYM, QX, IN, XI, NXI. Again, the goal is to minimize this leakage. This IPCR setting is significantly more challenging due to the need to protect the immutable set I as well. Okay, let's get into the actual solutions proposed in the paper. We'll start with the schemes designed for the standard PCR setting where all features are potentially mutable. All three schemes we'll discuss first. Baseline PCR, diff PCR, and mask PCR share some common ground. They all assume encode replicated servers. The database D is fully copied onto two independent non-colluding servers.
And they all initially use the squared A2 norm, Euclidean distance squared, as the distance metric dxi. For shorthand, let's just write dx to mean the square distance between the user's input X and the IT database sample Y, so dxy by 22.
All right, NNT2 servers, NE2 distance. Let's start with the first one, the baseline PCR. How does this foundational scheme actually work? What does it achieve?
The baseline PCR scheme is laid out first, and it really sets the stage. Its properties are formally stated in Theorem 2. It guarantees perfect user privacy, satisfying that I, X, QX, and D equals 0 constraint for each of the two servers. The communication cost involves the user uploading essentially two gay symbols, 2 vectors of dimension D, and downloading 2 M symbols, 2 vectors of dimension M, 1 from each server. So the total is roughly 2 D plus M symbols exchanged over the finite field. And speaking of the finite field, it requires FQ, where Q is chosen to be larger than the maximum possible square distance. Specifically, if R is the maximum possible value for any single feature coordinate after quantization, say 0R, then the maximum possible square distance, D, could be up to DR2. So they require QDR2.
Why does Q need to be that large?
It's crucial to avoid ambiguity caused by the wraparound arithmetic in FQ. If Q were too small, two very different squared distances, say D1x and D2x, might accidentally become equal after taking the result modulo Q. By choosing Q larger than the maximum possible value of dix, we ensure that all the distances D1x, DMx are uniquely represented within the field FQ. There's no collision due to the modulo operation.
Okay, so Q is large enough to hold all possible distance values distinctly. How does the user actually query the servers privately?
This is where the one-time pad comes in. The query generation is described in equation 14. The user first generates a random vector z of the same dimension d as their input x. Each component of z is chosen uniformly at random from the finite field FQ. This z is the one-time pad. The user also needs two distinct non-zero elements from the field. Let's call them alt1 and I2. These are public parameters known to the user and the servers. The user then constructs two queries. The query sent to server n, where n is 1 or 2, is qxn plus I and z. So server 1 gets x plus a1z, and server 2 gets x plus the oz. Because z is a uniform random vector and unknown to the servers, and it's used only once for this query, each qxn looks like pure random noise to the respective server. By Shannon's one-time pad theorem, ix qxn equals 0, the query reveals absolutely nothing about the user's secret input x.
Perfect user privacy for the input X is achieved right there. Now, what do the servers do with these random-looking queries?
Okay, now for the server's answer computation, equations 15-16. Each server n receives QXN. For every sample y in its copy of the database D, for I from 1 to m, server n computes a value x and ei. This value involves the squared Euclidean distance between its database sample y and the query QXN it received, y qx air 22. But there's an additional twist for privacy. The user and servers also need to share m additional independent random values from FQ, let's call them Z1, AEF. These act as one-time pads for the distances themselves. The actual answer computed by server n for sample I is AK, AXNI equals E, QXN22 plus ANZI. Now, let's look closely at that square distance term, E, QXN22. We can substitute QXN dx plus NEZ is EN plus NEE equals AX and DD22. If you expand this squared norm using AB2, AE2, ATB plus B2, you get U with X, U by 22, X, E, X, D plus NEC, Z plus NEC2 plus NEC, Z. Remember, E by 22, so strength T plus NTVCC, SN plus NTVC plus NEZ, NE plus NEC, Z to NZ, Z plus NEZ plus NZ.
Whoa, okay, that looks complicated. How does the user make sense of that? It seems to have the distance d buried inside, but also lots of terms involving the secret random vector z and the random paths z.
It looks messy, but here's where the magic of the Vandermonde matrix comes in for the user's decoding. Equation 17 to 18. The user receives x1i from server 1 and x2i from server 2 for each i. Notice the structure of x and I. It's a quadratic polynomial in I. X and I at x plus n is 2y xtz plus z plus n to 2 z22. The user knows x. They generated z so they can compute the term z22. They can subtract the answer z22 part from each received answer, x and I. Let x and I, x and I, x and I, and to z22. Now for each I, the user has two equations, a plus 1i dex plus a plus 20 xtz plus z, a plus 2i xz plus a plus 2i stz plus z. This is a system of two linear equations in two unknowns. The unknowns are dies and the term megas 2x, xtz plus zi. Let's call this second unknown day for interference term 1. So we have x1x plus I was 2i plus x 2i. This can be written in matrix form. x1i was 101x, x1 quadrant pi. Right. The matrix 1 equivalent 1 is exactly the Vandermonde matrix V2 constructed from I and I.
There it is, the Vandermonde matrix.
Exactly. Since ANO1 and ANO are distinct and non-zero, V2 is invertible. The user knows V2, since ANO1 and ANO2 are public, and can compute its inverse V21. To find the unknowns, the user just multiplies the vector of adjusted answers by V21 die x V2 to 1, a go 1 I die on y to 1. This calculation perfectly recovers both die and the interference term 2 for each sample I from 1 to m. The user only cares about dies, the square distance. They now have the exact value of dies for all I.
That is incredibly clever. The one-time pad z hides x, the other one-time pad z help mask the distances within the protocol, and the Vandermonde structure lets the user perfectly strip away all the randomness and recover the true distances.
Precisely. Once the user has recovered d1x, d2x, dmx, the final step is trivial. They just find the index I that corresponds to the minimum value among these recovered distances. That index is state.
And the user privacy regarding die, does server n learn which I had the minimum die?
No, because server n never sees the actual times values. It only computes x and I, which is heavily masked by the random z and xi. Furthermore, the structure of the answer x and I is the same for all I. There's nothing in the computation done by server n or the answer it sends back that distinguishes the index lay from any other index.
Sure.
So qxn a could the 0 holds as well.
Okay, let's quickly recap the cost for baseline PCR. Upload is TODI symbols, 2 vectors qx1, qx2. Download is 2m symbols, 2 answer vectors x1, x2. Total communication 2D plus m. Computation for the user involves generating z, forming queries, receiving answers, doing m Vandermonde inversions, which is fast for 2 by 2, and finding the minimum of m values. Roughly OD plus m work. Computation for each server involves calculating m answers. Each answer takes OD time for the dot products and norms. So server computation is roughly OMD. Is that about right?
That's a perfect summary of the costs. And as remark 1 in the paper points out, this basic structure is quite flexible. While we focused on the U2 norm, the core idea of using the n coefficients and the random vector z combined with Vandermonde decoding can be adapted. For example, if you wanted to use the OT norm for some even integer k, you would likely need Ender's k servers instead of 2, because the expanded distance expression would become a polynomial of degree k in on, requiring a k xk Vandermonde matrix to decode. Or if you wanted to use a simpler metric like the dot product dxy equals ytx for finding the maximum dot product, that also leads to a quadratic form in ANHON, so it could likely be done with n to 2 servers similar to the YOTU case. The framework is adaptable.
Okay, baseline PCR works. It's perfectly private for the user's input x and their choice, but as we discussed, the user does learn all the exact squared distances d1x, en(x). This feels like it might leak a fair bit about the institution's database D. Can we do better on database privacy?
Exactly. This is the motivation for the next scheme, diff PCR, which stands for difference PCR. Its primary goal is to reduce that database leakage, IYM, AGX, NX, compared to baseline PCR. Theorem 3 describes its properties. It achieves this lower database leakage. The communication cost is slightly lower, upload is still taken, but download is 2M1 because it deals with M1 differences. Total is roughly 2D plus M1. However, there's a trade-off. It requires a larger finite field size. Specifically, Q needs to be greater than 2DR2 more, twice as large.
Let me guess. Because differences can be negative.
You got it. The squared distances DRT are always non-negative and bounded by DR2, but a difference DRT key could range from DR2 to plus DR2. To represent this full range of positive and negative values uniquely with an FQ without wraparound ambiguity, we need roughly double the field size, so Q2 DR2.
Okay, larger field size, slightly less download. What's the core idea to reduce leakage?
The core idea is simple, but effective. Instead of having the servers compute something that allows the user to recover each die individually, Have them compute something that allows the user to recover only the differences between adjacent squared distances, like dix, di plus 1x. The intuition is that knowing only the differences between values leaks less information about the absolute values themselves.
Makes sense. How do they achieve this?
The user's query QXN equals x plus nz is exactly the same as in baseline PCR. Perfect user privacy for x is maintained. The difference is in the server's answer computation, equations 21, 23. Server n still uses the shared random pad zi, but now for each I from 1 to n1, it computes AXNI equals EA QXN22 YI plus 1, QXN22 plus NZ. It's calculating the difference of the squared norms between sample I and sample I plus 1 relative to the query QXN, and then adding the random pad term. Now let's expand those squared norm terms again, just like we did for baseline. Remember E QXN22 plus ANI plus ANN2Z2, where A is the interference term related to U. Similarly for YI plus 1. When you take the difference, E QXN22 YI plus 1 QXN22, the NN2Z22 terms cancel out. What's left simplifies to DUX DI plus 1 plus ZI. This is just another combined interference term involving Z and Z. So the answer from server N for difference I is beautifully simple in structure, AXNI DX DI plus 1X plus NI.
Okay, that's neat. The quadratic term vanished. So now the user receives AX1I and X2I for each difference I from 1 to M1. They again have a system of two equations, AX1I DI plus 1X plus AX2I plus 1X plus ANS2Is. And again, this looks exactly like the Vandermonde V2 system.
Exactly. The user's decoding uses V21 again. For each I from 1 to M1, the user multiplies the vector AX1I AX2IT by V21. This perfectly recovers the two unknowns, dx, di plus 1x, the difference of square distances, and the interference term I. So at the end of this, the user knows d1x, d2x, d3x, dm1x, dm/dfs. They know all the adjacent differences, but not the individual dix values themselves.
But wait, if I only know the differences, how do I find the index that corresponds to the minimum dx? This seems like a puzzle. If I know a, b, and bc, how do I know if a, b, or c is the smallest?
That's the clever part, detailed in algorithm 1. The user can still find the index of the minimum distance without reconstructing the actual distances. It relies on the properties of arithmetic in the finite field FQ, specifically the large field size Q to DR2. Remember, the actual difference dx, djx, lies in the range dr2, dr2. The field FQ represents numbers from 0 to Q-1. We can think of the numbers from 0 to DR2 as representing positive differences, and the numbers from QDR2 to Q-1 as representing negative differences, due to the wraparound. The middle range from DR2 plus 1 to QDR2-1 should ideally not occur if Q is chosen large enough. The algorithm works iteratively. It starts by assuming E equals 1. Then for I, from 1 to M1, it looks at the recovered difference diff equal dx, di plus 1x. If d falls into the negative range, specifically if the paper uses dr2 plus 1 q1, which corresponds to negative results modulo q, it implies that di is actually larger than di plus 1x. In this case, I plus 1 is a better candidate for the minimum, so the algorithm updates its current guess for the minimum index to I plus 1. If different falls into the positive or 0 range, 0 big point dr2, it means dix is di plus 1x. So the current guess for the minimum index remains unchanged. By iterating through all the differences d1, d2, d2, d3 dec, this process effectively performs pairwise comparisons and bubbles up the index corresponding to the overall minimum distance, using only the information contained in the differences and the field representation.
That is really subtle. By checking which range the difference falls into within the large finite field, they can deduce the ordering or without knowing the actual values. Very clever. So diff-PCR maintains perfect user privacy, has slightly less download cost, requires a larger field queue, and achieves lower database leakage because the user only learns the differences di x di plus 1x.
Precisely. The costs are upload 2N, download 2M1. Computation complexity is similar to baseline PCR for both user and servers.
Okay, that's diff PCR. Now what about the third approach, mask PCR? Masking sounds intriguing. How does it try to boost database privacy?
Mask PCR takes a different tack to reduce database leakage compared to baseline PCR, as outlined in Theorem 4. Like baseline, it uses ND2 servers. Its communication cost is 2D plus M, the same as baseline. And interestingly, it works with the original finite field size requirement, QDR2. It does not need the expanded field size that diff-PCR required.
Okay, same comms, cost, and field size as baseline. What's the mechanism? How does it mask?
The core idea is to add randomness directly to the distances before they get encoded in the protocol. The user query, QXN equals x plus INZ, is again exactly the same. User privacy for x is still perfect. The servers still share the random pad ZI. But now they also need to share another set of M random values. Let's call them 1. These are the masks. Each mask is chosen uniformly at random from a specific range. 0, daemon, 1.
Daemon, what's that?
Daemon is a crucial parameter for mass PCR. Theoretically, it's defined based on a set of rejected samples. Let DC be the set of all possible rejected inputs. Daemon is the minimum difference between any two distinct squared distances from a point X in GC to any two accepted samples AJ in the database D. So daemon in die X DJ over all X in DC and all IJ. It's the smallest gap between any two squared distances you might encounter if you're a rejected user.
That sounds complicated to calculate. Does the user need to know DC?
That's a great point. Theoretically, the scheme's proof in Lemma 1, Appendix 8.2, relies on assuming the user's X is in DC to guarantee that daemon is well-defined and the masking works perfectly. However, Remark 3 acknowledges this is impractical. In practice, daemon would likely be estimated empirically from the database D itself, perhaps by looking at the minimum distance difference between accepted samples or using some domain knowledge. It becomes a system parameter chosen by the institution. Let's assume for now daemon is some positive integer known to the servers. So each mask is chosen randomly between 0 and daemon 1.
Okay, so they have these random masks. How are they used in the server's answer? Equation 27.
Server in receives QXN. For each sample Y, it computes XNI QXN 22 plus stage I plus INE Z. It's calculating the same squared norm as in baseline, but it adds the mask before adding the final random pad Z. Now let's expand Y QXN 22 again, DX plus INE plus INA. So full answer is cs.NI plus IN plus AA plus I plus 88 plus INE Z22, ISNI plus IXNI plus IN ASNI plus INT Z to 22.
This looks very similar to the baseline answer structure. It's quadratic in X. The only difference is that the constant term, the term without X, is now die X plus I instead of just die.
Exactly. So the user's decoding equation 28 works almost identically to baseline PCR. The user receives AKX1I and AKX2I. They subtract the known AKX-Z22 term. They're left with a V2 system of two linear equations. The unknowns this time are dies plus I and the interference term I.
Using V21, the user perfectly recovers both of these. So for each sample I, the user learns the value X plus I. They learn the true squared distance plus the random mask. They do not learn the original die.
If they only learn the mask distance dies plus I, how can they find the index corresponding to the minimum actual distance dies?
Doesn't the mask mess up the ordering?
This is the core insight of mass PCR. The mask I is specifically chosen to be small enough that it preserves the relative ordering of the distances, at least for finding the minimum. Remember, I is chosen randomly from 0 times daemon 1, and daemon is ideally the minimum possible difference between any two distinct squared distances, dx and dx. Let d be the index of the true minimum distance, so dx for all I. Consider any other index j. We know that dx by definition of daemon. Now the user observes the masked values, dx plus time and djx plus j. Let's look at their difference. dx plus dx plus dx plus, we know djx, dx daemon. We also know that dj is between 0 and daemon 1 and is between 0 and daemon 1. Therefore, the difference must be strictly between dx mean and plus daemon. It's in the range of daemon 1. So the total difference is something daemon plus something daemon. This sum must be strictly greater than 0. dgx plus sin dx plus ind. This means that dgx plus d is always strictly greater than dx plus 8d, even with the random masks added. The masked value for the true minimum I will still be the smallest among all the observed masked values.
That's brilliant. Because the mask is chosen to be smaller than the minimum possible gap daemon between distances, adding the masks can't change which distance is the overall minimum. It might shuffle the order of things that are very close, but it won't make something that was far away suddenly look like the closest.
Precisely. The user simply computes all the masked distances dix plus I for I was 1 to m, and then finds the index I that gives the minimum masked value. That index will be the correct d. Let's walk through that quick example from the paper. Suppose X will be the correct A, and the database has two accepted samples, Y1 equals 20, 0t, and Y2, 1, Y2, 0, 20t. The squared L2 distance D1X, Y1 by 2 plus 0, 2, 2 plus 1, 902 plus 902, 902 plus 902 times 1 is 61, plus 4 is 365. Squared L2 distance D2X, Y2 by 2 by 2 plus 22 plus 182 plus 182 plus 1 plus 324 was 325. Clearly D2X is smaller, so it's used 2. The difference is D1X, 32X, 365, 325. Let's do 40.
Oh, wow.
Let's assume daemon was determined to be, say, 40 or less. The masks 1 and 2 would be chosen randomly from 0.39. Suppose 1 involved 2 equals 30. The user compares 375 and 355. Since 355 is smaller, the user correctly concludes that 2 is 2. The masking preserved the ordering of the minimum.
Okay, that makes perfect sense. The mask hides the true distance value, but is designed not to hide which one is the minimum. And the costs for mask PCR.
Same as baseline PCR. Upload 2pen, download 2M, total 2D plus M, field size QDR2. Computation complexity is also similar for user and servers. The calculation of dmin is considered a one-time pre-processing step done by the institution. Remark 2.
So we have these three PCR schemes: baseline, GIF PCR, and mask PCR. Both diff and mask claim to offer better database privacy than baseline. Can we compare them rigorously? Why do they leak less?
Yes, we can compare their database leakage, IYM, AXNX, theoretically least relative to the baseline. For baseline PCR, the user perfectly recovers the entire vector of squared distances, dx equals d1x, dmx. So the leakage is essentially the information content of this vector, IYM, dxx. Knowing all distances implicitly leaks information about the locations of ym relative to x, equation 35. For diff PCR, the user only recovers the vector of differences diff(x) equal dx-dtx, dm1x, dmx. By the data processing inequality, a fundamental theorem in information theory, if you process data, like taking differences, the mutual information cannot increase. Since diff(x) is a function of dx, we must have IYM diff(x), IYM dx. Knowing only the differences leaks less, or at most the same information about ym, than knowing all the absolute distances. Equation 36. For mask PCR, the user recovers the vector of mask distances dmask d1x plus 1x plus m, here 1 is a vector of independent random variables, also independent of ym and x. The leakage is IYM dmasked x.
The paper shows, equations 3741, using properties of mutual information that adding this independent noise cannot increase the information about ym. Therefore, IYM dmasked x, IYM dx. The random mask adds uncertainty, reducing the information revealed about ym.
Okay, so both diff PCR and mask PCR are provably better than baseline in terms of database leakage. What about comparing diff PCR versus mask PCR? Can we say analytically which one leaks less?
That's much harder to say definitively just from the theory. Remark 4. The leakage of diff PCR depends on the information content of the differences. The leakage of mask PCR depends on the information content of the masked values, which in turn depends on the size of the mask, related to daemon. Since daemon itself depends on the specific distribution of the database D and potentially the rejected set DC, it's difficult to make a universal analytical comparison between the leakage of diff PCR and mask PCR. Their relative performance might depend heavily on the characteristics of the actual dataset.
Which is why numerical experiments are needed to compare them in practice.
Exactly. The theory tells us they're better than baseline, but experiments are needed to see how they stack up against each other on real or synthetic data.
All right, let's move on to the next level of complexity, handling those immutable features. This is where things get even more practical, addressing the fact that users often can't or won't change certain aspects of themselves. How do the IPCR schemes work?
Yes, the immutability constraint is absolutely crucial for making counterfactuals truly actionable. As we defined earlier, the user privately specifies a set I of feature indices that cannot be altered. The goal is to find the closest sample yi in the database that matches x on these immutable features. Yi equals x is I. And remember, the set I itself is private. This need to protect both x and I adds complexity. A general consequence mentioned in Remark 6 is that all the proposed IPCR schemes require more servers than their PCR counterparts. Typically, they need N3 replicated servers, up from M3 for PCR. That third server provides the extra dimension needed to handle the privacy of the immutable set I simultaneously with the privacy of X.
Okay, N3 servers now. The first approach mentioned is the two-phase IPCR. Sounds like it involves multiple steps. Tell us about phase 1.
Right, the two-phase IPCR scheme, Theorem 5, breaks the problem down logically. It uses N3 servers. The communication cost is higher, roughly 90 plus M symbols in total, and it operates over a field FQ where Q are DR2, similar to baseline PCR. Phase 1, finding the eligible set, see equations 42-49. The goal of this first phase is solely for the user to privately determine the set of the indices I of database samples, E, whose immutable feature is E, match the user's immutable features. How does it work? The user first creates a binary indicator vector, let's call it H1, where H1K1 if feature K is immutable, i.e. Ki, and H1K is 0 otherwise. The user then generates two independent one-time pad vectors, Z1 and Z2, both of dimension D. They construct queries QXen for each of the N3 servers in 1, 2, 3. These queries are pairs of vectors, QXen equals H1 plus ENZ1, XH1 plus ENZ2. Here, E none are distinct non-zero elements from FQ. We need 3 now, E none and 2A3. And D denotes the element-wise Hadamard product. So XH1 is a vector where the K element is XK if K is immutable and 0 otherwise.
These queries securely encode both the immutable mask H1 and the values of the immutable features, each using the one-time paths Z1 and Z2.
Okay, user sends these two-part padded queries to the 3 servers. What do the servers compute? It looks like equation 45 is quite complex.
It is a bit involved, yes. Each server N receives QXN equals QN1, QN2. For each database sample yi, the server computes an answer AXN. This involves another layer of randomization using shared random non-zero scalars IA, one for each yi chosen from FQ. The core calculation is I, QN1, yi, QN2, 22. This term essentially calculates a mask distance related only to the immutable features. The full answer AXNI EQ 4547 includes this term plus additional padding terms involving n and shared randomness z to ensure privacy. It turns out to be a quadratic polynomial in ANA.
Quadratic again, so the user can decode using the Vandermonde matrix V3 since n and 3.
Exactly. The user's decoding in phase 1 uses the inverse of the 3x3 Vandermonde matrix V3 built from R2 A3. After receiving AXI1, AXI2, AXI3, and applying V31, the user recovers the term RH1 IH22. Now here's the key insight. The vector H1 IHX has non-zero entries only where feature K is immutable. H1K1 AHE is different from XK. Therefore, H1H22 will be exactly 0 if and only if U matches X on all immutable features, i.e. AH8. If even one immutable feature mismatches, this squared norm will be non-zero. Since I is a random non-zero scalar unknown to the user only learns whether the result IH1HX22 is 0 or non-zero. They don't learn the magnitude of the mismatch or which specific features mismatched. So by checking if the decoded result is 0, the user perfectly identifies the set HHA, the indices of all eligible samples.
Wow, okay. Phase 1 successfully finds the indices of the matching samples without revealing I or X to the servers and without learning anything extra about the non-matching samples. What if A is empty or has only one element?
Good point. If A turns out to be empty, no match is found. The process stops. There is no counterfactual satisfying the immutable constraints. If A contains exactly one element, say index J, then A must be J, and the process also stops. The user has their answer. If A has 2 or more elements, the user proceeds to phase 2.
Okay, so phase 2, finding EA, closest match within A, equations 50-59. We now know the set A. How do we find the closest EA among only those in A without revealing it itself?
This phase is quite similar in spirit to the baseline PCR, but adapted to work only on the subset. First, the user creates a new binary indicator vector H2, where H2i equal 1 if A, that is, I is an eligible index found in phase 1, and H2i equals 0 otherwise. This H2 vector effectively masks the database based on eligibility. The user generates 2 more one-time pad vectors, Z3 and Z4. They send new queries QXMN to the N3 servers. These queries encode the masked H2 and the user's full input vector X. QXMN equals H plus ANZ3, X plus ANZ4. Notice X here is the full vector, as we need to compute distances based on mutable features now.
Okay, queries encoding the eligibility mask H2 and the full X go to the servers. What do they compute now?
The servers use these queries to compute answers, AXMNI for each I from 1 to M. The calculation is designed to cleverly use the H2 mask. Essentially, server N constructs a masked version of the database sample yi, effectively calculating H2I1. If I is not in each H2I, so this becomes 0. If I is in each 2I1 and it's just yi, the server then computes something related to the square distance between this masked sample and the padded X from the query. Details in EQ 5357. Again, the resulting answer, AXMNI, turns out to be a quadratic polynomial in AN.
Quadratic again, so V31 for decoding.
You've got it. The user's decoding in phase 2 uses V31 on the received answers X as MNI. This time the user recovers the value H2I by 22. Let's see what this means. If I AA, then H2I equals 1. The user recovers yi by 22, which is exactly die, the square distance they need for the eligible sample yi. If I x2i, then h2i equals 0. The user recovers 0i by 22 equals passes by 22 equals by 22. They just get the squared norm of their own input vector x, a constant value that reveals nothing specific about yi. So the user obtains the true squared distances die only for the relevant samples IA and gets useless constant information for all other samples IE.
It's extremely elegant. Phase 1 identifies privately. Phase 2 calculates distances only for IA privately, revealing nothing about samples outside. The user then just finds the minimum among the recovered die values for IA to get I.
Exactly. That completes the two-phase IPCR.
What about the costs? You mentioned 9 plus M total communication.
Yes, let's break that down. Phase 1. Upload is 3 tinch equals 6 brilliants, 3 servers, 2 vectors each. Download is 3M equals 3M. Phase 2, upload is 3M plus D. Encoding H2 takes M, X takes D. Download is 3M. So total upload equals 6 brilliants plus 3M plus 3M plus 3M. Total download at 3M plus 6M. grand total communication equals 9 plus 9m. Okay, my earlier 9d plus m was slightly off. It's 9d plus 9m. Still quite substantial.
That is a lot of communication. Is there any way to optimize that?
Remark 5 mentions a potential alternative using N4 servers. It seems counterintuitive, but by using properties of polynomial interpolation with 4 points, they suggest it might be possible to reduce the communication cost, particularly if the dimension d is larger than the database size m. But the primary scheme uses N3.
Okay, two-phase IPCR. Conceptually clear, private, but communication heavy. Now, what about the alternative, the single-phase IPCR? You said it's simpler, potentially lower communication, but has a trade-off.
Correct. The single-phase IPCR theorem sucks. Aims to achieve the same goal, finding a by privately, but in a single round of interaction. It uses NT3 servers. The communication cost is lower. Upload 6 pen, download 3m for a total of 6 pen plus 3m. It's a noticeable improvement over 9d plus 9m.
Lower communication is good. What's the catch? You mentioned a trade-off involving field size.
Exactly. The catch is the required finite field size Q. It needs to be significantly larger. The requirement is roughly Q FLR2 plus DR2, where F is the maximum possible number of immutable features a user might specify, and L is a special scaling factor chosen to be very large, specifically LDR2. This L factor is the key to making the single-phase approach work, but it dramatically increases the required Q.
Okay, why this huge L and the massive field size? How does the single-phase idea work? Equation 60.
The core idea is to encode both the immutability constraint and the distance calculation into a single value, using this large scaling factor L. The user defines a single vector h of dimension d. If feature k is mutable, ki, then hkl. If feature k is mutable, kai, then hk each 1. This vector h now combines the immutability information via the large value L with a default weight of 1 for mutable features.
Okay, H has L for immutable, 1 for mutable. What's the query? Equation 61, 62.
The user generates two one-time pad vectors z1, z2. They send queries qx into the N3 servers, qxn plus nz1 ah plus nz2. This query privately encodes the user's input x and their special combined vector h.
Servers receive this. What answer do they compute? Equation 63, 66.
Each server n computes an answer ax and I for each sample yay. The calculation is designed to compute a value related to yxt, yxh. This expression looks complicated, but let's break it down. It's a weighted sum of square differences, yk2, where the weight for feature k is given by hk. So it's ahk xk2 over all features k. The actual server answer ax and I involves computing this based on the padded queries and adding more padding terms. Again, it conveniently results in a quadratic polynomial in X.
Quadratic again, so V31 for decoding.
Yes. The user's decoding, EQ6769, uses V31 to recover, for each I, the value V, yxtex.
Okay, the user gets this value V for every sample I. How does this tell them which is the closest eligible counterfactual key? This seems different from getting distances directly.
This is where the large scaling factor L and the huge field size Q become critical for decodability. Let's analyze the value P and xk and k kubian. Case 1, I and A immutable features match. If y matches x on all immutable features I, then y xk 0 whenever hk. And so the sum only includes terms where k is mutable, erj k equals 1. In this case, v me enk over mutable k. This is just the squared Euclidean distance calculated over the mutable features only. Let's call this dmx, he and ei, since eae owe the full distance dmx ei. So I annotate if the user recovers v egal. The maximum value this can take is roughly dir2, distance over dn immutable dimensions. Case 2, at least one immutable feature mismatches. If y does not match x on all immutable features, then there is at least one key AA where yhk, for this khk, L ysk2 is at least 1. So the sum vhk ha2 will contain at least one term multiplied by L. The value v will be approximately L, number of mismatched immutable features, plus distance over mutable features. Since L was chosen to be very large, LDR2, this value vi will be significantly larger than any possible value from case 1. Specifically, the values for case 1 fall in the approximate range 0, dir2. The values for case 2 fall in the approximate range L, FLR2 plus dir2, where FEI is max immutable features. Because L is so large, these two ranges are completely disjoint.
Ah, I see. The value V itself tells the user two things at once. If V is small in the first range, it means I must be an eligible sample, and V is actually the true squared distance D. If V is huge, in the second L-dominated range, it means I is ineligible.
Exactly. The user calculates V for all I. They discard all the huge values corresponding to ineligible samples. Among the remaining small values, which are the true distances due for I, they simply find the minimum. The index of that minimum is AI.
That's a very different but also very clever way to achieve the result in one phase. Costs. Upload 6 pins, download 3M, total 6 pins plus 3M, but requires a much, much larger field size queue.
That's the essence of the single-phase IPCR.
So we have two-phase IPCR, higher communication, smaller field, and single-phase IPCR, lower communication, huge field. Which one is better for the institution's database leakage?
This is where the two-phase scheme generally wins, offering lower database leakage. Let's analyze why, connecting back to our leakage definition IYM answers XI. There is a common leakage component, EQ 73 to 76, that both schemes inevitably reveal. The user must learn which samples satisfy the immutable constraints. Let EM be a binary vector where EI1, E and O otherwise. Both schemes effectively reveal EM to the user. The minimum unavoidable leakage is HEMX. The two-phase advantage comes from what happens after EM is known conceptually. In phase 2, the user only learns the actual distances dias for samples I where EI1. For samples I where EI0, that is AEIM, the user learns nothing further about E, they just get the constant by 2. The leakage is essentially HEMXI plus IIYDXX or INDX refer only to the eligible samples. See analysis around EQ 102, 105. The single-phase disadvantage is that the user observes the value VI, KL plus R2DH, for all I from 1 to M, including those where EI0. If I am in, the value V falls into that large range, KL plus R2DI, where K is the number of mismatched immutable features for sample I. Even though these values don't directly give dies, they still leak information about E specifically. They leak K, the number of immutable features that mismatch X. This is more information about the ineligible samples Y, where IE, and is revealed by the two-phase approach, which reveals nothing about them in phase 2.
So knowing how many immutable features mismatch from single phase is more leakage than just knowing whether they mismatch or not from phase 1 of two-phase and then learning nothing more about the non-mismatching ones.
Precisely. Therefore, the two-phase IPCR scheme generally offers lower database leakage.
What about that edge case where all features are immutable, IELD?
Yes, the paper discusses this. If I and the user X was rejected, then O must be empty. No accepted sample Y can exactly match X. In two-phase, the user runs phase 1, discovers A is empty, all decoded results are non-zero. The process stops. Leakage is just HEMXI, where EM is the all-zero vector, which likely has low inter-pi leakage. No phase 2 runs. In single phase, the user still computes all VI values. All VI will fall into the large L-dominated range, since all features are immutable and mismatch the accepted Y. The user deduces empty. However, they still observed VI for all I, revealing the number of mismatched features K, which is D, in this case V is different from X, for all M samples. This constitutes non-zero leakage about the database YM, even though the answer is no counterfactual exists, so two-phase leaks less in this case too.
This is fascinating. We've covered finding the nearest counterfactual privately and handling immutable features privately. But what if nearest isn't always the most actionable for the user? For instance, maybe changing my income by $10 is mathematically further than changing my job title, but changing income is much easier for me to actually do. Can the system incorporate my personal preferences about which features are easier or harder to change?
Absolutely. This is where the schemes get even more sophisticated and arguably more useful in practice. The paper introduces user actionability by moving from the standard U distance to a weighted U distance. The weighted distance equation 77 is defined as dxy_yx_t_wyx_tiedge_iwsk2. Here, W is a private weight vector provided by the user. Each component, WK, represents the user's cost or reluctance to change feature K. A higher WK means the user really doesn't want to change feature K. We can assume WK values are positive integers, say up to L1. The goal now is to find the counterfactual Y that minimizes this weighted distance to X. And crucially, the weight vector W itself must remain private from the institution.
Okay, so now we have two private inputs from the user, their feature vector X and their weight vector W. This sounds like it will require more machinery.
It does. Let's look at the PCR plus schemes, which add these weights but without considering immutability for now. Theorem 7 lays out the properties. A key consequence of having the additional private vector W is that these schemes now generally require n=2 servers, up from n=2 for standard PCR. We need that extra server again to handle the privacy of W simultaneously with X.
Makes sense. How does baseline PCR plus work? Equation 7884.
It builds directly on baseline PCR. Requires n3 servers. Field size Q needs to be larger to accommodate the weighted distances, roughly QD L1R2, where L1 is the max weight. The user query now needs to encode both X and W privately. User generates two one-time pads Z1, Z2. The query to server N and 1223 is QXN equals X plus NZ1W plus NZ2.
Servers receive QXNs equal QN1, QN2. The server answer AXNI is computed based on a calculation related to YIGO QN1 to DIAG QN2, UI QN1. When you expand this using the padded QN1 and QN2, it turns out the resulting answer AXNI is now a polynomial of degree 3 and I, because QN1 has an and QN2 has an, and they get multiplied together effectively. Since the answer is cubic in an, the user needs answers from NT servers to set up the system of 3 equations. The decoding uses the inverse of the 3x3 Vandermonde matrix V3. This allows the user to perfectly recover the desired weighted distance, DIXNI WK GIK for all I. They then find the minimum. Communication cost increases due to N3. Upload is roughly 6 BD download is 3M.
Okay, so adding weights bumps PCR from N2 to NE3 servers because the answer polynomial becomes cubic. How about diff PCR plus and mask PCR plus?
They extend similarly. Diff PCR plus, EQ8588, computes differences of weighted distances. Still uses N3 servers. The required field size Q needs to be even larger, Q2D L1R2, to handle positive and negative weighted differences. User decodes the differences using V31 and uses a modified algorithm 1 to find the minimum index. Communication 6D plus 3M1, leaks less than baseline PCR plus stat, mask PCR plus EQ8991, adds a random mask chosen based on a weighted daemon to the weighted distance, DIX, still uses N3 servers, field size QD L1R2. User decodes the masked weighted distance as DIX plus CM using V31. Lemon 2, Appendix 8.3 confirms that the masking still preserves the minimum index correctly even with weights. Communication 60 plus 3M leaks less than baseline PCR plus rate.
Got it. So adding actionability weights generally requires N3 servers and increases field size requirements, but the core ideas of diff and mask still apply to reduce leakage relative to the weighted baseline. Now for the grand finale, combining immutability and actionability. This is the IPCR plus setting. We have private immutable set I, A and D private weight vector W. This sounds like the most complex scenario.
It is indeed the most complex, requiring careful integration of all the techniques. Theorem 8. First, the weight vector modification, EQ92. The user's private weight vector W needs to align with the immutable set I. For immutable features Ki, the weight WK is effectively set to infinity conceptually, or handled structurally so they aren't changed. The paper suggests setting WK for Kii and letting the structure handle immutability, while for mutable features Ki, the user provides their preference weight WK from 1 to L1.
How does two-phase IPCR plus handle this? Equations 93 and 98.
It extends the two-phase IPCR logic. Phase 1 remains exactly the same as standard two-phase IPCR. It only uses X and I to find the eligible set based on immutable features matching. It doesn't need the weights W yet. This still requires N3 servers. Phase 2 is extended to incorporate the weights W. The user now needs to encode the eligibility mask H2, the full input X, A, and D, the modified weight factor W. This requires 3 one-time pads, Z3, Z4, Z5. The querying to server N in Phase 2 because QXMN appease 2 plus NZ3, X plus NZ4, AW plus NZ5. The server answer XMNI is computed based on a weighted distance calculation involving these 3 parts. Because the calculation effectively involves multiplying terms related to X and W, both padded with N, the resulting answer polynomial becomes degree 3 anyway. Wait, rereading EQ97, it seems the answer polynomial might actually go up to degree 4 if not structured carefully. Let's recheck the paper's claim. Theorem 8 states the communication cost scales with N4. So yes, the complexity requires N4 servers for two-phase IPCR plus A. With N4 servers, the user can use the 4x4 Vandermonde matrix V4A1 to decode the result. The decoded value is HOII XT DIHW, HQIX. If I enter stat, this gives the correctly weighted distance, IWK2, over mutable features. If I enter it gives a constant related to by 2 weighted by W, the user finds the minimum among the valid decoded weighted distances. Costs. Phase 1 and 3 cost 90 plus 3M upload, 3M download. Phase 2 and 4 costs 4M plus D upload, 4M download. Total communication is significantly higher, roughly 17D plus 7M upload and 7M download. Okay, the outline said 14U plus 11M total. Let me re-verify. The upload in P2 seems like 4M plus D toward M plus 8 chord and upload P1 is 6 chord. Total upload 14 P plus 4M. Download P1 3M, P2 4M. Total download 7M. Grand total 14D plus 11M. Yes, the outline was correct. So N4 servers and 14D plus 11M communication.
N4 servers, that's getting complicated. What about single-phase IPCR plus ET? Does it manage to avoid going to 4 servers? Equation 99.
Remarkably, yes. The single-phase approach integrates actionability quite elegantly, still using only N3 servers. It modifies the special vector H used in the query. Recall H had L for immutable, 1 for mutable in standard single-phase IPCR. For single-phase IPCR plus add, the vector H is defined as edge K if feature K is immutable. KHK, HK, the user's preference weight, if feature K is mutable, KH. The scaling factor L now needs to be chosen even larger, LD, L1, R2, to dominate the weighted mutable distances. The query is still QXN plus X plus N's is 1, H plus N's is 2, sent to N is 3 servers. The server answer XNI is computed similarly related to ENXT, EAX. It remains quadratic in age. The user decodes using V31 to get VEAXT, IXT.
How does this V value work now with both L and WN in H?
The logic is similar to before, relying on disjoint ranges. If immutable features match, then VWK over mutable K. This is exactly the desired weighted distance over mutable features. It falls in the range 0D L1 R2. If immutable features mismatch, then V will contain at least one term multiplied by L. Phi will be approximately L num mismatched immutable plus weighted distance over mutable. This falls in the range L FLR2 plus DL1 R2. Again, because L is chosen to be huge, LDL1 R2, these two ranges are disjoint. The user calculates V for all I, throws away the huge values ineligible, and finds the minimum among the remaining small values, which are the true weighted distances for eligible samples.
So single-phase I PCR Plus achieves the most complex goal, immutability plus actionability, with N3 servers and communication costs 6 pins plus 3M. That sounds like the winner.
It sounds appealing, but Remark 7 highlights the crucial trade-off. While the number of servers, N3, and the communication costs, 6PIM plus 3M, are not affected by adding actionability compared to single-phase IPCR, it comes at the expense of a dramatically higher field size requirement Q. The field Q now needs to be larger than FLR2 plus DL1R2, where L itself is larger than DL1R2. This Q can become astronomically large, potentially making computation impractical. So that's a classic trade-off. Single-phase IPCR Plus uses fewer servers and less communication than two-phase IPCR Plus MAT, but demands a potentially infeasible field size. Two-phase IPCR Plus requires N4 servers and more communication, but works with a more manageable field size.
Okay, we've covered a lot of theoretical ground exploring these increasingly complex schemes with their clever privacy mechanisms and trade-offs. Theory is great, but how do they actually perform when tested? Did the researchers run experiments?
They did. The final section of the paper presents numerical results to evaluate two key aspects. One, the accuracy of the retrieved counterfactual, especially considering the need for quantization. Two, the database leakage, empirically measuring how much information the different schemes reveal to the user about the institution's data.
Let's start with accuracy. You mentioned quantization is needed because the schemes work over finite fields, integers, but real data is often continuous. How does that affect things?
Right. Real-world feature values like income, age, sensor readings are often real numbers. To use them in these schemes which rely on finite field arithmetic FQ, these real values must first be quantized. This means mapping the continuous range of each feature onto a discrete set of integers, typically 0R for some chosen integer R. R represents the number of quantization levels. This quantization process inevitably introduces some approximation error. A higher R means finer-grained quantization and less error, but potentially requires a larger field size Q, since Q often depends on R. So there's an accuracy quantization trade-off. More levels R mean higher potential accuracy in finding the true nearest neighbor, but also potentially higher computational communication overhead due to larger Q.
And what about daemon for masked PCR in these experiments? Did they assume X was in that theoretical DC set?
No, they acknowledge the impracticality. For the experiments involving masked PCR, the Facio DC restriction was lifted. The daemon value, which determines the size of the mask, O10 daemon 1, was determined empirically from the dataset itself. A larger field Q allows for a potentially larger daemon to be used, which might offer more masking, but as we'll see, could impact accuracy if daemon is too large relative to the actual distance gaps.
What dataset did they use for accuracy tests?
They used the wine quality dataset from the UCI repository. It has about 4,900 instances, 11 real-valued features like acidity, sugar, alcohol content, and a quality score. They converted this into a binary classification problem. Wines with a quality score above a certain threshold were considered accepted, forming the database D, and those below were rejected, used as the user queries X.
And how did they measure accuracy? Equation 100.
They used a straightforward accuracy metric. For a given rejected input X, let BX be the counterfactual sample retrieved by one of the private schemes after quantization and decoding. Let YX be the actual true nearest neighbor to X in the original unquantized accepted database D. The accuracy for input X is 1 if EX is the same as YX, or potentially if EXX equals X if there are ties, and 0 otherwise. They averaged this accuracy over many different rejected inputs X.
Makes sense. What were the results? Figure 3.
The results, shown in Figure 3, confirmed the expected trends. First, as R, the number of quantization levels increased, the accuracy of all schemes generally improved and approached 100%. This makes sense. Better representation of the original data leads to better results. Second, focusing on mask PCR for a fixed quantization level R, the accuracy tended to degrade slightly as the masking parameter diamond increased. This is also intuitive. A larger mask adds more noise to the distances. While it preserves the minimum, if diamond becomes too large relative to the actual gaps between distances, especially gaps involving the true minimum, the added noise might occasionally cause the wrong sample to appear as the minimum after masking, reducing accuracy. When diamond was set to 1, meaning the mask I could only be 0, mask PCR became equivalent to baseline PCR, and as expected, showed the highest accuracy for any given R.
Okay, so accuracy is generally good, improves with quantization, and mask PCR's accuracy slightly decreases if the mask size diamond gets too large. Now, what about the main event? Database leakage in PCR. Did the experiments confirm that diff and mask leak less than baseline?
Yes, this was a key focus. They numerically estimated the mutual information, IYM AXNX, for the baseline diff PCR and mask PCR schemes. The technical details of how they computed this mutual information are in Appendix H or 4, likely involving complex estimation techniques.
What data did they use for the leakage tests?
They used two data sets here. First, a small synthetic data set R4D2M5, where they could potentially compute the leakage more accurately. The results are in Table 2. The findings were clear. Baseline PCR had the highest leakage score, around 3.13 bits. Diff PCR had significantly lower leakage, around 2.04 bits.
Right.
Mass PCR had the lowest leakage, and it decreased further as daemon increased. 0.91 bits for daemon 2, 0.78 bits for daemon 3. This numerically confirms the theory. Diff PCR and mask PCR do indeed reduce leakage compared to baseline, and mask PCR can potentially offer even lower leakage than diff PCR, especially with a larger daemon.
That's on synthetic data. Did the trend hold on real data?
Yes. They also used the COMPASS dataset, a real-world dataset often used in algorithmic fairness research. It has about 772 instances and 20 features after preprocessing. They quantized features to R10. Due to the complexity of calculating mutual information on this larger, higher dimensional dataset, they had to use sampling techniques to estimate the leakage. The results were in Table 3. The trend was similar, although the absolute differences were smaller. Baseline PCR had the highest estimated leakage, around 1.5144 bits. Diff PCR was very slightly lower, around 1.51436 bits. Mask PCR was again the lowest, around 1.51427 bits. So even on more complex real-world data, the relative ordering holds. Baseline leaks the most, then diff PCR, then mass PCR leaks the least. This demonstrates the practical effectiveness of the leakage reduction techniques.
Okay, that's compelling evidence for the standard PCR schemes. What about the database leakage in IPCR schemes? Did they compare two-phase versus single-phase leakage experimentally?
They did. They conducted experiments comparing the leakage of two-phase IPCR and single-phase IPCR on a synthetic dataset, R3D3M3. Calculating leakage for IPCR is even more complex because it depends on the private immutable set I. For single phase, the leakage is I, YM, V, IM, X, I, where Vi are those combined values the user recovers, EQ 101. For two-phase, the leakage is conceptually HEMX, I leakage from learning the eligible set, plus IY, IX, IAEM, leakage from learning distances only for the eligible set, EQ 102.
And the results.
On Table 4. The results in Table 4 strongly supported the theoretical analysis. Two-phase IPCR consistently showed lower leakage than single-phase IPCR for all tested sizes of the immutable set I. This confirms that revealing only the eligibility mask EM and the distances just for U leaks less information than revealing the combined Vi values for all samples. They also observed some interesting patterns related to the size of the immutable set I. For single-phase, the leakage seemed roughly symmetrical, being similar for I and DI. For two-phase, the leakage actually decreased as the size of the immutable set I increased. This makes intuitive sense. A larger I means the eligible set is likely to be smaller. If A is smaller, learning the distances for only I in phase 2 reveals less information about the overall database YM. And finally, the I'd case we discussed earlier, when all features are immutable. The experiments confirm that two-phase leakage dropped to essentially 0, as expected since E is an empty and phase 2 doesn't run. But single-phase still showed non-zero leakage because the user still processed the Vi values for all M samples, learning something about their mismatches even if no counterfactual was found.
Fantastic. The experiments seem to nicely validate the theoretical privacy analysis for both PCR and IPCR settings. Hashtag tag outro. We have really gone on a deep dive today exploring the intricate world of private counterfactual retrieval. We started by grounding ourselves in why this matters, the crucial need for transparency and actionable explanations when AI systems, especially those black box models, make decisions that impact our lives in significant ways. Then we pivoted to tackle that often underexplored, but as we've seen, incredibly important challenge of user privacy. How can you get that valuable what-if explanation without having to expose your own sensitive data in the process?
Indeed. And we saw how the solution involves some truly ingenious mathematical constructions. We navigated through the power of Vandermonde matrices, acting almost like universal decoders, and the fundamental strength of Shannon's one-time pad, providing that perfect information-theoretic secrecy for the user's input. We explored multiple schemes tailored for different privacy priorities. There was the baseline PCR, establishing the foundation with perfect user privacy. Then we saw diff PCR and mask PCR, both cleverly designed to reduce the amount of information leaked about the institution's database, offering better protection for their data assets.
And we didn't stop there. We layered on the practical reality of immutable features, those things about ourselves we can't or won't change. We saw how the IPCR schemes, both the two-phase and single-phase approaches, tackled this additional privacy challenge, protecting not just your data X, but also your private constraints I. And finally, we saw how these frameworks can even incorporate your personal preferences, user actionability, using weighted distances, allowing for truly personalized counterfactuals, all while maintaining these rigorous privacy guarantees, albeit sometimes at the cost of more servers or larger fields.
I think the key takeaways from this deep dive are pretty clear. First, counterfactual explanations are incredibly powerful tools. They move beyond just a yes or no to give users real agency and understanding. Second, user privacy isn't just a feature, it's a critical and often overlooked requirement for ethical and truly usable, explainable AI. Third, information theory, especially concepts like the one-time pad, provides a solid mathematical foundation for achieving provably strong privacy guarantees, not just heuristics. And finally, the existence of different schemes like baseline, diff, and mask, and their IPCR variants demonstrates that there are trade-offs. Institutions can potentially choose a scheme that balances communication cost, computational feasibility related to field size, and the level of database leakage they are comfortable with. It shows that powerful AI explanations don't necessarily have to come at the expense of user privacy.
You know, this deep dive really highlights something profound for me. It shows that privacy doesn't have to be bolted on as an afterthought in AI design or seen as some kind of barrier to functionality. Instead, it can be woven right into the core of the system, built from the ground up using elegant, mathematically sound solutions like the ones we've explored today. So as AI becomes ever more deeply integrated into, well, everything, how might these kinds of rigorous privacy-preserving approaches change our expectations for how all our sensitive data is handled online and offline? What steps might you, our listener, start taking to demand and ensure that your digital interactions prioritize your privacy by design? It's definitely something worth mulling over.
Absolutely. Well, thank you for joining us on this very detailed deep dive. If this discussion has sparked more questions, or if you're curious to explore more cutting-edge research in privacy-preserving AI and explainability, please do reach out to us. Until next time, keep digging deeper.